Artificial Intelligence and Robotics Engineering. First semester. Let's explore together. Slide 4, AI.701, Introduction to Artificial Intelligence. Artificial intelligence begins not with algorithms but with fundamental questions about intelligence itself: what constitutes intelligent behavior, whether machines can exhibit such behavior, and how we might engineer systems that perceive, reason, learn, and act in ways intelligent to human observers. This foundational course establishes the conceptual vocabulary, historical context, and methodological frameworks that enable sophisticated engagement with all subsequent AI and robotics coursework, moving beyond popular misconceptions of artificial general intelligence or science fiction tropes to understand AI, a collection of precisely defined techniques for solving specific classes of problems under constraints of computation, data availability, and environmental uncertainty. The 1956 Dartmouth Summer Research Project marks the formal birth of artificial intelligence as a distinct discipline, where John McCarthy, Marvin Minsky, Claude Shannon, Nathaniel Rochester proposed that every aspect of learning or any other feature of intelligence can in principle be so precisely described that a machine can be made to simulate it. This optimism birthed the symbolic AI paradigm, where intelligence was modeled as symbol manipulation. Systems like Logic Theorist, 1956, proving mathematical theorems through logic; General Problem Solver, 1957, solving puzzles through means-ends analysis; and later expert systems like MYCIN, 1974, encoding medical diagnostic knowledge into rule-based architectures that could recommend antibiotics for bacterial infections with accuracy rivaling infectious disease specialists. These systems demonstrated narrow competence within carefully bounded domains but catastrophically failed when confronted with uncertainty, incomplete information, or situations requiring common-sense reasoning, limitations that precipitated the first AI winter of reduced funding during the 1970s when overpromised capabilities met practical constraints. The connectionist paradigm emerged concurrently but gained prominence later. Warren McCulloch and Walter Pitt's 1943 mathematical model of neural activity inspired Frank Rosenblatt's 1958 perceptron learning algorithm, which could classify visual patterns after training but suffered from limitations exposed by Minsky and Papert's 1960 critique, revealing perceptrons' inability to solve nonlinear problems like XOR without hidden layers. This theoretical limitation caused neural network research to lie dormant until the 1986 backpropagation breakthrough enabled training of multilayer networks, leading to the connectionist renaissance of the late 1980s. Contemporary AI presents neither pure symbolic nor pure connectionist approaches but pragmatic integration. IBM's Deep Blue defeating chess champion Garry Kasparov in 1997 through brute force search combined with handcrafted evaluation functions. IBM Watson winning Jeopardy! In 2011 by combining statistical natural language processing with massive knowledge bases. Minds AlphaGo defeating world champion Lee Sedol in 2016 through Monte Carlo tree search guided by deep neural networks evaluating board positions, each milestone revealing that intelligence manifests differently across contexts requiring pluralistic rather than monolithic solutions. Understanding this historical trajectory prevents engineers from repeating past mistakes, overpromising capabilities during hype cycles as occurred with expert systems in the 1980s, abandoning promising approaches prematurely during disillusionment phases, or failing to recognize that today's deep learning successes in perception tasks don't automatically translate to reasoning, planning, or causal understanding where symbolic approaches retain advantage. Problem-solving constitutes the core capability that defines artificial intelligence, transforming ill-defined challenges into computational representations where algorithms can systematically search for solutions. The 8 puzzle provides a concrete illustration, a 3x3 grid with 8 numbered tiles and 1 empty space where the is sliding tiles into numerical order. This seemingly simple puzzle embodies fundamental AI concepts: state representation where each tile configuration defines a unique state space as the graph connecting states through valid moves, goal state as the ordered configuration, path cost as the number of moves required, and solution sequence of moves transforming initial to goal state. Real-world navigation systems operationalize these abstractions. Google Maps representing road networks as graphs where intersections become nodes and road segments become edges weighted by travel time. A * search algorithm expanding nodes toward the destination while prioritizing paths with estimated total cost, distance traveled plus heuristic estimate to goal. Dynamic replanning when traffic conditions change requiring reconstruction of optimal paths in real time. Warehouse robotics confronts more complex problem solving. Amazon's Kiva robots navigating fulfillment centers must solve multi-agent pathfinding where dozens of robots coordinate movements to avoid collisions while retrieving shelves containing customer orders. Constraint satisfaction frameworks ensuring no two robots occupy same location simultaneously while minimizing total travel distance. Partial order planning generating flexible sequences where subtasks like retrieve shelf A and retrieve shelf B may act in either order as long as both complete before deliver to packing station. Medical diagnosis represents problem solving under uncertainty. Mission's rule-based system encoded approximately 450 rules like, if the infection is Primorobacteremia and the site of the culture is blood and the suspected microorganism is Pseudomonas then therapy over Pseudomonas, with certainty factors quantifying confidence. Modern systems like IBM Watson for oncology integrate natural language processing to extract features from unstructured clinical notes, machine learning to identify patterns across patient cohorts, and knowledge graphs representing relationships between diseases, symptoms, and outcomes, transforming diagnosis from linear rule application to probabilistic inference over complex evidence networks. These examples reveal problem-solving's essential components: precise state representation capturing relevant aspects while abstracting irrelevant details, well-defined operators transforming states, goal specification distinguishing success from failure, and search strategy navigating state space efficiently toward solutions. Principles that scale from toy puzzles to autonomous vehicle decision-making where state spaces encompass vehicle dynamics, traffic rules, pedestrian intentions, and environmental conditions. Search algorithms provide the computational machinery for navigating problem spaces, systematic strategies for exploring state spaces to locate solutions when direct computation proves infeasible. Uninformed search techniques operate without domain-specific guidance, breadth-first search expanding all nodes at current depth before proceeding deeper, guaranteeing shortest path solutions in unwaves as employed by early robotic vacuum cleaners mapping room layouts through systematic coverage. Depth-first search pursuing single paths to maximum depth before backtracking, efficient in memory usage but risking infinite loops in cyclic graphs, iterative deepening combining advantages of both through repeated depth-limited searches with incrementally increased limits, enabling chess programs to explore deeper move sequences within fixed-time constraints. Informed search leverages heuristic functions estimating distance to goal states, a * algorithm maintaining priority queue ordered by f, n equals g, n plus h, n, where g, n, represents actual from start to node n and h, n, represents estimated cost from n to goal. Manhattan distance heuristic for grid navigation summing horizontal and vertical displacements provides admissible estimate, never overestimating true cost, enabling optimal pathfinding for delivery robots navigating city blocks. Euclidean distance heuristic continuous spaces guides drone flight planning through 3D environments while avoiding obstacles. Real-world navigation systems illustrate heuristic design trade-offs, ways employing travel time heuristics incorporating historical traffic patterns, weather conditions, and road types to estimate journey duration. These heuristics prove inadmissible, sometimes overestimating true travel time, but produce practically useful routes by prioritizing major highways even when theoretically suboptimal minor roads exist. The trade-off between optimality guarantees and computational efficiency becomes critical when routing thousands of vehicles simultaneously across continental road networks. Serial search addresses competitive scenarios with opposing agents. Minimax algorithm assuming optimal play from opponents forms foundation for game-playing AI. IBM Deep Blue evaluated 200 million chess positions per second using alpha-beta pruning to eliminate branches provably irrelevant to final decision. Modern systems like AlphaZero abandon handcraft evaluation functions entirely, learning value networks through self-play that estimate win probability from board positions, enabling mastery of chess, shogi, and Go without human game databases. Constraint satisfaction problems represent another search class where solutions must satisfy multiple conditions simultaneously, schedule university courses across time slots while respecting room capacities, instructor availability, and student enrollment constraints, solving Sudoku puzzles through backtracking search with forward-checking eliminating inconsistent values from unassigned variables, configuring computer systems where component selections must satisfy compatibility constraints. CPU socket matching motherboard, power supply wattage exceeding component requirements. These examples demonstrate search algorithms as practical engineering tools, not abstract graph traversals but computational strategies enabling robots to navigate warehouses, vehicles to route through traffic, games to challenge human champions, systems to configure complex products under constraint. Knowledge representation addresses how intelligent systems encode information about the world, translating human understanding into formal structures that support inference, reasoning, and decision-making. Propositional logic provides simplest representation. Atomic propositions like, the robot is in room, combined through logical connectives, and, or, not, implies, to form complex statements. Resolution refutation proving unsatisfiability of clause sets through systematic application of resolution rule enables automated theorem proving but lacks expressiveness for real-world domains requiring quantification objects. First-order predicate logic extends expressiveness through quantifiers and relations. Universal quantification turned AX, student, X, has ID, X, stating all students have ID cards. Existential quantification Y, robot, Y, lander in room, Y, kitchen, asserting there exists but in the kitchen, predicates capturing relationships like adjacent, room A, room B, enabling spatial reasoning essential for robotic navigation. Semantic networks represent knowledge as graphs where nodes denote concepts and edges denote relationships. WordNet organizing English vocabulary into synonym sets, synsets, connected by hyper, dog, ISA, mammal, meronymy, wheel part OF, car, and other relations. These structures enable word sense disambiguation in natural language processing by selecting meanings consistent with surrounding context. Frames formalize stereotypical situations through slots and fillers. Restaurant frame containing slots for cuisine type, range, location, with fillers like Italian, expensive, downtown. Inheritance mechanisms allowing Italian restaurant to inherit slots from restaurant while adding specialized slots like has pasta menu. This representation powered early question-answering systems like SHRDLU operating in blocks world domains. Ontologies provide specifications of shared conceptualizations within domains. Gene ontology standardizing terminology for gene functions across species enabling computational biology research. SNOME CT, systematized nomenclature of medicine, clinical terms, structuring medical concepts with hierarchical relationships enabling electronic health record interoperability. Robotics ontology specifying relationships between actions, objects, and spatial relations enabling robots to interpret commands like put the red block on the blue block by mapping linguistic elements to ontological concepts. Real-world applications reveal representation trade-offs. IBM Watson's knowledge base integrated multiple representation schemes, unstructured text from medical literature processed through natural language understanding, structured knowledge graphs encoding relationships between diseases, symptoms, and treatments, probabilistic networks quantifying uncertainty in diagnostic inferences. This hybrid approach enabled Watson to answer Jeopardy! Clues requiring diverse knowledge types but also revealed limitations when symbolic reasoning lacked grounding in physical experience. Watson could retrieve facts about surgery but couldn't perform surgical procedures requiring embodied understanding of tissue properties and tool dynamics. Modern systems increasingly employ distributed representations, word embeddings like word-to-vec positioning semantically similar terms near one another in continuous vector spaces. King, man plus woman almost equal to queen, knowledge graph embeddings like transi representing entities and relations as vectors where head plus relation almost equal to tail, Paris plus capital of almost equal to France. These representations enable networks to perform analogical reasoning but sacrifice the explicit interpretability of symbolic representations. Engineers must select representation schemes aligned with application requirements. Symbolic representations for domains requiring explainability like medical diagnosis, distributed representations for perceptual tasks like recognition, hybrid approaches for complex domains, demanding both pattern recognition and logical inference. Logic and reasoning mechanisms enable intelligent systems to draw conclusions from available knowledge, transforming static representations into dynamic inference capabilities that support decision-making under varying conditions of and completeness. Deductive reasoning derives logically certain conclusions from premises. Modus ponens inferring Q from PQ and P enables expert systems to chain rules. IF fever and cough then possible flu. IF possible flu then recommend rest. Observing fever and cough triggers recommendation for rest through two applications of ponens. This forward chaining approach powered XCON, expert configurer, Digital Equipment Corporation's system that configured VAX computer orders with 95 to 98% accuracy, saving an estimated $40 million annually by reducing configuration errors and technician time. Inductive reasoning analyzes from specific observations to broader patterns, forming hypotheses consistent with training examples while balancing fit against complexity to avoid overfitting. AlphaFold's protein structure prediction exemplifies sophisticated induction, training on known protein structures to learn patterns relating amino acid sequences to 3D folds, then using to predict structures for previously unsolved proteins with atomic accuracy, accelerating drug discovery. Pipelines by providing structural models where experimental determination would require months of laboratory work. Abductive reasoning infers best explanations for observed phenomena, selecting hypotheses that would, if true, make observations most expected. Medical diagnosis systems employ abduction, observing symptoms fever, rash, and joint pain. The system infers Lyme disease as best explanation because this hypothesis would predict exactly these symptoms given tick exposure history. This differs from deduction. Symptoms necessarily follow disease, and induction, frequency patterns across populations. Abduction addresses the inverse problem of identifying causes from effects under uncertainty. Probabilistic reasoning handles uncertainty through Bayesian networks, directed acyclic graphs where nodes represent random variables and edges represent direct dependencies. The Asian network models diagnostic reasoning with nodes for tuberculosis, lung cancer, bronchitis, and their relationships to symptoms like dyspnea and test results like X-ray abnormalities. Belief propagation algorithms efficiently compute posterior probabilities given evidence, observing positive X-ray updates belief in tuberculosis and lung cancer while belief in bronchitis. This framework powers modern diagnostic assistants like Babylon Health's symptom checker that quantifies disease probabilities given symptom inputs while explicitly representing uncertainty rather than providing deterministic diagnoses. Fuzzy logic handles vagueness through continuous truth values between 0 and 1, enabling approximation with linguistic variables like warm or tall represented as membership functions over numerical domains. Washing machines employing fuzzy controllers adjust wash cycles based on inputs like heavily soiled, membership 0.8 in heavy soil set, and large load, membership 0.9 in large load set, triggering extended washing with high water level. Anti-lock braking systems modulate brake pressure based on will slip estimates represented as fuzzy sets, approaching lock, membership 0.7, enabling smooth deceleration without will lockup. These applications demonstrate reasoning under imprecision where binary true, false distinctions prove inadequate for world sensor data and human preferences. These diverse reasoning paradigms reflect fundamental recognition that intelligence operates under multiple forms of uncertainty: probabilistic, known distributions, possibilistic, unknown distributions, vagueness, linguistic imprecision, and ignorance, complete lack of information, requiring pluralistic rather than single unified theory. With engineers selecting appropriate mechanisms based on domain characteristics and decision stakes. Artificial intelligence applications permeate contemporary society across diverse domains, transforming industries through capabilities that augment human expertise, automate routine tasks, and enable previously impossible functionalities. Healthcare applications demonstrate AI's life-saving potential. IDXDR became first FDA-approved autonomous diagnostic system detecting diabetic retinopathy from retinal images with sensitivity of 87.2% and specificity of 90.7%, enabling care clinics without ophthalmologists to screen patients. PathAI assists pathologists analyzing tissue biopsies by highlighting regions suspicious for cancer, reducing diagnostic variability while maintaining pathologist oversight. Surgical robots like Da Vinci system enhance surgeon capabilities through wristed instruments providing degrees of freedom, 3D high-definition visualization, and motion scaling filtering physiological tremor to sub-millimeter precision, performing over 1 million procedures annually including prostatectomies, hysterectomies, and cardiac valve repairs. Transportation applications reshape mobility paradigms. Tesla's autopilot combines cameras providing 360-degree visibility, 12 ultrasonic sensors detecting nearby objects, and forward-facing radar penetrating fog and dust to enable adaptive cruise control, automatic lane changing, and traffic-aware cruise control. Waymo's fully autonomous taxis operate without safety drivers in Phoenix metropolitan area, having did over 20 million miles of autonomous driving through combination of LiDAR for precise 3D mapping, computer vision for object recognition, and sophisticated prediction models forecasting pedestrian and vehicle trajectories. These systems reduce traffic fatalities. 94% of crashes involve human error according to NHTSA, while increasing mobility access for elderly and disabled populations unable to drive conventional vehicles. Manufacturing applications drive Industry 4.0 transformation. Siemens Amberg Electronics plant employs AI-powered quality control where computer vision systems inspect circuit boards at production line speeds, detecting microscopic defects visible to human inspectors with 99.99885% quality rate. Collaborative robots, cobots, from Universal Robots work alongside human assemblers in automotive plants, handling repetitive tasks like screw driving while humans perform dexterous operations like wiring harness installation. Increase productivity 30% while reducing ergonomic injuries. Predictive maintenance systems analyze vibration patterns from factory equipment using deep learning to predict bearing failures weeks before catastrophic breakdown, reducing unplanned downtime by up to 50%. Natural language processing applications reshape human-computer interaction. Google, employing neural machine translation with attention mechanisms, provides near-human quality translations across 135 languages, facilitating cross-cultural communication and business expansion. Amazon Alexa and Google Assistant process billions of voice commands daily through automatic speech recognition, converting audio to text, natural language understanding, extracting intents and entities. Play jazz. Music, intent, play music, entity, jazz, and dialogue management, maintaining context across multi-turn interactions. These systems increasingly handle complex tasks like restaurant reservations through integration with booking APIs, demonstrating progression from simple command execution to service orchestration. Computer vision applications extend human perception capabilities. Facial recognition systems like Apple's Face ID employ dot projectors casting 30,000 infrared dots onto faces to create depth maps resistant to photograph spoofing, enabling secure device unlocking with false acceptance rate of 1 in 1 million. Agricultural robots like John Deere's See and Spray identify individual weeds among crops through real-time computer vision, applying herbicides only to weeds rather than broadcast spraying. Entire fields, reducing chemical usage by up to 90% while maintaining weed control efficacy. Autonomous drones inspect infrastructure like wind turbine blade, bridge undersides, detecting cracks and corrosion through high-resolution imagery analyzed by convolutional neural networks, accessing locations dangerous or impractical for human inspectors. These applications reveal AI's distinctive value not as human replacement but as capability amplifier, enhancing medical diagnostic accuracy while preserving physical judgment, extending mobility access while maintaining safety oversight, increasing manufacturing precision while supporting human workers, breaking language barriers while respecting cultural context, extending visual perception into microscopic, infrared, and temporal domains beyond human biological limits. Ethical implications permeate artificial intelligence development and deployment. Technical decisions about data selection, algorithm design, and system architecture carry profound societal consequences requiring proactive consideration rather than retrospective mitigation. Algorithmic bias manifests when training data reflects historical inequities or underrepresents demographic groups. Facial recognition systems trained predominantly on light-skinned male faces demonstrated error rates up to 34% higher for dark-skinned women compared to light-skinned men according to MIT Media Lab research, leading to wrongful arrests when deployed in law enforcement contexts. Mortgage approval algorithms trained on historical lending data replicated red lines by denying loans to qualified applicants in minority neighborhoods. These failures stem not from malicious intent but from uncritical acceptance of biased data as ground truth. Engineers must implement bias detection through disaggregated performance metrics across demographic subgroups, mitigation strategies like adversarial debiasing that remove protect attributes from representations, and ongoing monitoring detecting drift as deployment contexts evolve. The alignment problem, ensuring AI systems pursue objectives aligned with human values, emerges directly from representation challenges in reward function specification. Cleaning robot designers specifying reward for minimizable dirt inadvertently created incentive for robot to hide dirt under furniture or disable its own vision system to avoid perceiving mess. Outcomes technically optimal under specified reward but catastrophically misaligned with human intent. Autonomous vehicle trolley problems reveal limitations of simplistic ethical frameworks. programming vehicles to miss total casualties might systematically sacrifice passengers to save pedestrians, undermining public trust and adoption. Real-world solutions require transparency about decision criteria, human oversight for edge cases, and regulatory frameworks establishing liability allocation rather than expecting algorithms to resolve centuries-old philosophical dilemmas. Privacy preservation demands architectural choices from system inception. Clearview AI scraping 3 billion images from social media without consent to build facial recognition database accessible to law enforcement raised fundamental questions about consent in public spaces. Differential privacy adds calibrated noise to query responses guaranteeing indistinguishability between datasets differing by single individual. Apple employs this technique in iOS to collect usage statistics. Without identifying specific users, federated learning trains models on decentralized devices without centralizing sensitive information. Google Keyboard's board learns personalized word predictions from individual patterns while keeping raw data on device, transmitting only model updates to central server. Explainability requirements vary by application context. Medical diagnostic systems require clinical trust, necessitating interpretable models like decision trees or attention visualizations highlighting image regions influencing predictions. In quality control systems where failure modes are well understood may accept black box approaches maximizing accuracy. European Union's GDPR, right to explanation, mandates meaningful information about logic involved in automated decision-making. Affecting individuals, engineers must design systems with explanation capabilities matching their needs rather than treating transparency as uniform requirement. Dual-use awareness recognizes beneficial technologies can enable harm. Facial recognition aiding disaster victim identification in earthquake rubble or enabling mass surveillance suppressing political dissent, autonomous drones delivering medical supplies to remote villages or conducting target strikes without meaningful human control, language models democratizing information access or generating persuasive disinformation campaigns. Researchers bear responsibility considering plausible misuse scenarios and implementing mitigations like capability restrictions, access controls, and transparency mechanisms enabling detection use. These ethical dimensions aren't peripheral concerns addressed after technical development completes, they are foundational design parameters shaping data collection protocols, algorithm selection criteria, validation procedures, and deployment strategies from project inception, with engineers bearing professional responsibility to anticipate consequences, engage diverse stakeholders, and prioritize human dignity alongside technical performance metrics. Slide 5, AI.702, Machine Learning. Machine learning represents the computational engine powering artificial intelligence's transformation from rule-based systems to adaptive technologies that improve through experience, algorithms that automatically discover patterns in data without explicit programming for every possible scenario, enable systems to generalize from examples to novel situations. Unlike traditional software where developers specify precise instructions for every input-output mapping, machine learning systems learn mappings from data. Netflix's recommendation engine doesn't contain hand-coded rules like, if user watched Stranger Things then recommend dark, but discovers latents across millions of viewing histories to predict preferences. Tesla's autopilot doesn't encode exhaustive rules for every road configuration but learns to recognize lanes, vehicles, and pedestrians from billions of miles of driving data. This paradigm shift, from programming explicit behaviors to training systems on repetitive examples, enables capabilities impossible through manual coding alone, particularly in domains with high-dimensional inputs, images with millions of pixels, language with combinatorial syntax, or environments too complex to model analytically, financial markets, human behavior. The mathematical foundation rests on statistical theory, given training data drawn from unknown probability distribution P, X, Y, algorithms search hypothesis space H to find function f, x, y minimizing expected risk R, f, equals E, L, f, x, y, where L quantifies prediction error. In practice, we minimize empirical risk score EMP, f, equals 1, n, sigma L, f, x underscore I, y underscore I, over finite dataset while controlling model complexity to ensure generalization to unseen data, a delicate balance between fitting training examples and maintaining predictive accuracy on novel inputs that defines the core challenge of machine engineering. Supervised learning constitutes the most widely deployed machine learning paradigm, algorithms learning input-output mappings from labeled training examples where each instance x_i comes paired with target value y_i. Regression tasks predict continuous outputs. Zillow's Zestimate algorithm analyzes 7 million home features, square footage, bedroom count, neighborhood characteristics, recent sales, to predict property values within 1.9% median error for on-market homes. Weather forecasting systems ingest atmospheric pressure readings, satellite imagery, and historical patterns to predict temperature with hourly granularity. Industrial predictive maintenance models analyze vibration sensor data from factory equipment to forecast remaining useful life in hours before bearing failure. These systems employ algorithms like linear regression where prediction y equals plus x represents weighted combination of input features, polynomial regression captain linear relationships through terms like x squared or xx, support vector regression finding optimal hyperplane with epsilon insensitive tube accommodating prediction errors within tolerance threshold, or gradient boosting machines sequentially correcting residuals through decision trees to achieve state-of-the-art accuracy. Classification predict discrete categories, email spam filters analyze message content, sender reputation, and header metadata to assign binary labels, spam, not spam, with greater than 99.9% accuracy blocking billions of malicious messages daily. Medical imaging systems process mammograms to classify tissue as benign or malignant. Radiologist-level sensitivity reducing false negatives in breast cancer screening. Credit scoring models evaluate applicant income, debt ratios, payment history, and employment stability to approve or deny loan applications while complying with fair lending regulations. Classification algorithms include logistic regression probability p, y equals 1x, through sigmoid transformation of linear combination, k-nearest neighbors assigning labels based on majority vote among geometrically proximate training examples, support vector machines finding maximum margin hyperplane separating classes in high-dimensional feature space. Naive Bayes leveraging Bayes' theorem with independence assumption enabling real-time classification despite simplistic probabilistic modeling, and ensemble methods like random forests combining hundreds of decorrelated decision trees to reduce variance while maintaining interpretability. Real-world deployment demands understanding trade-offs. Logistic regression provides interpretable codes revealing feature importance, e.g., each additional year of credit history increases approval probability by 3.2%, essential for regulatory compliance but struggles with complex nonlinear relationships. Deep neural networks achieve superior accuracy on image classification but operate as black boxes requiring post-hoc explanation like SHAP values for high-stakes domains. K-nearest neighbors requires no training time but suffers quadratic inference complexity making it impractical for real-time applications with millions of examples. These trade-offs necessitate contextual algorithm selection. Fraud detection systems prioritize recall, minimizing false negatives, even at cost of increased false positives requiring manual review. Medical diagnosis prioritizes precision, minimizing false positives, to avoid unnecessary invasive procedures. Recommendation systems balance accuracy against diversity to prevent filter bubbles, demonstrating that optimal algorithm choice depends not merely on accuracy but on domain-specific cost structures and ethical constraints. Unsupervised learning addresses scenarios where labeled data proves unavailable, prohibitively expensive, or conceptually undefined. Algorithms discovering hidden structure in unlabeled datasets, x, without target variables y. Clustering algorithms partition data into homogeneous groups revealing natural segmentations. Retail companies like Target apply k-means clustering to purchase histories identifying customer segments, frequent baby product buyers, organic food enthusiasts, electronics early adopters, enabling personalized marketing campaigns increased sales by 15 to 20% through targeted promotions. Genomic researchers employ hierarchical clustering on gene expression profiles grouping patients by molecular subtypes of cancer leading to precision oncology treatments where therapies target specific genetic mutations rather than organ location alone. Cybersecurity systems use DB, density-based spatial clustering of applications with noise, analyzing network traffic patterns to detect anomalous clusters representing zero-day attacks without prior knowledge of attack signatures. Dimensionality reduction techniques compress high-dimensional data into lower-dimensional representations preserving essential structure. principal component analysis, CA, transforms correlated features into orthogonal principal components ordered by variance explained. Applied in facial recognition systems where 10,000 pixel images compress to 100-dimensional agent faces retaining 95% of visual information enabling real-time identification, T-distributed stochastic neighbor embedding, TSNE. Preserves local neighborhoods in nonlinear manifolds. Used by Spotify's music recommendation engine visualizing 1 point for million songs in 2D space where proximity reflects acoustic similarity enabling discovery of niche genres. Autoencoders employ neural networks with bottleneck layers learning compressed representations through reconstruction loss. Deployed in industrial quality control where high-resolution images of manufactured parts compress to latent codes enabling rapid anomaly detection when reconstruction error exceeds threshold. Association rule mining discovers co-occurrence patterns in transactional data. Walmart's market basket analysis revealed customers purchasing frequently buy beer on Friday evenings, a counterintuitive correlation leading to strategic product placement increasing sales of both categories. Amazon's customers who bought this also bought. Recommendations stem from a priori algorithm mining frequent item sets with minimum support thresholds generating rules like phone case, screen protector, wireless charger, with 78% confidence driving 35% of total revenue through cross-selling. Anomaly detection identifies rare deviations from normal patterns. Visor's fraud detection systems analyze 150 billion annual transactions using isolation forests that efficiently isolate anomalies through random feature partition, flagging suspicious purchases within milliseconds while maintaining 99.999% uptime. Manufacturing plants employ one-class SVMs monitoring sensor streams from production lines detecting subtle deviations in vibration spectra indicating bearing where weeks before. Catastrophic failure, reducing unplanned downtime by 40%. Unsupervised learning's power lies in exploratory discovery, revealing structure invisible to human analysts through computational pattern recognition, while its limitation stems from evaluation difficulty without ground truth labels requiring domain expert validation to distinguish meaningful patterns from statistical artifacts. Real-world applications often combine supervised and unsupervised techniques. Semi-supervised learning leverages small labeled dataset with large unlabeled corpus. Medical imaging startups training tumor classifiers on 1,000 expert annotated scans augmented with 100,000 unlabeled images through self-training where models high confidence predictions on unlabeled data on pseudo-labels. Transfer learning initializes models with unsupervised pre-training on massive unlabeled corpora then fine-tunes on task-specific labeled data. BERT language model pre-trained on 3.3 billion words through masked language modeling then fine-tuned on sentiment analysis with 10,000 labeled examples achieving state-of-the-art with minimal labeled data. These hybrid approaches address the fundamental constraint of supervised learning. High-quality labeled data remains scarce, expensive, and domain-specific while unlabeled data proliferates across digital systems, making unsupervised and semi-supervised techniques essential for scaling machine learning beyond narrow domains with annotations. Decision trees provide intuitive, interpretable models representing decisions as hierarchical sequences of feature-based tests, each internal node testing feature value against threshold, each branch representing outcome, each leaf node assigning prediction. The ID3 algorithm constructs trees through greedy recursive conditioning maximizing information gain at each split, measuring reduction in entropy H, S, equals, sigma p underscore I log p underscore I where p underscore I represents class proportion in subset S. Consider a loan approval scenario with features, income, debt underscore ratio, employment underscore length, and binary outcome, approve, deny. Root node might split on income greater than $50,000 separating high-income applicants. 70% approval rate, from low income, 30% approval, left child might further split high income group on debt underscore ratio less than 0 point for yielding 85% approval for low debt subgroup versus 45% for high. Right child might split low income group on employment underscore length greater than 2 years yielding 55% versus 15% approval. This hierarchical structure enables transparent decision making. Loan officers can explain denials through specific feature thresholds. Your application was denied because income below $50,000 combined employment under 2 years, satisfying regulatory requirements for algorithmic transparency under laws like EU's GDPR Article 22. CART, classification and regression trees, extends ID3 to handle continuous outputs through variance reduction rather than information gain. predicting house prices by recursively partition space. First split on square_footage greater than 2,000 separating large homes, mean price $750,000, from small, $450,000. Large homes split on neighborhood_school_rating, H yielding $950,000 versus $650,000. Small homes split garage_exists yielding $520,000 versus $410,000, creating piecewise constant approximation of continuous price surface. Real-world applications leverage decision trees interpretability. Healthcare systems deploy them for clinical decision support. Sepsis prediction models analyze signs, lab results, and comorbidities through 15-node trees, enabling nurses to understand risk factors triggering alerts. Manufacturing quality control uses them for root cause analysis, identifying that solder joint failures correlate with humidity greater than 65% combined with cooling rate less than 2 degrees Celsius per second, enabling process adjustments. However, single trees suffer from high variance. Small data perturbations produce dramatically different structures, motivating ensemble methods that combine multiple trees for robustness. Random forests address variance through bagging, bootstrap aggregating, training hundreds of trees on random sets of data with random feature subsets at each split, then averaging predictions, regression, or voting, classification. Capital One employs random forests with 500 trees analyzing 200 applicant features to approve credit cards with 99.2% accuracy while maintaining model stability against data drift. Individual might overfit noise, but ensemble averages converge toward true signal. Gradient boosting constructs trees sequentially where each new tree fits residuals of previous ensemble. XGBoost implementation used by Airbnb to predict booking probabilities, analyzing 50+ features, price, location, amenities, seasonality. Gradient boosted trees achieving 12% higher accuracy than logistic regression while identifying nonlinear interactions like luxury amenities increase booking probability only when price below neighborhood 75th percentile. These ensembles sacrifice some interpretability for accuracy but maintain partial transparency through feature importance metrics. Permutation importance measuring accuracy drop when feature values randomly shuffled reveals which inputs drive predictions most strongly. Decision trees geometric interpretation as recursive axis-aligned partitions provides intuition for limitations. They struggle with diagonal decision boundaries requiring many splits to approximate, e.g., exoplum, motivating kernel methods or neural networks. For complex manifolds, they exhibit instability near split thresholds where small input changes flip predictions, mitigated through soft decision trees using probabilistic splits or ensemble averaging. Despite limitations, decision trees remain foundational, provide line performance, interpretable prototypes for stakeholder alignment, and building blocks for sophisticated ensembles, demonstrating that algorithmic simplicity often enables practical deployment where black box models face regulatory or trust barriers. Model evaluation transforms subjective claims of good performance into objective, quantifiable evidence guiding algorithm selection, hyperparameter tuning, and deployment decisions, requiring metrics aligned with domain-specific costs of different error types rather than generic accuracy alone. Classification metrics extend beyond accuracy, correct predictions, total, which proves misleading under class imbalance. Fraud detectors face 0.1% fraud prevalence. Random classifier predicting not fraud achieves 99.9% accuracy while missing all actual fraud. Precision, true positives, predicted positives, measures reliability of positive predictions. Critical for medical diagnosis where false positives cause unnecessary biopsies. Call, true positives, actual positives, measures. Coverage of actual positives. Critical for disease screening where false negatives miss treatable conditions. F1 score harmonizes precision and recall through harmonic mean essential when both error types carry significant costs. Receiver operating characteristic. C. Curves plot true positive rate against false positive rate across classification thresholds. Area under curve, AUC, quantifies separability independent of threshold selection. Zell's fraud detection achieves AUC 0.98, distinguishing legitimate from fraudulent transfers through transaction velocity, device fingerprinting, behavioral biometrics. Precision recall curves prove more informative than ROC under extreme imbalance. plotting precision against recall reveals performance in high recall regimes essential for safety-critical applications. Autonomous vehicle pedestrian detection requires greater than 99% recall even at precision cost, missing a pedestrian catastrophic consequences while false alarms merely trigger unnecessary braking. Regression metrics quantify prediction error magnitude. Mean absolute error, MAE, measures average absolute deviation, interpretable in original units, e.g., Zillow's estimate MAE $14,000 means typical prediction deviates $4,000 from sale price. Root mean squared error, RMSE, penalizes large errors quadratically, sensitive to outliers making it appropriate when catastrophic errors carry disproportionate costs, e.g., structural load prediction where 10% error risks collapse, R-squared quantifies. Variance explained relative predictor, values near 1 indicate model captures most signal though can be misleading with overfitting. Cross-validation addresses over-optimistic performance estimates from single train test splits. K-fold cross-validation partitions data into K subsets, trains on K, 1 folds, tests on held-out fold, repeats K timing results. Time series cross-validation maintains temporal order preventing data leakage where future information contaminates training, essential for financial forecasting where models trained on shuffled timestamps achieve deceptively high accuracy by exploiting look-ahead bias. Learning curves diagnose bias variance trade-offs. Plotting and validation error against dataset size reveals whether additional data would improve performance. Validation error decreasing with more data indicates high variance, overfitting, or whether model complexity must increase. Validation error plateauing while training error near zero indicates high bias, underfitting. Confusion matrices provide granular error analysis. Healthcare AI startup Path AI analyzing pathology slides discovered their cancer detector achieved 92% accuracy but confusion matrix revealed 18% false negative rate for aggressive subtypes prompting model refinement before clinical deployment. Domain-specific evaluation extends beyond statistical metrics. Fairness metrics by performance disparities across demographic groups. Facial recognition systems must achieve similar false match rates across skin tones to prevent discriminatory law enforcement outcomes. Robustness metrics measure performance degradation under distribution shift. Autonomous vehicles tested under fog, rain, and snow to quantify safety. Beyond clear weather benchmarks, calibration metrics assess alignment between predicted probabilities and observed frequencies. Medical diagnosis systems requiring 90% predicted probability to correspond to 90% actual occurrence enabling clinicians to trust risk estimates. These evaluation practices transform machine learning from artifact into engineering discipline, replacing subjective impressions with reproducible evidence, enabling rational algorithm selection, and establishing safety cases for high-stakes deployment where human lives or financial systems depend on reliable performance. Feature engineering transforms raw data into predictive representations, domain-informed transformations that expose signal obscured in original measurements while suppressing noise irrelevant to target variable. Time series features extract temporal patterns. Financial trading algorithms compute rolling averages, 7-day, 30-day, volatility measures, standard deviation of returns, momentum indicators, price change look back windows, and technical indicators like relative strength index quantifying overbought, oversold conditions. Renaissance Technologies Medallion Fund leveraged thousands of engineered time series features achieving 66% annual returns before fees through pattern recognition. Invisible to raw price charts. Text convert unstructured language into numerical vectors. Bag of words representing documents as term frequency vectors enables spam detection by identifying overrepresented terms like free, winner, click here, TF-IDF, term frequency inverse document frequency, downweights common terms like the while upweighting discriminative terms like phishing, proving document classification. Ngram features capturing word sequences, New York as bigram, preserve phrase meaning lost in. Bag of words, sentiment lexicons assigning polarity scores to words enable rapid sentiment analysis without training data, used by Brandwatch monitoring 95 million online sources tracking brand perception. Engineered sentiment features. Image features extract visual patterns beyond raw pixels. Histogram of oriented gradients, HOG, captures edge orientations in localized cells enabling pedestrian detection in autonomous vehicles. Scale invariant feature transform, SIFT, identifies distinctive keypoints invariant to scale, enabling image matching across viewpoints. Used by Google Photos for face recognition across decades of family albums, color histograms quantifying distribution of hues enable content-based image retrieval. Pinterest's visual search matches user-uploaded images to product catalog through engineered color and texture features. Specific feature engineering leverages expert knowledge. Healthcare predictive models incorporate clinical risk scores like Apache 2, acute physiology and chronic health evaluation, combining 12 physiological measurements into validated severity index, more predictive than raw vitals alone. Manufacturing quality models compute statistical pro metrics like CPK quantifying process capability relative to specification limits, revealing drift before defects occur. Retail demand forecasting models engineer holiday proximity features, days until Christmas, seasonality indicators, queue for dummy variables, and promotional flags. Campaign effects. Walmart's forecasting system reduces stockouts by 16% through sophisticated feature engineering beyond simple historical averages. Automated feature engineering tools accelerate discovery. Feature tools employs deep feature synthesis recursively applying primitive operations, sum, mean, max, across databases, analyzing customer transaction histories to generate features like mean purchase amount over last 30 days, or count of returns in past year, without manual specification. Fresh extracts 200 plus time series features from sensor data identifying predictive patterns in industrial equipment vibration, reducing manual feature engineering effort by 80% while improving predictive maintenance accuracy. Feature selection reduces dimensionality eliminating redundant or irrelevant features. L1 regularization. Lasso drives uninformative feature coefficients to zero during training. Genomic studies analyzing 20,000 genes identify 50 biomarkers for disease progression through Lasso feature selection. Recursive feature elimination iteratively removes least important features based on model weights, improving training speed 10x while maintaining accuracy for real-time inference on edge devices. Feature scaling ensures numerical stability. Standardization. Z-score normalization transforms features to zero mean and unit variance essential for distance-based algorithms like k-nearest neighbors where unscaled features with larger ranges dominate similarity calculations. Minute-max scaling compresses features to 0, 1 range required by neural network activation functions preventing variation. Robust scaling using median and interquartile range resists outlier influence critical for financial data with extreme values. These engineering practices transform machine learning from passive pattern recognition into active knowledge representation, encoding domain understanding into data representations that make tractable, interpretable, and robust, demonstrating that algorithm selection matters less than representation quality when solving real-world problems where signal hides within complex, noisy measurements. Overfitting and underfitting represent fundamental trade-offs governing machine learning model performance, balancing capacity to fit training data against to generalize to unseen examples. Overfitting and underfitting represent fundamental trade-offs governing machine learning model performance, balancing capacity to fit training data against ability to generalize to unseen examples. Overfitting occurs when models minimize noise and idiosyncrasies in training data rather than learning generalizables. High-capacity models like deep neural networks with millions of parameters fitting training examples perfectly but failing catastrophically on novel inputs. Visualize polynomial regression fitting housing price data. Degree, 1 polynomial, straight line, underfits capturing only cause trend. Degree, 5 polynomial fits training, smoothly generalizing well. Degree, 15 polynomial snakes through every training point achieving zero training error but oscillating wildly between points, predicting negative prices for plausible square footages. Real-world consequences manifest dramatically. Microsoft's Tay chatbot trained on Twitter interactions learned to generate racist, misogynistic content by overfitting to toxic patterns in training data without constraints on acceptable outputs, shut down after 16 hours. Medical imaging startups deploying overfitted models achieved 99% training accuracy but 65% test accuracy because models memoized scanner artifacts specific to training hospital rather than learning pathology patterns, potentially causing misdiagnosis if deployed clinically. Regularization techniques constrain model complexity preventing overfitting. L2 regularization, RIG, adds penalty lambda sigma squared to loss function shrinking coefficients toward zero without eliminating features. effective for multicollinears like square footage and room count in housing prediction. L1 regularization, lasso, adds penalty lambda sigma driving uninformative coefficients exactly to 0, enabling automatic feature selection, valuable when thousands of genomic markers predict disease risk. But only dozens prove causal. Dropout randomly deactivates network neurons during training, preventing coadaptation. AlexNet's 50% dropout rate between fully connected layers reduced overfitting, enabling ImageNet breakthrough. Early stopping halts training when validation error increases despite decreasing training error. Essential for deep networks where performance peaks then degrades as optimization continues. Unlearning occurs when models lack capacity to capture essential patterns. High bias preventing accurate representation of target function. Linear regression predicting Boston housing prices using only crime rate as feature achieves R squared equals 0.17, fundamentally incapable of capturing nonlinear relationships with room count, proximity employment centers, or school quality. Symptoms include high training and validation error converging to similar poor performance, unlike overfitting where training error nears 0 while validation error remains high. Remedies increase model capacity, adding polynomial features, x squared, x cubed, as linear models to fit nonlinear relationships. Increasing tree depth in decision trees captures complex interactions. Adding hidden layers or neurons in neural networks expands representational capacity. Incorporating domain-specific features like interaction terms, bedrooms times bathrooms, exposes signal invisible to main effects alone. Bias variance decomposition formalizes this trade-off. Expected prediction error equals bias squared plus variance plus irreducible error, where bias measures systematic deviation from true function. Underfitting, variance measures sensitivity to training set fluctuations. Overfitting, irreducible error stems from inherent noise in data generation process. Optimal models balance bias and variance, minimizing total error. Visualized through U-shaped validation error curve where left side represents high bias, underfitting, right side high variance, overfitting, bottom optimal complexity. Learning curves diagnose these conditions. Underfitting shows training and validation error both high and converging with more data, indicating need for more complex model or better features. Overfitting shows training error near 0 while validation error significantly higher with gap widening as model complexity increases, indicating need for regularization or more training data. Real-world deployment requires continuous monitoring for concept drift, gradual distribution shifts causing previously well-calibrated models to overfit new patterns. Retail demand forecasting models trained on pre-pandemic data overfitted to historical seasonality, failing during lockdowns when consumer behavior fundamentally changed. Autonomous vehicle perception systems overfitted to California conditions, failing in snowy Michigan winters until retrained on diverse weather data. These phenomena demonstrate that overfitting, underfitting aren't one-time training concerns but ongoing operational challenges requiring monitoring systems detecting performance degradation, retraining pipelines, updating models with fresh data, and fallback strategies maintain safety when models operate outside validated regimes. Transforming machine learning from static artifact into living system requiring continuous care. Machine learning pipelines orchestrate end-to-end workflows, transforming raw data into predictions through standardized, reproducible sequences of processing stages, enabling collaboration, version control, and production deployment beyond ad hoc Jupyter notebooks. Data ingestion pulls raw information from diverse sources, batch ingestion from data lakes, Amazon S3 storing petabytes of historical sensor logs, streaming ingestion from message queues, Apache Kafka processing 1 million IoT device messages per second, API ingestion from external services, weather APIs enriching agricultural yield predictions with real-time precipitation forecasts. Data validation ensures quality before processing. Great Expectations framework asserts expectations like temperature readings between -50 degrees Celsius and 60 degrees Celsius, or more than 5% missing values in critical sensors. Failing validation triggers alerts, preventing garbage in garbage out scenarios. TensorFlow data validation computes statistics across training and serving data, detecting schema skew, new sensor model producing different value ranges, or feature skew, training data normalized differently than inputs. Pre-processing transforms raw values into model-ready formats, missing value imputation replacing nulls with median, numerical, or mode, categorical, or predictive imputation using other features. outlier handling windowizing extreme values at 1 st 99 th percentiles preventing distortion of scaling operations, encoding converting categorical variables like material_type into numerical representations, label encoding for ordinal categories, small, medium, large, one-hot encoding for nominal categories, steel, aluminum, composite, preventing false ordinal relationships. Feature engineering predictive representations as previously detailed, automated tools like feature tools generating thousands of candidate features from relational schemas, domain experts incorporating physical constraints like Reynolds number in fluid dynamics predictions. Feature selection reduces dimensionality through statistical tests, chi-square for categorical targets, model-based importance, random forest feature importances, or regularization paths, lasso coefficient trajectories. Model training executes learning algorithms with hyperparameter optimization, grid search exhaustively evaluating predefined hyperparameter combinations, random search sampling hyperparameter space more efficiently, optimization building probabilistic surrogate model of performance surface guiding intelligent exploration. Google's Vizier service reduced hyperparameter tuning time 5x for recommendation systems through Bayesian methods. Model evaluation computes metrics on held-out test set with statistical significance testing, paired t-tests comparing new models baseline ensuring improvements aren't due to random variation, bootstrap confidence intervals quantifying metric uncertainty especially critical for small datasets. Model validation confirms readiness for deployment, fairness audits measuring performance disparities across demographic groups using AI Fairness 360 Toolkit, robustness testing adversarial perturbations or distribution shifts, interpretability analysis generating SHAP values explaining individual predictions for high-stakes domains. Model packaging serializes trained artifacts with dependencies, ONNX format enabling cross-framework deployment, PyTorch training TensorFlow serving, Docker containers in environment ensuring identical behavior across development and production, model cards documenting performance characteristics, limitations, and intended use cases. Deployment strategies manage transition to production, blue-green deployment running old and new models simultaneously routing subset of traffic to new version, canary deployment increasing traffic to new model while monitoring error rates, shadow deployment running new model parallel to production without affecting outputs enabling validation under real traffic patterns. Monitoring tracks operational health, data drift detection comparing production input distributions against training data using Kolmogorov-Smirnov tests, drift monitoring output distribution shifts indicating concept drift, performance degradation alerts triggering retraining when accuracy drops below threshold, business metric tracking connecting model outputs to organizational outcomes, e.g., recommendation system click-through rate correlating with revenue. Retraining pipelines automate model scheduled retraining weekly with fresh data, event-triggered retraining when drift detectors fire, human-in-the-loop validation where domain experts review model updates before deployment for safety-critical systems. Real-world pipeline examples illustrate complexity. Uber's Michelangelo platform processes 100+ billion predict requests daily through standardized pipelines, feature stores ensuring training serving consistency, automated retraining on fresh trip data, A/B testing frameworks comparing model variants, monitoring dashboards tracking business impact. Tesla's autopilot pipeline ingests 10 billion miles of fleet data through validation filters removing low-quality, automated labeling. Through sensor fusion and human review, distributed training across GPU clusters, shadow mode deployment validating new versions against human drivers before rollout. These pipelines transform machine learning from research prototype into industrialized capability, enabling reliable, scalable, and maintainable AI systems operating continuously in production environments where failures impact millions of users and billions in revenue. Pipeline engineering thus constitutes as critical a skill as algorithm selection, determining whether machine learning capabilities deliver sustained business value or remain isolated experiments unable to transition beyond proof of concept stage. Supervised learning algorithms demonstrate practical application through domain-specific implementations where theoretical concepts translate to engineered solutions addressing real constraints. Customer churn prediction in telecommunications exemplifies end-to-end supervised learning. Dataset contains 10,000 customer with features, monthly_charge, contract_length, support_calls, data_usage, and binary target, churned. Data exploration reveals 22% churn rate with contract_length inversely correlated. Month-to-month contracts show 41% churn versus 11% for 2-year contracts. Pre-processing handles missing support_calls through median imputation, encodes contract types via one-hot encoding. Feature engineering creates interaction term contract_length times support_calls, capturing hypothesis that frequent support seekers on short contracts face highest churn risk. Model selection compares logistic regression, interpretable coefficients for business stakeholders, random forest, handling nonlinearities, and gradient boosting, state-of-the-art accuracy. Logistic regression reveals coefficient_contract_month-to-month equals plus 1.32, meaning month-to-month customers have exp. 0.32 equals 3.7x higher churn odds, controlling for other features, actionable insight for retention teams offering contract extensions. Random forest achieves 84% accuracy versus logistic regression's 81% but provides feature importance, showing support_calls rank third behind contract_monthly_charge, refining retention strategy focus. Gradient boosting with XGBoost reaches 86% accuracy but requires SHAP analysis to explain predictions to customer service representatives who need to understand why specific customers receive retention offers. Business integration deploys model scoring daily with top 5% churn risk receiving personalized retention offers, reducing churn by 18% and saving $4.2 million annually in customer acquisition costs. Medical diagnosis illustrates high-stakes supervised learning where error costs differ dramatically. Diabetic retinopathy detection from retinal fundus image using convolutional neural networks. Dataset contains 88,702 de-identified images graded by ophthalmologists on 5-point severity scale. Pre-processing standardizes illumination through histogram equalization, crops optic disc region containing diagnostic features, augments data thresholds, flips addressing limited rare disease examples. Transfer learning initializes ResNet, 50 pre-trained on ImageNet, then fine-tunes final layers on medical images, leveraging general feature extractors while adapting to domain specifics. Model outputs probability distribution across severity grades with decision thresholds rated to clinical requirements, high sensitivity, greater than 97%, for referable disease, grades 3 to 4, minimizing false negatives where misdiagnosis causes blindness, moderate specificity, 85%, acceptable for false positives triggering additional screening rather than treatment. FDA approval rigorous validation, 10-fold cross-validation reporting sensitivity, specificity with 95% confidence intervals, external validation on independent dataset from different camera models proving generalization, subgroup analysis ensuring consistent performance across ethnicities, ages, and image qualities. Deployment into with clinical workflow, images uploaded through DICOM interface trigger asynchronous analysis returning results within 60 seconds. Uncertainty quantification flags low confidence predictions for ophthalmologist review, audit trail logs all predictions enabling quality assurance. System achieved 90% sensitivity and 92% specificity, matching board certified ophthalmologists while screening 10x faster, enabling primary care clinics without specialists to provide early detection. Industrial predictive maintenance demonstrates time series supervised learning, wind turbine failure prediction using SCADA sensor data, vibration, temperature, power output, sampled every 10 over 3 years. Problem framed as binary classification. With 7-day look-ahead window, predicting failure within next week, enabling scheduled maintenance, avoiding catastrophic breakdown. Feature engineering computes statistical aggregates over sliding windows, rolling mean, STD of vibration RMS capturing trends, spectral analysis extracting dominant frequencies indicating bearing wear, cross-correlations between temperature and power output revealing efficiency losses. Temporal validation prevents look-ahead bias, training on data before 2021, validating on 2021, testing on 2022, ensuring model generalizes to conditions. Gradient boosting achieves 93% recall at 85% precision, critical for recall since missed failures cause $250,000 repair costs and 14-day downtime. Deployment architecture streams real-time sensor data through Apache Kafka to feature computation engine generating 200 feet turbine every hour. Model scores features triggering maintenance tickets when failure probability exceeds 70%. feedback loop incorporates maintenance outcomes, updating model monthly. System reduced unplanned downtime 38% and extended component lifetime 22% through timely interventions, demonstrating supervised learning's impact beyond accuracy metrics. These examples reveal supervised learning's engineering reality. Success depends not on algorithm novelty but on thoughtful data preparation, domain-informed feature engineering, metric selection aligned with business costs, rigorous validation preventing over-optimism, and seamless integration in operational workflows where predictions drive actions delivering measurable value. Unsupervised learning algorithms solve problems where supervision proves impractical through creative application of structured discovery techniques. Customer segmentation in e-commerce illustrates clustering's business value. Amazon analyzes 300 million active purchase histories containing 10+ years of transaction data, billions of records impossible to label manually for supervised learning. K-means clustering with K equals 12 identifies natural segments, budget-conscious parents, frequent diaper, paper product purchases, price-sensitive, tech enthusiasts, early adopters of electronics, high return rates, luxury shoppers, high average order value, brand loyal, health-conscious, organic food, supplements, fitness equipment. Validation employs silhouette scores measuring cluster cohesion, separation plus business expert review ensuring segments align with marketing capabilities. Actionable outputs, personalized experiences, segment-specific homepage layouts featuring relevant categories, email campaigns with product recommendations matching segment preferences, inventory allocation prioritizing high-value segments during supply constraints. Revenue impact. Segment-targeted campaigns achieved 27% higher conversion versus generic gains, contributing $1.8 billion incremental revenue annually. Dimensionality reduction enables visualization and compression. Single-cell RNA sequencing generates 20,000 gene expression measurements per cell, impossible to visualize directly. PCA reduces dimensions to top 50 principal components in 85% variance. TSNE further compresses to 2D revealing distinct cell types as spatial clusters, immune cells grouping separately from epithelial cells enabling biologists to identify novel cell subtypes driving disease progression. Compression ratio 400:1 enables interactive exploration of million-cell dataset standard laptops, accelerating discovery cycles from months to days. Anomaly detection protects critical infrastructure. Power grid operators monitor 10,000+ sensors across transmission network, current, voltage, frequency measurements sampled every second generating terabytes daily. Isolation trained on normal operation data flag anomalies within milliseconds. Sudden voltage dip at substation combined with frequency deviation triggers automatic circuit breaker isolation preventing cascading blackout. Gradual temperature rise in transformer detected weeks before failure enabling scheduled replacement avoiding $2 million emergency repair and 8-hour out affecting 50,000 customers. System processes 1 million measurements, second with 99.99% uptime, demonstrating unsupervised learning's reliability for safety-critical applications. Association rule mining optimizes retail operations. Walmart analyzes 2.5 million point-of-sale trends daily identifying product affinities through a priori algorithm. Rules like diapers, baby wipes, baby formula, with 68% confidence and 0.5% support drive planogram decisions, placing formula adjacent to diapers increases basket size 12%, seasonal rules, grill, chart, hot dog buns, with 82% confidence guide summer merchandising layouts. Cross-category rules revealed unexpected affinity, beer and diapers purchased together Friday evenings, prompting strategic placement increasing sales of both categories 15%. These applications demonstrate unsupervised learning's distinctive, discovering structure without predefined labels, enabling exploration in data-rich but annotation-poor domains, revealing insights invisible to human analysts through computational pattern recognition, transforming unlabeled data from unusable resource into strategic asset driving business decisions, scientific discovery, and operational resilience. Machine learning's mathematical foundations provide theoretical guarantees guiding practical engineering decisions, statistical learning theory establishing conditions for generalization, bias variance decomposition quantifying error sources, PAC, probably approximately correct, learning defining learnability criteria. Empirical risk mitigation, ERM, principle states that minimizing training error R_EMP, F equals 1 N sigma L F X underscore I Y underscore I approximates minimizing true risk R F equals E L F X Y when sample size n sufficiently large relative to space complexity. Vapnik-Chervonenkis, VC, dimension quantifies model capacity, maximum number of points hypothesis class can shatter, classify arbitrarily. Linear classifiers in 2D have VC dimension 3, can separate any 3 points but not all configurations of 4 points. Generalization bound states that with probability 1, delta, true risk R, F, less than or equal to R underscore EMP, F, plus O, square root, VC, H, log n, n, revealing fundamental trade-off, complex models, high VC dimension, achieve low training error but suffer large generalization, simple models, low VC dimension, exhibit higher training error but smaller gap. This formalizes intuition behind regularization, constraining hypothesis space complexity to control generalization error even at cost of increased training error. No free lunch theorem proves no single algorithm universe performs others across all possible problems. Performance depends on alignment between algorithm inductive biases and problem structure. Decision trees excel when decision boundaries align with axis parallel splits. K-nearest neighbors succeed when similar inputs yield similar outputs. Smoothness assumption, support vector machines dominate when classifiable by wide margin in transformed feature space. Engineers must match algorithm biases to domain characteristics. Image recognition favors convolutional architectures encoding translation equivariance. Time series forecasting benefits from recurrent structures capturing temporal dependencies. Graph data demands graph neural networks respecting null structure. These theoretical insights prevent blind algorithm selection, guiding informed choices based on problem geometry rather than hype cycles or benchmark leaderboard chasing. Real-world engineering applies theory pragmatically. VC dimension guides regularization strength selection. Complex models like deep network require stronger regularization. Dropout rates, weight decay, proportional to parameter count. Bias variance decomposition informs data collection strategy. High variance problems benefit from more training data. High bias problems require feature engineering or model architecture changes. No free lunch theorem justifies ensemble methods combined. Verse. Algorithms whose errors decorrelate, random forests averaging decorrelated trees, gradient boosting sequentially correcting residuals, stacking blending heterogeneous base learners. Theory thus serves as compass rather than map, providing principles for navigating uncertainty rather than prescribing exact routes, and engineers to diagnose failures, select appropriate remedies, and design robust systems grounded in mathematical understanding rather than empirical trial and error alone. This theoretical grounding distinguishes machine learning engineers from API consumers, transforming practitioners who can troubleshoot failures, adapt algorithms to novel domains, and innovate beyond existing toolkits into professionals capable of extending the field's boundaries through principled design informed by deep understanding of learning mechanics. Slide 6, AI.703, Deep Learning. Deep learning represents a paradigm shift in artificial intelligence, moving beyond handcrafted feature engineering to hierarchical representation learning where neural networks automatically discover increasingly abstract patterns from raw data through multiple processing layers. Traditional machine learning requiring domain experts to design features like SIF descriptors for images or TF-IDF weights for text, deep learning systems ingest pixels or characters directly and learn optimal representations through exposure to massive datasets. This capability emerged not from theoretical breakthroughs alone but from convergence of three enablers: algorithmic innovations like rectified linear units, ReLU, and dropout regularization stabilizing training of deep architectures, computational advances delivering GPU parallelism accelerating matrix operations by 50-100x, and data abundance with ImageNet providing 1.2 million labeled images enabling statistically significant pattern discovery. The 2012 ImageNet Large-Scale Visual Recognition Challenge marked the inflection point. AlexNet's convolutional architecture achieved 15.3% top 5 error versus 26.2% for second place, demonstrating deep learning's transformative potential and triggering industry-wide adoption. Today, deep learning powers capabilities once considered science fiction. Real-time translation earbuds converting Spanish speech to English text with 95% accuracy, autonomous vehicles navigating complex urban environments by fusing camera, lidar, and radar inputs, protein folding prediction accelerating drug discovery by molecular structures previously requiring years of laboratory work. These applications share a common architectural principle: depth enables compositionality, early layers detect simple patterns, edges, phonemes, intermediate layers combine these into parts, object components, word phrases, and deep layers assemble parts into holistic faces, semantic meaning, mimicking hierarchical processing observed in biological visual cortex where V1 neurons respond to edges, V4 to shapes, and IT cortex to object identities. Neural network fundamentals begin with the perceptron, the simplest computational neuron inspired by biological counterparts. A perceptron receives inputs X weighted by connection strengths W, computes weighted sum Z equals sigma Wx plus B, where B represents bias term, then applies activation function sigma Z, producing output. Frank Rosenblatt's 1958 implementation used potentiometers adjusting weights through motorized mechanisms. Training involved manually rotating knobs until output matched desired target. Modern implementations replace physical knobs with gradient descent, mathematically adjusting weights to minimize prediction error. The critical limitation exposed by Minsky and Papard's 1969 single-layer perceptrons cannot solve non-linearly separable problems like XOR where inputs 0, 0, 0, 0, 1, 1, 1, 0, 1, 1, 1, 0 require curved decision boundaries. This limitation necessitates hidden layers, intermediate processing units enabling networks with complex decision surfaces. A two-layer network solves XOR by creating internal representations. First-layer neurons detect X and not X, and not X and X. Second layer combines these through OR operation producing correct output. This architectural insight, depth enables complexity, all modern deep learning. Real-world illustration: credit scoring systems require nonlinear decision boundaries where high income alone doesn't guarantee approval if debt ratio exceeds 50%. Deep networks learn these complex interactions automatically whereas linear models require manual feature engineering like income, debt_ratio action terms. The universal approximation theorem guarantees that networks with single hidden layer containing sufficient neurons can approximate any continuous function, providing theoretical foundation for deep learning's representational capacity while practical implementations require depth for efficient learning of hierarchical patterns. Activation functions transform weighted sums into nonlinear outputs, enabling networks to model complex relationships beyond linear combinations. Sigmoid function sigma Z equals 1, 1 plus E, maps inputs to 0, 1, range mimicking biological neuron firing rates, used in early networks for binary classification where output represents probability. However, sigmoid suffers from vanishing gradients. For Z, 4, derivative sigma Z, almost equal to 0 causing backpropagated gradients to diminish exponentially through layers, preventing weight updates in early layers during training. Rectified linear unit, real f, z, equals max, 0, z, solved this critical limitation, derivative equals 1 for z greater than 0 enabling robust gradient flow through deep architectures. ReLU's simplicity proved transformative. AlexNet's training time reduced from weeks to days compared to sigmoid networks. MOSNet architectures with 152 layers became feasible only with ReLU variants. Real-world impact: Tesla's autopilot processes 2,300 frames per second from 8 cameras. ReLU's computational efficiency enables real-time inference on vehicle-mounted hardware where sigmoid networks would exceed latency budgets. Variants address ReLU limitations. Leaky ReLU f, z, equals max, 0.01 z, z, prevents dying neurons where units output 0 for all inputs halting learning. Parametric ReLU learns leak coefficient during training adapting to data characteristics. Swish f, z, equal times sigma, z, where beta trainable, demonstrated superior performance on ImageNet by balancing nonlinearity and gradient flow. Activation selection directly impacts application performance. Medical imaging systems detecting microcalcifications in mammograms require sensitive gradient flow through deep layers. Swish activate proved detection sensitivity by 2.3% versus ReLU by preserving subtle gradient signals. industrial quality control systems inspecting circuit boards prioritize computational efficiency. ReLU variance reduced inference latency 37%, enabling real-time defect detection at production line speeds. These tools demonstrate activation functions as engineering choices with measurable impact on accuracy, speed, and robustness, not merely theoretical components. Backpropagation provides the mathematical engine for training deep networks, efficiently computing gradients of loss function with respect to millions of weights through dynamic programming. Consider a three-layer network classifying handwritten digits. Input layer, 784 pixels, hidden layer, 128 neurons, output layer, 10 digits. Forward pass computes activations layer by layer. A to the power of 1 equals sigma, w to the power of 1x plus b to the power of 1, a equals sigma, w squared a to the power of 1 plus b squared. Loss function L compares output to true label, e.g., cross-entropy for classification. Backward pass computes gradients starting from output, squared equals del L, del Z squared measures output layer error sensitivity, to the power of 1 equals, squared, sigma, Z to the power of 1, propagates error to hidden layer through chain rule, weight gradients del L, del W equals a to the power of 1 accumulate error signals across layers. Computational efficiency emerges through reuse. Gradients for layer L depend only on gradients from layer L plus 1 and activations from L1, avoiding redundant calculations that would make training intractable for deep networks. Real-world training illustrates scale. ResNet 50 contains 25.6 million weights. Processing single image net image requires 3.8 billion floating point operations. Training on 1.2 million images for 90 plans for 110 petaflop days of computation, equivalent to 1,000 NVIDIA V100 GPUs running continuously for 14 days. Optimization algorithms transform gradients into weight updates addressing challenges beyond vanilla gradient descent. Stochastic gradient descent, SGD, updates weights after training example rather than full batch, introducing noise that helps escape local minima but causing oscillations. Momentum accumulates velocity vector v equals v plus nabla L, where gamma damping factor, typically 0.9, smooths oscillations, enabling faster convergence through ravines in loss landscape. Optimizer combines momentum with adaptive learning rates per parameter, maintaining moving averages of gradient, first moment, and squared gradient, second moment, to scale updates inversely proportional to historical gradient magnitude. Adam's adaptive behavior proves critical for sparse data. Natural language processing models encounter rare where gradients appear infrequently. Adam increases learning rates for these parameters, accelerating convergence versus fixed rate SGD. Real-world comparison. Training BERT language model on Wikipedia corpus. SGD required 1 million steps to reach validation perplexity 5.2. Adam achieved same performance in 400,000 steps, reducing compute costs by $187,000. Learning rate scheduling further optimizes training. Warm-up phases gradually increase learning rate, preventing early divergence. Cosine annealing smoothly decreases rate toward end, enabling fine-tuning of solution. Cyclical schedules periodically reset rate, escaping saddle points. Tesla's vision pipeline employs learning rate warm-up during initial training on synthetic data, then cosine decay during fine-tuning on real-world driving footage, reducing convergence time 22% while improving obstacle detection recall by 3.8%. Convolutional neural networks, CNNs, revolutionized computer by encoding spatial invariance, recognizing patterns regardless of position within input through weight sharing and local connectivity. Biological inspiration comes from Hubel and Wiesel's 1959 discovery of cat visual cortex neurons responding to oriented edges within localized receptive fields. CNN architecture implements this through convolutional layers, filters, kernels, slide across input computing. Products at each location, 3x3 filter detecting vertical edges activates strongly wherever vertical boundaries appear in image. Weight sharing ensures same filter detects edges everywhere, reducing parameters from millions, fully connected to thousands while enforcing translation equivariance. Pattern shift causes activation shift. Pooling layers provide translation invariance. Max pooling selects maximum activation within 2x2 regions, discarding precise location while preserving presence, enabling recognition of objects despite small translations. AlexNet's 12 architecture demonstrated this power. 5 convolutional layers with ReLU activations and max pooling followed by 3 fully connected layers achieved breakthrough ImageNet performance. Real-world applications leverage CNN's spatial reasoning. Medical imaging startup ADOC developed CNN detecting intracranial hemorrhages in CT scan. Convolutional layers identify blood density patterns, hyperdense regions greater than 70 Hounsfield units, regardless of brain location. System processes scans in 20 seconds versus 30 minutes for radiologists, flagging critical cases for priority review, reducing time to treatment by 47% in emergency departments. Agricultural robotics company Blue White Robotics employs CNNs on tractor-mounted cameras identifying weeds among crops. Convolutional filters detect plant morphology differences, broadleaf weeds versus narrow cereal crops, enabling precision spraying that reduces herbicide usage 90% while maintaining 99.2% weed kill rate. Autonomous vehicles rely on CNNs for environmental perception. Waymo's perception stack uses multiscale CNNs where early layers detect lane markings and curbs, intermediate layers identify vehicles and pedestrians, deep layers estimate 3D bounding boxes, processing 1.3 million pixels per frame at 10 Hz enabling navigation through complex urban intersections. Architectural innovations address CNN limitations. Residual connections, ResNet, enable training of 1,000 plus layer networks by adding identity shortcuts bypassing layers, gradients flow directly through shortcuts preventing vanishing, inception modules, process inputs through parallel filter sizes, 1 by 1, 3 by 3, 5 by 5, capturing multiscale patterns within single layer, attention mechanisms, SENet, recalibrate channel-wise feature responses emphasizing informative features, improving ImageNet. Accuracy 1.3% computation. These innovations transformed CNNs from academic curiosities into industrial workhorses, processing 4.5 billion images daily across Facebook's platforms, enabling real-time object detection in 2 billion Android devices via TensorFlow Lite, and powering surgical robots that identify anatomical during minimally invasive procedures with sub-millimeter precision. Recurrent neural networks, RNNs, extend deep learning to sequential data, modeling temporal dependencies where current output depends on previous inputs through hidden state recurrence. Basic RNN maintains hidden state H equals sigma, Wx plus UH plus B, where H carries information from prior time steps, enabling language models to predict next word based on context. The sky is blue, not car. However, basic RNNs suffer from vanishing, exploding gradients during backpropagation through time. Gradients decay exponentially long sequences preventing learning of distant dependencies. Long short-term memory, LSTM, networks solved this through gated architecture. Input gate I equals sigma, W times, H, X, plus B, controls new information flow. Forget gate F equals sigma, W underscore F times, H, X, plus B underscore F, regulates memory retention. Output gate O equals sigma, W times, H, X, plus B, modulates output. Cell state C equals FC plus I tan, W underscore C times, H, X, plus B underscore C, maintains long-term memory with minimal distortion. Mechanisms enable LSTMs to learn dependencies spanning hundreds of time steps, critical for applications requiring long-range context. Real-world implementations demonstrate temporal reasoning. Google translates RNN-based system processes entire sentences before generating translations. LSTM encoder reads source sentence build textual representation. Decoder generates target words conditioned on this representation, enabling accurate translation of gendered languages where pronoun gender depends on distant antecedents. The nurse told the patient she needed rest, correctly identifying she refers to nurse in languages with gendered pronouns. Financial systems employ LSTMs analyzing 10-year price histories. Cell state maintains memory of economic cycles, recessions, bubbles, while gates modulate relevance of distant events. JP Morgan's LOXM system uses LSTMs to execute large equity trades, minimizing market impact by timing orders based on predicted short-term price, reducing transaction costs by $150 million annually. Speech recognition systems leverage RNN's sequential processing. Apple's Siri employs bidirectional LSTMs processing audio both forward and backward. Forward pass captures causal context, recognize speech, versus recognize speech, backward incorporates future context resolving ambiguities, achieving 95% word accuracy on noisy mobile recordings. Gated recurrent units, GRUs, simplify LSTMs by merging forget and input gates into update gate Z equals sigma, W underscore Z times, H, X, plus B underscore Z, introducing reset gate R equals sigma, W underscore R times, H, X, plus B underscore R, controlling previous state influence, reducing parameters 33% while maintaining performance for shorter sequences. Industrial predictive maintenance systems use GRUs analyzing sensor time series, reset gate towards irrelevant historical vibrations when new failure modes emerge. Update gate gradually incorporates new degradation patterns. Siemens system predicts turbine failures 14 days in advance with 92% precision by learning temporal signatures of bearing wear across 6-month operational histories. These applications reveal RNN's distinctive value, modeling temporal dynamics where sequence order carries semantic meaning, language syntax, financial trends, sensor degradation patterns, transforming time series data from flat sequences into rich contextual representations enabling prediction, generation, and anomaly detection impossible with static models. Transformers revolutionize sequential modeling by replacing recurrence with self-attention, computing relationships between all sequence elements simultaneously regardless of distance. Self-attention mechanism calculates attention scores between query, Q, key, K, and value, V, vectors derived from inputs. Attention, Q, K, V equals softmax, QK, square root D, V where D scales. Products preventing gradient saturation. For sentence, the animal didn't cross the street because it was too tired. Attention weights connect it strongly to animal, score 0.87, and weakly to street, score 0.03, resolving preference through contextual relationships rather than positional proximity. Multi-head attention employs parallel attention layers with different linear projections. Each head learns distinct relationship types, syntactic dependencies, semantic roles, coreference, then concatenates outputs enabling rich representation learning. Positional projects sequence order information through sinusoidal functions PE equals sin, POS, 10,000 squared, since transformers lack recurrence, preserving order awareness without positional parameters. Transformer architecture stacks encoder layers, self-attention plus feed-forward networks, and decoder layers, masked preventing future token leakage plus encoder-decoder attention, enabling parallel training impossible with sequential RNNs. Real-world impact emerged through BERT, bidirectional encoder representations from transformers, pre-trained on 3.3 billion words through masked language modeling, predicting masked tokens from context, and next sentence. Fine-tuned on GLUE benchmark, BERT achieved state-of-the-art results across 11 NLP tasks. Question answering accuracy jumped from 68.9% LSTM to 87.4% by leveraging bidirectional context. Industry adoption transformed applications. Google Search integrated in 2019 understanding nuanced queries like 2019 Brazil traveler to USA need visa, correctly interpreting to as direction rather than 2019 Brazil traveler who is going to USA versus previous systems misinterpreting as traveler from USA to Brazil. This improved search quality for 1 in 10 English queries. Service chatbots employ transformers for intent recognition. Bank of America's Erica analyzes conversation history through 12-layer transformer identifying user intent. I want to dispute a charge, with 94% accuracy while tracking dialogue state across 15+ turns, reducing human agent handoffs by 38%. Generation systems like GitHub Copilot use transformer decoders trained on 159 terabytes of public code, predicting entire functions from comments, // sort array in descending order, with 40% acceptance rate by developers, accelerating software development while introducing security vulnerabilities requiring careful validation. Vision transformers, VITs, extended this architecture beyond sequences, splitting images into 16 by 16 patches treated as tokens, processing through standard transformer encoder. VITs matched CNNs on ImageNet with sufficient data, demonstrating attention's universality across modalities. Medical imaging startup Path AI employs VITs analyzing whole slide pathology images. Self-attention connects distant tumor regions revealing spatial patterns invisible to CNN's local receptive fields, improving cancer subtype classification accuracy 5.2% critical for treatment selection. Transformers computational cost challenge, self-attention complexity O, n squared, for sequence length n limits context window, GPT-3 processes 2048 tokens versus human working memory capacity of ~7 items but far below document lengths. Innovations address this. Sparse attention restricts connections to local neighborhoods, relevant tokens. Linear attention approximates softmax through kernel tricks reducing complexity to O, n. Retrieval augmented generation fetches relevant passages from external memory extending context. These advances enable practical deployment. Legal AI platform CaseText uses sparse transformers analyzing page contracts, identifying clause risks by attending to related sections scattered throughout document, reducing review time from 4 hours to 22 minutes per contract while maintaining 98% precision on risk detection. Generative models create novel data instances matching training distribution, enabling synthetic data generation, creation, and data augmentation. Generative adversarial networks, GANs, employ adversarial training between generator G and discriminator D. G maps random noise Z to synthetic sample G, Z, attempting to fool D, declassifies samples as real or fake, attempting to distinguish authentic from synthetic. Equilibrium reached when G produces samples indistinguishable from real data. Training dynamics resemble counterfeiting. G improves forgery skills through DS feedback. D enhances detection ability through exposure to increasingly realistic fakes. Real-world applications leverage GAN's photorealism. NVIDIA-style GA generates synthetic human faces indistinguishable from photographs, used by game studios creating diverse character assets without model releases. Training data augmentation for autonomous vehicles. Waymo generates synthetic rainy night driving scenes by translating clear-day footage through GANs, expanding training distribution to rare conditions without dangerous real-world collection. Fashion retailer Zalando employs GANs generating virtual clothing Try-ONS. Customers upload photos. GAN renders garments on their bodies with realistic fabric draping and lighting, increasing conversion rates 27% while reducing returns 35% by improving size, fit expectations. Training challenges include mode collapse where G produces limited diversity, only generating blonde faces despite training on diverse ethnicity. Wasserstein GANs address this through Earth movers distance, providing meaningful loss gradients even when distributions disjoint, enabling stable training of high-resolution generators. Variational encoders, VAEs, approach generation through probabilistic modeling. Encoder maps input X to distribution parameters mu, sigma in latent space. Decoder reconstructs X from latent sample Z tilde mu, sigma. Loss combines reconstruction error with KL divergence, regularizing latent space toward standard normal distribution. VAEs excel at controlled generation through latent space interpolation. Traversing dimensions in face VAE smoothly transitions between attributes, smiling left and right arrow neutral, young left and right arrow old, used by dermatology apps simulating aging effects for skincare recommendations. Diffusion models emerged as state generators through iterative denoising. Forward process gradually adds Gaussian noise to data over T steps, destroying structure. Reverse process neural network predicts noise at each step, enabling sample generation through iterative denoising. Dole times E2 and stable diffusion employ diffusion for text-to-image synthesis, generating photorealistic from textual descriptions, a teddy bear swimming in the ocean at sunset, by conditioning denoising process on text embeddings. Real-world impact spans creative industries. Adobe Firefly integrates diffusion models into Creative Cloud, enabling designers to generate custom textures, expand image boundaries, and recolor objects natural language, reducing asset creation time from days to minutes. Pharmaceutical company In Silico Medicine uses diffusion models generating novel molecular structures with desired binding properties, designing preclinical candidate for idiopathic pulmonary fibrosis in 18 months versus industry average for 0.5 years. Generative capabilities raise ethical considerations. Deepfakes created through GANs enable realistic face swapping for misinformation, necessitating detection systems analyzing physiological signals, inconsistent blinking patterns, or frequency domain artifacts. Copyright questions around training on copyrighted works, then generating derivative content, running licensing frameworks and attribution mechanisms. Generative models thus represent double-edged sword, enabling unprecedented creativity and data efficiency while demanding responsible deployment through detection technologies, legal frameworks, and ethical guidelines. Training deep networks demands sophisticated visualization to prevent overfitting given millions of parameters relative to training examples. Dropout randomly deactivates neurons during training with probability p, typically 0.5, preventing co-adaptation where neurons rely on specific partners rather than learning robust features. During inference, all neurons activate, weight scaled by 1p, maintaining expected activation magnitude. AlexNet's 50% dropout between fully connected layers reduced overfitting, enabling generalization to novel ImageNet classes. Batch normalization stabilizes training by normalizing layer inputs to zero mean and unit variance, reducing covariate shift where parameter updates change distribution of subsequent layer inputs. For minibatch b equals x, compute equals 1 m sigma x, squared b equals 1 m sigma x squared, then normalize x equals x /square root b plus epsilon, finally scale, shift y equals x plus beta where gamma, beta learnable parameters preserving representational capacity. Batch norm enables higher learning rates, for -5x acceleration, reduces sensitivity to initialization, and provides mild regularization. ResNet, 50 training time reduced 28 hours to 6 hours with batch norm. Real-world impact. Medical imaging startup PathAI trains tumor classifiers on limited biopsy datasets, 5,000 images, batch norm plus dropout reduced validation error 18% versus unregularized networks by preventing memorization of scanner-specific artifacts. Data augmentation artificially expands training sets through label-preserving transformations. Computer vision employs random crops, flips, color jittering, and cut mix, pasting patches from one image to another. NLP uses synonym replacement, random insertion, deletion, and backtranslation, translating to foreign language then back. Each recognition applies time stretching, pitch shifting, and additive noise. Tesla's vision system trains on 1.5 billion augmented frames, synthetic rain, fog, snow generated through physics-based rendering, expanded adverse weather coverage 40x beyond real-world collection, critical for safety validation since real-world edge cases occur too rarely for statistical significance. Transfer learning leverages knowledge from source tasks to accelerate learning on target tasks with limited data, pre-training on large dataset, ImageNet, then fine-tuning on small dataset, medical images. Feature extraction freezes early layers pre-trained on source data while trained final classification layers, efficient when target dataset small. Full fine-tuning updates all weights with lower learning rates on pre-trained layers, beneficial when target dataset sufficiently large. Dermatology AI startup Skin Vision fine-tuned ResNet, 50 pre-trained on ImageNet to classify skin lesions using 12,000 dermatologist annotated images, achieved 91% sensitivity for melanoma detection versus 85% for training from scratch, demonstrating transfer learning's data efficiency. Domain adaptation addresses distribution shift between source and target domains. Adversarial training aligns feature distributions across domains by feature extractor to full domain discriminator. Importance weighting reweights source examples based on similarity to target distribution. Waymo adapts perception models trained in Phoenix to San Francisco through domain adaptation. Adversarial alignment of feature distributions reduced false positive rate on San Francisco's dense pedestrian environments by 30% without collecting additional labeled data in New City. These regularization techniques transform deep learning from fragile memorization to robust generalization, enabling deployment in safety-critical domains where failure carries severe consequences. Hardware acceleration enables practical deep learning deployment by optimization for neural network operations. Graphics processing units, GPUs, revolutionize training through massive parallelism. NVIDIA A100 contains 6,912 CUDA cores executing thousands of matrix multiplications simultaneously. Tensor cores accelerate mixed precision training, performed by 4 matrix multiplications in single clock cycle using FP16 inputs with FP32 accumulation, reducing ResNet, 50 training time from 28 hours, FP32, to 6 hours, mixed precision, on NVIDIA V100. Tensor processing units, TPUs, represent Google's application-specific integrated circuits optimized for TensorFlow operations. TPU v4 delivers 275 teraflops of bfloat 16 performance with high bandwidth memory enabling large batch training. Real-world infrastructure. Meta's AI research supercluster contains 6,144 NVIDIA A100 GPU connected through 176 terabits second fabric, training large language models in days versus months on conventional clusters. Edge deployment demands specialized hardware balancing performance, power, and cost. Mobile NPUs, neural processing units, integrate into smartphone SoCs. Apple 16 Bionic 16-core neural engine performs 17 trillion operations, second enabling real-time computational photography, night mode processing 9 frames in 1 second, Qualcomm Hexagon processors accelerate on-device speech recognition reducing cloud dependency and latency. Industrial edge devices employ specialized accelerators. NVIDIA Jetson Orin delivers 275 TOPS for robotics perception enabling real-time object detection on mobile manipulators. Google Coral Edge TPU performs for TOPS at 2 watts for IoT applications like smart cameras detecting intruders without cloud connectivity. Model compression techniques bridge capability gap cloud and edge. Quantization reduces precision from FP32 to INT8. MobileNet v3 quantized to INT8 achieved 3.2x speedup on ARM CPUs with less than 1% accuracy drop enabling real-time segmentation on smartphones. Pruning removes redundant connections. Iterative magnitude pruning eliminated 60 of ResNet, 50 weights with retraining maintaining accuracy while reducing model size 2.3x. Knowledge distillation trains compact student network mimicking. Larger teacher, TinyBERT with 14.5 M parameters matched BERT-base accuracy on GLUE tasks while reducing inference latency 7.5x in deployment on resource-constrained devices. Tesla's full self-driving computer employs custom SoC with 72 TOPS neural accelerator, running quantized vision transformers processing 8 camera streams simultaneously at 36 Hz within 250 watt power budget, demonstrating hardware-software co-design enabling real-world audio. These hardware advances transform deep learning from research curiosity to ubiquitous technology, powering real-time translation on $200 smartphones, enabling autonomous vehicles to process sensor data faster than human reaction times, and bringing medical diagnostic AI to rural clinics through battery-powered edge devices. Deep learning's limitations reveal boundaries where current approaches struggle, highlighting frontiers for future research and hybrid architectures. Reasoning and planning remain challenging. Deep networks excel at pattern recognition but struggle with multi-step logical deduction requiring explicit symbolic manipulation. Mathematics problem illustrates this gap. Minerva language model achieves 50.3% accuracy on high school math problems but fails on novel problems requiring compositional reasoning, solving, if 3 times plus 5 is equal to 20, what is 2x plus 3, requires algebraic manipulation beyond pattern matching in training data. Neurosymbolic integration addresses this by combining neural perception with symbolic reasoning. DeepMind's AlphaGeometry uses language model to generate synthetic geometry theorems, then symbolic solver proves them, achieving gold medal performance on International Math Olympiad problems by leveraging neural pattern recognition for conjecture generation and symbolic engines for rigorous proof. Common sense reasoning exposes another limitation: systems lack implicit knowledge humans acquire through embodied experience. Winograd schema challenges reveal this. The city council refused the protesters a permit because they feared violence versus the city council refused the protesters a permit because they advocated violence, resolving the as understanding that councils fear violence while protesters advocate it. Current language models guess correctly 70% of time versus human 95%, highlighting gap in causal and social reasoning. Embodied AI research addresses this through physical interaction. Robots manipulating objects develop intuitive physics understanding impossible from visual data alone. MIT's learning from play approach has robots interact with 200+ household objects, building internal models of object affordances and dynamics that transfer to novel manipulation tasks. Distributional shift causes catastrophic failure when deployment environments differ from training distribution. Autonomous vehicles trained on California roads fail in snowy Michigan winters because snow changes visual appearance of lane markings and road surfaces. Solutions include domain randomization during training. NVIDIA's robot manipulation system trained in simulation with randomized lighting, textures, and object positions achieved 85% rate on physical robots without real-world training. Test time adaptation adjusts model parameters during deployment using unlabeled test data, reducing error by 40% on corrupted ImageNet benchmarks. Adversarial examples reveal fragility to imperceptible perturbations, adding 0.5% noise to Pander image cores in net, 50 to classify as gibbon with 99.3% confidence. Defenses include adversarial training, exposing models to perturbed examples during training, randomized smoothing, adding noise during inference to create certified robustness regions. Medical imaging systems employ adversarial training to resist patterns that could cause misdiagnosis, reducing attack success rate from 92% to 8% while maintaining 94% clean accuracy. Energy consumption raises sustainability concerns. Training GPT-3 consumed 1,287 megawatt-hours, equivalent to 120 homes for 1 year. In-scale compounds impact with 200 billion daily queries across major platforms. Green AI initiatives address this through algorithmic efficiency, sparse models activating only relevant neurons per input, reducing computation 10x, hardware-aware training optimizing models for specific accelerators, carbon-aware computing scheduling job low-carbon grid periods. These limitations don't invalidate deep learning but contextualize its appropriate domains, pattern recognition in high-dimensional data with abundant examples, while highlighting need for hybrid approaches combining neural learning with symbolic reasoning, causal models, and embodied interaction for robust intelligence. Engineers diagnose when deep learning suits the problem versus when alternative paradigms better address reasoning, planning, or distributional robustness requirements, selecting tools aligned with problem structure rather than defaulting to neural networks for all challenges. Deep learning applications span domains transforming industries through capabilities inbuilt with prior technologies. Healthcare leverages deep learning for early disease detection. Google Health's mammography AI analyzes screening mammograms detecting breast cancer 11 months earlier than radiologists with 5.7% fewer false positives and 9.4% fewer false negatives, deployed across 15 countries screening in women annually. Drug discovery accelerates through protein folding prediction. DeepMind's AlphaFold 2 predicts 3D protein structures with atomic accuracy. Median global distance test score 92.4. Solving 200 million structures in AlphaFold DB, enabling researchers to design drugs targeting previously intractable proteins like those involved in Parkinson's disease. Manufacturing achieves zero-defect production through visual inspection. Foxconn employs CNNs inspecting iPhone components at 200 parts per minute, detecting microscopic defects, scratches less than 10 micrometers, with 99.998% accuracy, reducing failures 76% while eliminating human inspector fatigue-related errors. Agriculture optimizes resource usage through precision farming. John Deere's See and Spray uses real-time CNNs identifying weeds among crops, enabling targeted herbicide application, reducing chemical usage 90% while maintaining 99.2% control efficacy across 10 million acres annually. Entertainment personalizes content at scale. Netflix's recommendation engine employs deep matrix factorization, analyzing 250 million members' viewing histories to predict preferences with 93% accuracy, driving 80% of watched content and saving $1 billion annually. Reduce churn. Climate science models complex Earth systems. Google's GraphCast employs graph neural networks predicting 10-day global weather forecasts in under 1 minute versus 1 hour for traditional numerical models, enabling rapid disaster response planning for hurricanes and floods. Financial services detect fraud in real time. Card's Decision Intelligence analyzes 150 billion annual transactions through deep anomaly detection, flagging suspicious activity within 50 milliseconds while maintaining 99.999% uptime, preventing $25 billion in annual fraud losses. These applications share common success factors: abundant high-quality data reflecting deployment conditions, careful validation on edge cases beyond average performance, human-in-the-loop design maintaining oversight for high-stakes decisions, continuous monitoring detecting performance degradation from distribution shift. Failures occur when these factors neglected. IBM Watson for oncology trained on synthetic cases provided treatment recommendations when deployed in hospitals, highlighting danger of distribution shift between training and deployment environments. Comper's recidivism prediction system exhibited racial bias because training data reflected historical sentencing disparities, demonstrating necessity of fairness auditing before deployment. Deep learning thus functions as powerful, requiring responsible engineering practices, data curation, rigorous validation, bias mitigation, and human oversight to deliver societal benefit while minimizing harm. The technology itself remains neutral, its impact determined by how engineers design, validate, and deploy systems within ethical frameworks prioritizing human well-being alongside technical performance. Slide 7, AI.704, Natural Language Processing. Natural language processing transforms unstructured human language into structured computational representations, enabling machines to comprehend, generate, and reason with text and speech across diverse contexts. Unlike programming languages with rich syntax and unambiguous semantics, human language operates through probabilistic patterns, contextual dependencies, and pragmatic inference where meaning emerges from interaction between words, speaker intent, and situational context. The phrase, "it's cold in here," functions as literal temperature observation in weather discussion but becomes indirect to close window in shared room, requiring systems to infer pragmatic meaning beyond literal semantics. This complexity defines NLP's core challenge, bridging the gap between symbolic language structures and embodied human understanding where words connect to sensory experiences, social norms, and cultural knowledge accumulated through lived experience. Modern NLP systems achieve remarkable capabilities through statistical learning from massive text corpora, Google Translate processing 100 billion words daily across 135 languages, Amazon Alexa interpreting 1 billion voice commands weekly, legal AI platforms analyzing millions of case documents to identify precedents. But these systems remain fundamentally pattern recognizers lacking genuine comprehension of referenced concepts. Understanding this distinction between statistical correlation and causal understanding proves essential for responsible NLP deployment where overattribution of comprehension leads to dangerous overreliance in high-stakes domains like healthcare justice or legal advice. Text preprocessing transforms raw language into computationally tractable representations through systematic normalization pipelines. Tokenization segments text into meaningful units. Penn Treebank tokenizer splits USA into U.S. A. abbreviations while separating punctuation. Spacies rule-based tokenizer handles contractions, don't, do, ent, maintaining morphological integrity essential for syntactic analysis. Real-world impact emerges in social media analysis. Brandwatch processes 95 million daily posts where tokenizer must handle hashtags, Black Lives Matter, Black Lives Matter, emojis, red heart hash, heart, and code switching, Don Esther Albano, to accurately track brand sentiment across cultures. Normalization standardizes variants, lowercasing converts Apple and Apple to identical tokens critical for frequency analysis but proper for named entity recognition where capitalization signals proper nouns. Lemmatization reduces inflected forms to dictionary base, running, ran, runs, run, using morphological analyzers like WordNet's morphe function. Stemming applies heuristic rules. University, universities, universe, faster but less accurate than lemmatization. Stop word removal eliminates high-frequency low-content words, there, is, and, reducing dimensionality, critical for search engines where indexing there would waste 7% of storage given its 5% corpus frequency. Character-level normalization handles noise. Twitter analysis systems convert to so good through repeated character compression and punctuation normalization, improving sentiment classification accuracy 12% by reducing lexical variation. These pre-processing choices directly impact downstream performance. Medical NLP systems analyzing clinical notes preserve negation cues, no evidence of through specialized tokenization, failure to isolate, no causes catastrophic misclassification of patient conditions. Legal document processors maintain section numbering, section 4.2a, as single tokens preserving regulatory reference integrity. Pre-processing thus functions as foundational engineering decision, not mechanical cleanup but semantic preservation requiring domain-specific customization to maintain signal while removing noise. Language modeling quantifies probability distributions over word sequences, enabling prediction, generation, and anomaly detection through statistical patterns learned from text corpora. N-gram models of P, W, 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 through Markov assumption P, W, 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 almost equal to P, W, W, W. Trigram model estimates P, cat, there, black, by counting the black cat occurrences divided by the black occurrences in training corpus. Google billion word benchmark trained trigram model achieves 74.2 perplexity, lower perplexity indicates better prediction with human performance estimated at 12 to 15 perplexity revealing substantial gap between statistical models and human language understanding. Real-world applications leverage n-grams for efficiency, smartphone keyboard, next word through trigram models, typing, on my way, triggers, home, prediction with 89% accuracy based on users' historical patterns, spell checkers identify errors through n-gram probability drops, I am going home shows 1000x lower trigram probability for I'm going versus I'm going triggering correction. Language models overcome n-gram sparsity through distributed representations. Recurrent neural networks maintain hidden state H encoding context history enabling prediction of distant dependencies. LSTM networks with gating mechanisms learn dependencies spanning hundreds of words critical for document-level coherence. Google's neural machine translation employs LSTM encoder-decoder architecture. Encoder processes source sentence into context vector, decoder generates target words conditioned on this vector, reducing translation errors 60% versus phrase-based systems by capturing long-range dependencies like gender agreement across sentence boundaries. The nurse told the patient she needed rest, correctly translating pronoun gender in target language. Transformer-based models revolutionized language modeling through self-attention. BERT's masked language modeling pre-training predicts masked tokens from bidirectional context. Their mask sat on the mat, cat, using both left and right context. GPT series employs causal languaging predicting next token autoregressively enabling coherent text generation. Real-world deployment illustrates scale. Microsoft's Turing NLG model with 530 billion parameters powers Office 365's writing suggestions, analyzing document context to propose grammatical corrections, style improvements, and completions with 92% user acceptance rate. GitHub Copilot's Codex model trained on 159 terabytes of public code predicts entire functions from comments, / sort array descending, with 40% acceptance rate accelerating developer productivity while introducing security. Vulnerabilities require full validation. Language models' limitations manifest in factual inconsistency, GPT-3 generating plausible but false historical claims. Emperor Augustus invented the steam engine, due to training on internet text containing misinformation. Hallucination in medical chatbots fabricating drug dosages requiring retrieval or generation anchoring responses to verified knowledge bases. These challenges necessitate hybrid architectures combining parametric knowledge, model weights, with non-parametric retrieval, external databases, to ensure factual grounding, critical for high-stakes applications where accuracy determines patient safety or legal outcomes. Part of speech tagging assigns grammatical categories to words within context, resolving ambiguity through surrounding words where identical strings function differently. Hidden Markov models, HUMS, model tagging as sequence labeling problem, states represent POS tags, observations represent words, transition probabilities TT, capture grammatical constraints, determiner, likely followed by noun, emission probabilities P, WT, capture lexical preferences, the emits from determiner, with probability 0.98. Viterbi algorithm computes most probable tag sequence through dynamic programming, tagging, time flies like, as, NNVBZ in DTNN, noun verb preposition determiner noun, versus incorrect, NNNNS in DTNN, noun preposition determiner noun. Modern systems employ neural architectures, bidirectional LSTMs process context in both directions, conditional random fields, CRFs, dependencies through global sequence optimization. Real-world applications demonstrate tagging's foundational role. Grammar-checking systems like Grammarly use POS tags to detect errors. She go to school, flagged because verb, go, lacks third-person singular marking after pronoun, she tagged as third-person singular subject. Information systems identify entity types through tag patterns. DTNN in DTNN, pattern, the merger between company A and company B, triggers relation extraction identifying acquisition events. Financial sentiment analysis leverages POS patterns, adjective-noun pairs, strong earnings, weak guidance, carry stronger sentinels than isolated words, systems weighting, strong earnings, 3.2x higher than standalone, strong, improve earnings call sentiment prediction accuracy 18%. Social media analysis confronts informal language challenges, Twitter POS taggers handle hashtags, #Monday motivation proper noun, emojis face with tears of joy interjection, and non-standard spellings, so adverb, through specialized lexicons and character-level embeddings, enabling accurate sentiment tracking during brand crises where informal language dominates discourse. Named Entity Recognition, NER, identifies and classifies real-world entities within text, extracting structured information from unstructured language for knowledge-based population and information retrieval. Sequence labeling approaches treat NER as token classification problem. BIO tagging scheme marks beginning, beeper, inside, IPER, and outside, tokens for entity spans, Barack Obama, beeper, IPER. Feature-based models employ handcrafted features, word shape, Barack capitalized, suffix, ac common in names, context words, president preceding name, gazetteer matches against known entity lists. Neural approaches dominate modern NER. By LSTM CRF architectures combine LSTM modeling with CRF sequence constraints preventing invalid transitions. IPER cannot follow O without preceding beeper. Transformer-based models like BERT achieve state-of-the-art through contextual embeddings where Washington embedding differs in George Washington, person, versus Washington, D.C. Location. Real-world deployments as business value. Financial institutions employ NER extracting company names, executives, and deal terms from earnings calls. JP Morgan's Coin platform processes 12,000 annual commercial loan agreements extracting 150 data points per document, reducing manual review from 360,000 hours to seconds. Systems extract patient conditions, medications, and procedures from clinical notes. Mayo Clinic's NLP pipeline identifies 94% of adverse drug events from unstructured physician notes, enabling proactive intervention. Recruitment platforms parse resumes extracting skills, companies, and education. Links to matches candidates to jobs through entity-aware search, improving placement accuracy 31%. Domain adaptation challenges emerge when models trained on news text. CoNLL, 2003 benchmark, encounter specialized language. Biomedical NER requires recognizing gene names, BRCA1, and chemical bands. CHNO, legal NER identifies case citations. Smith vs. Jones, 123 U.S. for 56, and statutory references, 42 U.S.C. Section 1983. Transfer learning addresses this through domain-specific pre-training. BioBERT pre-trained on PubMed abstracts improve medical NER F1 score from 78.3%, BERT base, to 86.7%. LegalBERT pre-trained on court opinions enhances legal entity extraction by 14.2 points. These adaptations prove essential for practical deployment where generic models fail on domain-specific terminology and syntactic parsing. Syntactic parsing reconstructs grammatical structure of sentences, modeling hierarchical relationships between words through constituency or dependency representations. Constituency parsing builds phrase structure trees where nodes represent grammatical phrases. Sentence, the cat sat on the mat, parses as S, N, DT there, NN cat, VP, VBD sat, PP, IN on, NP, DT there, NN mat, revealing noun phrase, the cat, as subject and prepositional phrase, on the mat, as location modifier. Probabilistic context-free grammars, PCFGs, assign probabilities to production rules. NP-DT-NN equals 0.85 based on training corpus frequencies. CYK algorithm computes most probable parse through dynamic programming. Dependency parsing represents relationships as directed graphs where nodes are words and edges are grammatical relations. Head-dependent structure with sat as root, cat as NSUBJ, mat as object of preposition, POBJ. Transition-based parsers employ stack buffer architecture, making incremental decisions. Shift, left arc, right arc. Graph-based parsers score all possible edges then select maximum spanning tree. Neural parsers achieve state-of-the-art through contextual. Stanford's graph-based parser with BERT embeddings achieves 96.4% unlabeled attachment score on Penn Treebank. Real-world applications leverage syntactic structure for semantic interpretation. Machine translation systems use dependency trees to reorder constituents according to target language syntax, translating English SOV, I see the dog, to Japanese SOV, I the dog see, through dependency-guided reordering, reducing word order errors 43%. Question answering systems match question syntax to passage structure. Who directed inception identifies directed as relation and inception as object. Enabling precise answer extraction. Christopher Nolan directed Inception in 2010, voice assistants resolve pronoun references through syntactic binding. Show me flights to Chicago and hotels there. Uses dependency path connecting there to Chicago through prepositional phrase structure enabling correct location resolution. Parsing challenges intensify with informal language. Media text contains fragments. Going to Chicago tomorrow, ellipsis, so the movie. Loved it, and non-standard punctuation requiring robust parsers trained on diverse genres. Google's conversational parser handles these variations through data augmentation with synthetic fragments and transfer learning from formal to informal domain, achieving 91.3% parsing accuracy on Twitter data versus 76.8% for parsers trained solely on news text. Semantic role labeling, SRL, identifies predicate argument structures within sentences, extracting who did what to whom, relationships essential for deep language understanding. FrameNet provides lexical resource where predicates evoke semantic frames with frame elements. Predicate, by, evokes commerce_by frame with buyer, seller, goods, and money elements. SRL systems assign labels like ARG0, agent, ARG1, patient, ARGMLOC, location where, to constituents, John, ARG0, port, V, a book, ARG1, from Amazon, ARGMLOC, for $20, ARGMMNR. Pipeline approaches first identify predicates then label arguments. End-to-end neural models jointly predict both through span-based architectures. BERT-based SRL achieves 87.2% F1 on CoNLL, 2012 benchmark by leveraging contextual embeddings where run embedding differs in run a company, manage, versus run a marathon, move quickly. Real-world applications demonstrate SRL's value for information extraction. Business intelligence systems analyze earnings calls extracting commercial events. Apple sold 50 million iPhones in Q4 triggers commerce_sell frame with seller equals Apple, goods equals iPhones, quantity equals 50 million, time equals Q4 enabling automated financial database population. Healthcare NLP extracts clinical events from notes. Patient 5 mg warfarin daily identifies treatment frame with patient equals present patient, medication equals warfarin, dosage equals 5 mg, frequency equals daily supporting medication reconciliation systems. Legal document analysis identifies contractual obligations. Tenant shall maintain premises in good condition. Extracts obligation frame with obligor equals tenant, obligee equals landlord, action equals maintain premises enabling automated compliance checking. SRL limitations emerge with implicit arguments. John bought a book, amidst seller requiring world knowledge inference. Metaphorical language, Apple devoured the competition, requiring devour metaphor to acquire frame. These challenges necessitate integration with knowledge bases and common sense reasoning modules. Systems combining SRL with ConceptNet infer missing sellers from commercial context. Metaphor resolution modules map literal predicates to figurative frames through similarity metrics. Despite limitations, SRL provides critical bridge between surface syntax and deep semantics, enabling machines to extract structured event representations from unstructured text for downstream reasoning and decision support. Sentiment analysis quantifies subjective opinions expressed in text, classifying polarity, positive, negative, neutral, and aspect-specific attitudes essential for brand monitoring, market research, and customer experience management. Document-level classification assigns single sentiment score to entire text. Movie review: this film was breathtakingly beautiful with stunning performances, positive. Feature-based approaches employ sentiment lexicons. CentuWordNet assigns positivity, negativity scores to synsets. Wonderful, plus 0.875, terrible, minus 0.875. Machine learning classifiers combine lexicon scores with n-gram features. Neural approaches leverage contextual embeddings. BERT fine-tuned on SSD, 2 dataset achieve 4.8% accuracy by capturing negation scope, not good versus good, and intensifiers, very good versus good. Aspect-based sentiment analysis, ABSA, provides granular insights by identifying sentiment toward specific entities or attributes. The battery life is excellent but the screen resolution yields battery, positive, screen, negative. Pipeline ABSA first extracts aspects through dependency parsing identifying noun phrases modified by sentiment words, then classifies sentiment toward each aspect. Real-world deployments illustrate business impact. Amazon analyzes 500 million annual reviews through ABSA, identifying that 68% of negative smartphone reviews mention battery life versus 22% mentioning camera, enabling targeted engineering improvements that increased customer satisfaction 15% for subsequent models. Airline reputation management systems process 2 million annual tweets. ASA reveals sentiment toward baggage handling dropped 22 points after fee increases while in flight. Service sentiment remained stable, guiding service recovery investments. Political campaigns analyze voter sentiment toward policy positions. 2020 U.S. presidential campaign teams tracked sentiment toward healthcare and economy, demographics identifying swing voter concerns enabling message refinement. Multilingual sentiment analysis confronts cultural variation in expression. Japanese reviews use indirect negation, not unimpressive, equals positive, requiring culture-specific lexicons. Arabic sentiment employs religious phrases, mashallah, indicating approval, needing specialized dictionaries. Transfer learning addresses low-resource languages. Embert fine-tuned on English sentiment data then adapted to Swahili through 10,000 labeled examples achieves 82.3% accuracy versus 67.1% for monolingual Swahili model trained on same data. These adaptations potential for global brands operating across cultural contexts where direct translation of sentiment models fails due to linguistic and cultural differences in emotional expression. Machine translation converts text between languages while preserving meaning, overcoming challenges of structural divergence, lexical ambiguity, and cultural context by word-for-word substitution. Statistical machine translation, SMT, dominated pre-2017 era. Phrase-based systems like Moser's aligned bilingual corpora to extract phrase pairs, good morning, left and right arrow, buenos dias, then reordered phrases using distortion models. SMT limitation included poor handling of long-range dependencies and fluency issues from phrase fragmentation. Neural machine translation, NMT, revolutionized the field through encoder-decoder architectures, sequence-to-sequence models with attention mechanisms dynamically weighting source words during target generation. Google's 2016 Trans-to-NMT reduced translation errors 60% across languages by capturing context holistically, translating, he saw the girl with the telescope, correctly as, el vio a la niña con el telescopio, he used telescope, versus ambiguous SMT output. Transformer architectures further improved quality through self-attention. Google translates transformer model processes entire sentence context enabling accurate gender disambiguation in target languages with grammatical gender. The nurse told the patient she needed rest, correctly feminine pronoun in French, elle avait besoin de repos. Real-world applications demonstrate translation's societal impact. Humanitarian organizations deploy offline NMT on smartphones. Translators Without Borders uses Facebook's M2M 100 model translating 100 languages enabling aid workers to communicate with refugees speaking rare languages like Rohingya without internet connectivity. E-commerce platforms localize product listings. Alibaba's translation system processes 1 million product descriptions daily between Chinese and 18 languages increasing. Cross-border sales 34% by overcoming language barriers. Medical interpretation services employ NMT for preliminary translation. Hospital systems translate patient intake forms through NMT then route complex cases to human interpreters. Interpretation wait times from 45 minutes to 8 minutes while maintaining safety through human oversight for critical communications. Low-resource language challenges persist. Languages with under 1 million parallel sentences suffer quality degradation. Multilingual transfer learning addresses this. Facebook's M2M 100 retrained on 7.5 billion sentence pairs across 100 languages enables zero-shot translation between language pairs never seen during training. Swahili Bengali, by leveraging shared representations, pivot translation routes through high-resource language, Swahili English Bengali, though accumulating errors. These advances democratize access to information across linguistic boundaries while highlighting persistent inequities. 95% of NLP research focuses on 1% of world's languages, necessitating community-driven efforts like Masakane advancing African language NLP through grassroots collaboration. Question answering systems retrieve or generate precise answer natural language queries, spanning extractive QA, identifying answer spans in passages, abstractive QA, generating novel answers, and open domain QA, retrieving answers from large corpora. Extractive QA frames answer selection as span prediction problem, given passage, Paris is the capital of France, and question is the capital of France, system predicts start token Paris, and end token Paris. BERT fine-tuned on squad dataset achieves 93.5% F1 by modeling question passage interaction through self-attention. Attention heads learn to align question words, capital, with passage entities, Paris. Real-world deployment include enterprise search. IBM Watson answers processes employee queries against internal knowledge bases. How do I reset my password? Extracting answers from HR policy documents with 89% accuracy, reducing helpdesk tickets 37%. Customer support chatbots answer product questions by retrieving answers from manuals. What is the warranty period for Model X? With 92% first contact resolution. Open Domain QA combines retrieval and reading, DPR, dense passage retrieval, encodes questions and passages into shared vector space, enabling semantic search beyond keyword matching. Reader model then extracts answers from top passages. Google's Multitask Unified Model, MUM, processes 75 languages simultaneously, enabling cross-lingual QA. How do I fix a leaky faucet? Retrieves English repair guides, then translates instructions to user's language. Abstractive QA generates answers synthesizing information from multiple sources. T5 model trained on natural questions dataset generates answers like, the Eiffel Tower was built in 1889 for the World's Fair, by fusing facts from multiple retrieved passages. Medical QA systems demonstrate high-stakes applications. IBM Watson for oncology analyzes patient records and medical literature to answer what treatments are recommended for stage 3 lung adenocarcinoma, generating evidence-ranked treatment options with supporting citations. Rigorous validation revealed limitations when training data lacked diversity. System recommended unsafe treatments for rare subtypes, highlighting necessity of human oversight in clinical decision support. QA limits include handling unanswerable questions. Squad 2.0 introduced unanswerable questions requiring systems to abstain when passage lacks answer. Real-world systems employ confidence thresholds, abstaining when prediction probability falls below 0.85 to avoid hallucinated answers. These safeguards prove critical for trustworthy deployment where incorrect answers carry consequences in legal, medical, or financial domains. Dialogue systems enable interactive language-based interaction through task-oriented or open-domain architectures, modeling conversation structure, maintaining state, and generating contextually appropriate responses. Tasked dialogue systems follow pipeline architecture. Natural language understanding, NLU, extracts intents and slots. Book a flight to Paris, intent, book flight, slot, destination equals Paris. Dialogue state tracking, DST, maintains belief state across turns. Destination equals Paris, dates equals unspecified, policy selects action, request departure date. Natural language generation, NLG, produces response, when would you like to depart? Real-world deployments include airline booking assistance. Delta's chatbot handles 60% of booking inquiries, reducing call center volume 28% by maintaining complex state across 50 turns, including multi-city itineraries and seat preferences. Healthcare symptom checkers like Babylon Health extract symptoms through dialogue. Where is the pain? Location equals abdomen, severity equals 7, 10, then provide triage recommendations with appropriate disclaimers. Open domain dialogue systems generate in conversation without predefined tasks. Sequence-to-sequence models with attention generate responses conditioned on dialogue history. Transformer-based models like BlenderBot employ multitask training on dialogue acts, empathy detection, and knowledge grounding. Facebook's BlenderBot 3 engages users in 14-minute average conversations by relevant knowledge from web search during interaction. User mentions latest Marvel movie, triggers search, then generates informed response about Black Panther, Wakanda Forever. Safety challenges plague open domain systems. Microsoft's Tay chatbot learned toxic language from Twitter interactions within hours. Modern systems employ layered safety. Input filtering blocks harmful prompts. Response classifiers detect toxic outputs. Human-in-the-loop review for ambiguous cases. Empathetic dialogue represents emerging frontier. Wobot Health's therapeutic chatbot employs cognitive behavioral therapy techniques detecting emotional cues. I feel overwhelmed, then guiding users through exercises with 78% user retention over 8 weeks, demonstrating clinical efficacy for mild depression. Dialogue evaluation moves beyond perplexity to multidimensional metrics. Task success rate for goal-oriented systems. engagement duration and user satisfaction for open domain, safety metrics quantifying toxic response rate, empathy scores from human evaluators. These metrics guide development towards systems that are not merely fluent but helpful, safe, and emotionally intelligent, critical for applications in mental health support, education, and elder care where dialogue quality directly impacts human well-being. Word embeddings transform discrete word continuous vector representations capturing semantic relationships through distributional similarity. Words appearing in similar contexts occupy proximate vector space regions. Word 2-vex skipgram model predicts context words given target word, training objective maximizes p, context target, through negative sampling, resulting exhibit linear relationships where king, man plus woman almost equal to queen, cosine similarity 0.78. Glove, global vectors, combines global co-occurrence statistics with local context windows, factorizing word context matrix to produce vectors where semantic and syntactic relationships emerge geometrically. Real-world applications leverage embeddings for semantic search. Airbnb's search system maps query, cozy cabin near lake, to listing descriptions through embedding similarity, increasing booking conversion 18% by matching semantic intent beyond keyword overlap. Recommendation systems employ embeddings to model user-item interactions. NLP pipeline embeds song lyrics and user playlists into shared space enabling discovery features that recommend songs with similar thematic content. Songs about heartbreak, matching both Someone Like You and Back to December despite different artists, genres. Contextual embeddings overcome static embedding limitation. Polysemy causes vector averaging. Bank, in, riverbank, and savings bank share single vector despite distinct meanings. Elmo, embeddings from language models, generates context-dependent embeddings through bidirectional LSTM. First layer captures syntax, second layer captures semantics. Bank, in, riverbank activates different neurons than savings bank. BERT extends this through transformer architecture. 12-layer model produces embeddings where bank vector differs by 0.82 cosine distance between financial and geographical contexts. Real-world impact emerges in clinical text processing. Mayo Clinic's NLP uses BioBERT embeddings distinguishing positive attitude, sentiment, versus positive test result, medical finding, reducing diagnostic error 23% by preventing conflation of emotional and clinical positivity. Embedding debiasing addresses problematic associations. Gender bias where doctor, closer to he than she, cosine similarity difference 0.18. Hard debiasing removes gender subspace from embeddings. Soft debiasing reduces bias while preserving semantic relationships. Google Search implemented embedding debiasing reducing gendered occupation suggestions. Nurse jobs, no longer predominantly showing females, demonstrating that representation choices carry ethical consequences requiring proactive mitigation. These techniques transform language from symbolic tokens into geometric objects enabling algebraic manipulation of meaning, foundation for virtually all modern NLP systems where semantic relationships become computable through vector arithmetic. Large language models, LLMs, represent paradigm shift through scale-driven emergent capabilities. Models with hundreds of billions of parameters trained on trillions of tokens exhibit abilities absent in smaller counterparts including in-context learning, chain-of-thought reasoning, and instruction following. GPT-3, 1.5b parameters, demonstrates few-shot learning, receiving prompt with 2 examples, translate English to French, see otter loutre de mer, peppermint menthe poivre, then correctly translating novel words without weight updates. Chain of thought prompting elicits step-by-step reasoning. Question: if John has 5 apples and gives 2 to Mary, how many does he have left? A. John starts with 5 apples. He gives away 2 apples. 5 minus 2 is equal to 3. John has 3 apples left. Improving arithmetic accuracy from 17.7% to 78.7% on GSM 8K bench by making reasoning explicit. Instruction tuning aligns models with human preferences. FLAN, T5 fine-tuned on 1,836 NLP tasks with task prefixes, translate English to German, achieves zero-shot generalization across unseen tasks. Real-world deployments illustrate LLM capabilities and limitations. GitHub Copilot generates code from comments with 40% acceptance rate but introduces security vulnerabilities in 16% of suggestions requiring developer vigilance. Medical chatbots like Babylon Health's AI triage system provide symptom assessment but hallucinate drug dosages, necessitating mandatory disclaimers and human right. Legal research assistants like CaseText's co-counsel analyze case law but occasionally misstate precedents, requiring attorney verification. Safety challenges demand layered mitigation. Constitutional AI trains models to refuse harmful requests through reinforcement learning from human feedback, retrieval augmentations responses in verified knowledge bases, reducing hallucinations 62%. Uncertainty quantification flags low confidence predictions for human review. Economic impact transforms knowledge work. McKinsey estimates LLMs could automate 30% of current work hours in software engineering, customer operations, and content while augmenting productivity in legal, medical, and scientific domains. Critical limitations persist. Factual inconsistency due to training on internet text containing misinformation, recency bias where models lack knowledge beyond training cutoff, GPT-3 cutoff June 2021, inability to reason about physical world embodied experience, energy consumption during training, GPT-3, 1,287 megawatt-hours, and inference at scale. These limitations necessitate human-AI collaboration paradigms, systems designed for augmentation rather than replacement where humans provide oversight, contextual judgment, and ethical while AI handles pattern recognition and information synthesis. Responsible deployment requires transparency about capabilities and limitations, human-in-the-loop design for high-stakes decisions, continuous monitoring for emerging risks, and equitable access ensuring benefits extend beyond privileged users, principles essential for NLPs that increasingly mediate human communication, information access, and decision-making. NLP ethics addresses societal impacts of language technologies through proactive design choices mitigating harm while maximizing benefit. Algorithmic bias manifests when training data reflects historical inequities. Sentimentalist systems show 15% lower accuracy for African American English dialects due to underrepresentation in training corpora. Resume screening tools downgrade candidates from women's colleges due to historical hiring patterns encoded in training data. Mitigation strategies include debiasing embeddings through subspace projection, adversarial training, protected attribute information from representations, diverse data collection ensuring equitable representation across demographics. Privacy preservation demands architectural choices. Apple's on-device Siri processing keeps voice recordings on iPhone rather than cloud servers, preventing mass surveillance while maintaining functionality. Differency adds calibrated noise to language model training, preventing membership inference attacks where adversaries determine if specific text appeared in training data. Misinformation challenges require multilayered defense. Facebook's NLP systems detect coordinated inauthentic behavior through linguistic similarity analysis, identifying bot networks. Fact-checkations flag disputed claims with context from verified sources. Watermarking techniques embed detectable signals in AI-generated text, enabling identification of synthetic content. Dual-use awareness recognizes beneficial technologies can enable harm. Translation tools bridging language barriers also enable cross-border harassment. Sentimentalist improving customer experience also enables mass surveillance of dissent. Researchers bear responsibility implementing safeguards, capability restrictions limiting functionality in high-risk contexts, refusing to generate harassment templates, access controls preventing malicious actors from obtaining powerful systems, transparency enabling of misuse through output watermarking. Environmental impact demands sustainable practices. Model compression reducing inference energy 10x through pruning and quantization, carbon-aware training scheduling jobs during low-carbon grid periods, efficiency-focused architectures like mixture of experts activating only relevant subnetworks per input. Global equity requires addressing linguistic imperialism. 95% of NLP research focuses on English despite representing 4% of world's population. Initiatives like Massacane advancing African language NLP through community-driven data creation and model development, multilingual models with balanced training data preventing dominant resource languages. These ethical dimensions aren't peripheral concerns but foundational design parameters shaping data collection protocols, model architectures, validation procedures, and deployment strategies from project inception. Engineers bearing professional responsibility to anticipate consequences, engage diverse stakeholders, prioritize human dignity alongside technical performance metrics. NLP systems increasingly mediate human communication, information access, and social participation, their design thus carries profound societal implications demanding ethical reflection woven into technical decisions rather than treated as afterthought. Slide 8, AI.705, Computer Vision, Advanced Topics and Emerging Frontiers. Advanced computer vision transcends basic object recognition to achieve holistic scene understanding where systems comprehend spatial relationships, physical dynamics, functional affordances, and causal interactions within visual environments, transforming pixels into actionable world models that support reasoning, planning, and physical interaction. Unlike early vision systems that produced flat lists of detected objects, car, pedestrian, traffic light, modern architectures construct structured scene graphs representing entities as nodes and relationships as edges, car, driving, road, adjacent to, sidewalk, occupied by, pedestrian, enabling downstream reasoning about interactions and constraints. This representational shift powers capabilities once considered science fiction, autonomous vehicles predicting pedestrian intent by analyzing gait patterns and head orientation, surgical robots identifying anatomic structures while understanding their functional relationships, ureter runs parallel to iliac artery, warehouse robots recognizing that a toppled box requires uprighting before grasping. The progression from detection to understanding manifests through hierarchical scene representation frameworks. PixelNet processes raw pixels, ObjectNet identifies RelationNet models pairwise interactions, SceneGraphNet constructs holistic graphs, and WorldModelNet simulates future states through learned dynamics, each layer building upon the previous to transform visual input into predictive, actionable knowledge. Tesla's occupancy networks exemplify this progression, replacing traditional voxel-based occupancy grids representing free space versus occupied space at 10 cm resolution across 250-meter range. System reasons about drivable volumes rather than discrete object categories, enabling navigation around novel obstacles, fallen trees, construction debris, never seen during training by understanding spatial rather than object identity. Vision transformers revolutionized visual representation learning by replacing convolutional inductive biases with pure self-attention, treating images as sequences of patches processed through transformer encoders originally designed for language. Vision transformer (VIT) architecture splits image fixed-size patches, e.g., 16 by 16 pixels, linearly embeds each patch, prepends learnable, CLS, token for classification, then processes sequence through standard transformer encoder with positional embeddings encoding spatial relationships. VIT's breakthrough emerged not from architectural novelty but from scale. Trained on 300 million images, 6TL16 achieved 88.55% top, 1 accuracy on ImageNet surpassing CNNs despite lacking translation equivariance. Real-world deployments demonstrate VIT's distinctive capabilities. Medical imaging. Path AI's cancer grading system employs VIT analyzing slide pathology images where self-attention connects distant tumor regions revealing spatial heterogeneity patterns invisible to CNN's local receptive fields. System improved cancer subtype classification accuracy 5.2% critical for treatment selection where spatial distribution of tumor-infiltrating lymphocytes predicts immunotherapy response. Satellite imagery. Maxar Technologies employs VIT analyzing 50 cm resolution satellite imagery identifying infrastructure changes across 100 square kilometers regions. Self-attention captures long-range dependencies enabling detection of subtle patterns like illegal mining operations spanning multiple image tiles. Agricultural monitoring. Just Crop Health System employs VIT processing multispectral drone imagery where attention heads learn to focus on specific spectral bands, near-infrared for vegetation health. Thermal for water stress, enabling early disease detection 14 days before visible symptoms. SWIN Transformer introduced hierarchical design essentials prediction tasks. Shifted windows limit self-attention to local regions then merge windows hierarchically enabling efficient computation while preserving translation invariance. SWIN v2 scales to 3 billion parameters achieving state-of-the-art on 40-plus vision tasks. Autonomous vehicles leverage SWIN transformers for real-time perception. DriveThor platform employs SWIN-B processing 8 camera streams simultaneously generating semantic segmentation, depth estimation, and object detection through shared backbone reducing latency 40% versus separate CNNs while improving map 3.2 points through feature sharing across tasks. Vision language pre-training bridges visualistic modalities through joint embedding spaces, CLIP, contrastive language image pre-training, trains image and text encoders to maximize similarity between matching pairs while minimizing similarity between mismatches across 400 million image, text, pairs scraped from internet. Resulting embeddings enable zero-shot transfer where natural language description as classifiers classified this image as a photo of a dog versus a photo of a cat. Real-world clip deployments include content moderation. Pinterest employs clip filtering 500 million monthly uploads identifying policy-violating content through natural language queries, images containing weapons, task-specific training, robotic manipulation. Google's second system combines clip with affordance prediction enabling robots to execute novel commands, pick up the red tool, by grounding language in visual affordances without explicit object detectors for every tool. Variant, accessibility. Microsoft Seeing AI employs scribing complex scenes for visually impaired users. A woman in blue dress sitting at cafe table with coffee cup, achieving 89% description accuracy versus 72% for captioning-only models. DIN of 2 self-supervised learning eliminates dependence on labeled data. Self-distillation framework where teacher network processes multi-views generating pseudo-labels for student network, resulting features transfer effectively to downstream tasks without fine-tuning. Meta's DIN of 2 features deployed across 100+ internal applications. Instagram employs DIN of 2 embeddings for visual search enabling users to find similar products through images without manual tagging. Horizon Robotics employs DIN of 2 for robot navigation in unlabeled environments achieving 94% obstacle avoidance accuracy without semantic labels by leveraging geometric consistency in self-supervised features. These transformer-based approaches represent paradigm shift from handcrafted inductive biases, convolutional locality, translation equivariance, toward data-driven representation learning where scale and diversity of training data shape inductive biases, enabling capabilities impossible with CNNs alone while demanding massive compute resources and raising questions about environmental sustainability and accessibility of state-of-the-art vision systems. 3D vision reconstructs spatial structure and geometry from 2D observations, enabling robots to navigate physical environments, autonomous vehicles to avoid obstacles, and AR systems to anchor virtual objects in physical space with metric accuracy. Neural radiance fields, NERFs, represent scenes as volumetric functions. Multilayer perceptron maps 5D coordinates, x, y, z, theta, phi, to volume density sigma and view-dependent color C. Differentiable rendering integrates colors along rays enabling optimization from posed images through gradient descent. Instant NGP accelerated NERF training 1000 hash grid encoding, multi-resolution hash tables store feature vectors at grid vertices, trilinear interpolation retrieves features for arbitrary coordinates, combined with tiny MLPs enables training in seconds rather than hours. Real-world NERF deployments span domains, visual effects. Wetter FX employs instant NG-creating photorealistic digital doubles for avatar sequels reducing actor reshoots by 40% and enabling performance capture in challenging environments, underwater scenes, real estate. Zillow's 3D home tours use NERFs creating immersive walkthroughs from smartphone videos enabling accurate square footage measurement, plus or minus 2%, critical for property valuation. Robotics, NVIDIA's VMware framework employs NERFs for tabletop manipulation. Robots build scene representations from 3 to 5 images then plan grasps in continuous 3D space achieving 92% success rate on novel objects without CAD models. Gaussian emerged as real-time NERF alternative, representing scenes as collections of 3D Gaussians with position, covariance, opacity, and spherical harmonics coefficients. Differentiable splatting projects Gaussians to image plane enabling real-time rendering at 100+ FPS on consumer GPUs. Apple's Vision Pro employs Gaussian splatting for environment capture. Users scan rooms with headset cameras generating photorealistic 3D environments in 60 seconds enabling virtual objects to cast shadows on real surfaces and reflect in mirrors with physical accuracy. Automotive companies employ Gaussian splatting creating digital twins of test tracks. BMW scans proving generating centimeter-accurate 3D models enabling simulation of edge cases, wet cobblestone roads, glare conditions. Impossible to safely test physically. 3D Gaussian splatting sufficiency enables mobile deployment. Snapchat's AR lenses employ on-device Gaussian splatting rendering persistent virtual objects anchored spaces with 2 mm accuracy at 30 FPS on smartphone GPUs. Multiview stereo, MVS, reconstructs dense 3D geometry from calibrated camera arrays, cost-volume construction aggregates matching costs across views, regularization enforces smoothness while preserving discontinuities, depth mapping combines estimates from multiple views into unified point cloud. Autonomous vehicles employ MVS for detailed environment modeling. Waymo's perception system fuses LiDAR with MVS-derived depth maps, creating dense 3D representations of urban scenes, enabling precise path planning around complex obstacles like construction zones with 10 areas and workers. System achieves 5 cm accuracy at 50-meter range, critical for navigating narrow streets. Structure from motion, SFM, reconstructs 3D scenes from unordered image collections. Feature matching establishes correspondences across images. Essential matrix decomposition recovers relative camera poses. Bundle adjustment jointly optimizes 3D point positions and camera parameters, minimizing reprojection error. Cultural heritage preservation leverages SFM. SciArc digitizes endangered heritage sites like Bagan temples in Myanmar through SFM, processing thousands of tourist photos, creating millimeter-accurate 3D models for restoration planning after 16 earthquake. Real estate. Matterport's spatial cameras capture room scans through SFM, enabling virtual property tours with accurate measurements for furniture placement, reducing return rates 27% for online furniture retailers. Point cloud processing handles unordered 3D point sets. PointNet processes points through shared MLPs with symmetric functions. Max pooling, ensuring permutation invariance. PointNet++ adds hierarchical grouping, capturing local structures. PointBERT employs masked auto-encoding for self-supervised pre-training. Autonomous vehicles rely on point cloud processing for LiDAR data. Waymo's systems point clouds into objects, vehicles, pedestrians, through PointACNN, achieving 78.3% 3D map on Kitty benchmark. Temporal tracking maintains object identities across frames, enabling behavior prediction. Pedestrian likely to cross based on trajectory curvature. 4D reconstruction extends 3D domain. Dynamic NERF models time-varying scenes through deformation fields, mapping canonical space to observed space at each timestamp. NERFIS enables selfie videos with professional cinematography by reconstructing dynamic scenes from casually captured videos. Entertainment applications leverage 4D reconstruction. Disney employs dynamic NERF, creating volumetric video of actors, enabling virtual camera movements impossible during physical filming. Meta's codec avatars employ 4D reconstruction, creating photorealistic avatars for VR meetings where facial expressions and body language transmit naturally across distances. These 3D vision capabilities transform flat images metric spatial understanding, essential for physical interaction where robots must grasp objects with millimeter precision, vehicles must maintain safe distances in 3D space, and AR systems must anchor virtual content with physical plausibility. Video understanding extends computer vision to temporal domain, modeling motion patterns, recognizing activities, tracking objects across frames, and predicting future states to comprehend dynamic scenes beyond static snapshots. Video transformers process spatiotemporal tokens through 3D attention. Timesformer divides video into spacetime patches, applying factorized attention, spatial within frames, temporal across frames, enabling efficient modeling of long-range dependencies. Video MAE employs masked auto-encoding pre-training, where 90% of video tubes masked during training, forcing model to reconstruct motion dynamics from sparse observations. Real-world deployments demonstrate video understanding's value. Sports analytics. Second Spectrum's tracking system employs video MAE, analyzing broadcast footage, recognizing complex plays, pick and roll, isolation, and player roles with 94% accuracy, enabling real-time coaching insights. System tracks all 10 players plus ball at 25 Hz, generating advanced metrics like defensive impact scores derived from movement patterns impossible to quantify manually. Healthcare, safely use fall detection system monitors senior living facilities through video MAE, recognizing pre-fall indicators, staggering gait, loss of balance, 3.2 seconds before impact, enabling staff intervention, reducing fall injuries by 42%. System distinguishes falls from and through temporal dynamics analysis, achieving 99.3% specificity, minimizing false alarms. Retail analytics. Walmart's people counters employ video transformers, tracking shopper movements through stores, analyzing dwell times and path patterns to optimize store layouts, increasing sales per square foot by 8%. identifies that customers spending greater than 90 seconds in cereal aisle but not purchasing indicates confusing product placement, enabling targeted interventions. Action recognition classifies human activities through temporal modeling. Two-stream networks process spatial stream, RGB frames for appearance, and temporal stream, optical flow from, then fuse streams for classification. I3D inflates 2D CNN filters to 3D, enabling end-to-end spatiotemporal feature learning. Timesformer employs pure transformer architecture with divided spacetime attention. Manufacturing applications leverage action recognition. Siemens production line monitors recognize assembly errors through estimation, detecting incorrect tool usage or missing components with 97.3% accuracy, triggering immediate quality alerts. System identifies that technicians skipped torque verification step by analyzing tool motion patterns, reducing defect escape rate 63%. Video object detection extends image detection to video sequence, leveraging temporal redundancy to improve accuracy and efficiency. Feature propagation reuses features from previous frames, reducing computation. Tube linking connects detections across frames, forming object trajectories. Memory networks store historical features, enabling long-term context. Waymo's perception system employs object detection, achieving 82.1% map on Waymo open dataset versus 78.3% for image-based detection. Temporal context resolves occlusions. Pedestrian hidden behind bus reappears correctly tracked, and reduces false positives. Flickering detection smoothed through temporal consistency. Video instance section unifies detection, tracking, and segmentation. MaskTrack RCNN extends Mask RCNN with tracking branch. SIPMask employs single-shot architecture for real-time performance. Autonomous delivery robots employ video instance segmentation. Starship Technologies sidewalk robots segment and track pedestrians and vehicles, maintaining 2-meter safety buffer while navigating crowded urban environments with 99.97% collision-free operation across 5 million deliveries. Future prediction models anticipate scene evolution. PredRNN employs recurrent networks with zigzag memory flow, capturing long-term dynamics. Video models generate future frames through denoising. Diffusion processes conditioned on past observations. Autonomous vehicles leverage prediction for safety. Tesla's occupancy networks predict pedestrian trajectories 3 seconds ahead through diffusion models, achieving 89% accuracy at 2-second horizon, critical for avoiding with jaywalkers. System reduced near-miss incidents 37% versus constant velocity prediction baselines. Video language integration enables natural interaction with visual content. Video clip extends clip to video text pairs, enabling zero-shot activity recognition. Flamingo employs perceiver resampler, compressing video frame to fixed-size representation fed to language model, enabling open-ended video QA. Assistive technology applications. Microsoft Seeing AI app answers questions about surroundings for visually impaired users. What denomination is this bill? Is the crosswalk signal showing walk symbol? With 92% accuracy through video language integration. Walmart smart shelves employ video QA, answering inventory queries. How many cereal boxes remain on shelf A3? Through camera feeds, reducing manual stock checks by 76%. These video understanding capabilities transform static perception into dynamic comprehension, enabling machines to not merely see what's but understand how entities move, interact, evolve, and will likely behave in near future, critical for applications from autonomous navigation to healthcare monitoring, where temporal dynamics carry essential meaning beyond single-frame snapshots. Vision language integration bridges visual perception and linguistic understanding, enabling systems to discern screens in natural language, answer questions about visual content, follow language instructions for manipulation, and generate images from textual descriptions. Clips contrastive pre-training creates joint embedding space where images and text descriptions map to similar vectors when semantically aligned. Trained on 400 million image, text, pairs scrape internet. Clip achieves zero-shot transfer to 30-plus classification tasks by using natural language as classifier. This is a photo of a dog. Real-world clip deployments demonstrate versatility. Content moderation. Pinterest employs clip filtering 500 million monthly uploads, identifying policy-violating content through natural languages, images containing weapons, without task-specific training, reducing moderation latency from hours to seconds. Robotic manipulation. Google's Seiken system combines clip with affordance prediction, enabling robots to execute novel commands. Pick up the red tool by grounding language in visual. Affordances without explicit object detect. Every tool variant achieving 83% success rate on unseen objects. Accessibility. Microsoft seeing AI employs clip describing complex scenes for visually impaired users. A woman in blue dress sitting at cafe table with coffee cup, achieving 89% description accuracy versus 72% for captioning-only models. Bootstrapped language image pre-training improves captioning quality through multimodal mixture of encoder-decoder architectures, capable of both image-text matching and caption generation within single model. Bootstrapping mechanism filters noisy web data during pre-training, improving caption relevance. E-commerce applications leverage Blip. Amazon employ generating product descriptions from images for 10 million SKUs lacking textual descriptions, increasing search relevance 22% and conversion rates 15% for visually searched items. System generates accurate descriptions like women's black leather ankle boots with side zipper and 2-inch heel from product images alone. Vision language generative capabilities enables image synthesis from text. Dole times E2 employs clip latent space diffusion, generating photorealistic images from textual descriptions. A teddy bear swimming in the ocean at sunset, by conditioning denoising process on text embeddings. Stable diffusion employs latent diffusion in compressed latent space, enabling real-time gen on consumer GPUs. Creative industry applications demonstrate generative vision language capabilities. Adobe Firefly integrates diffusion models into Creative Cloud, enabling designers to generate custom textures, expand image boundaries, and recolor objects through natural language, reducing asset creation time from days to minutes, maintaining brand consistency through style transfer. Pharmaceutical company in silico medicine uses diffusion models, generating novel molecular structures with desired binding properties, designing preclinical candidate for idiopathic pulmonary fibrosis in 18 months versus industry average for 0.5 years by generating structures conditioned on protein site descriptions. Multimodal large language models, MLLMs, integrate vision encoders with language decoders, enabling open-ended visual reasoning. LRVA, large language and vision assistant, employs clipfit encoder with Vicuna language model connected through projection layer, trained on 158K visual and following data, enabling complex visual QA, captioning, and reasoning. Real-world MLLM deployments include enterprise search. IBM Watson answers processes employee queries against internal knowledge bases, including diagrams and screenshots. What does this error code mean? With screenshot, extracting answers with 18% accuracy, reducing helpdesk tickets 37%. Education. Khan Academies Cannego Tutor employs MLLMs analyzing student-drawn diagrams, providing feedback on geometry proofs or circuit diagrams with pedagogical explanations. Medical imaging. Parthei's MLLM system analyzes pathologies, answering clinician questions. What is the mitotic count in this region? With evidence-grounded responses achieving 94% concordance with pathologists while reducing interpretation time 60%. Embodied vision language models ground language in physical interaction. RT2, Robotics Transformer 2, combines vision language with robotic action tokens, enabling robots to follow novel natural language commands, pick up the extinct animal, by grounding language in physical affordances. Trained on 1.2 million robot trajectories and 17 billion web-scale vision language pairs, achieving 67% success rate on novel tasks without task-specific training. World embodied VLM deployments include warehouse robotics. Amazon Sparrow robot employs RT2 variants, identifying and grasping novel objects through language descriptions. The cylindrical container with red label, achieving 92% success rate on deformable objects like clothing previously considered impossible for robots. Robotics. Tesla's Optimus prototype employs embodied VLMs following natural language instructions. Bring me the cold drink from the refrigerator, by grounding language in household object affordances and spatial relationships. These vision language integrations transform computer vision from isolated perception module into interface, enabling natural human-machine collaboration where language serves as intuitive control modality and vision provides grounding in physical reality, essential for embodied intelligence. Self-supervised visual representation learning eliminates dependence on manual annotations by constructing learning signals from data structure itself, transforming unlabeled images into rich feature representations through pretext tasks that capture semantic structure without human labels. Contrastive learning frameworks learn representations by maximizing agreement between differently augmented views of same image while minimizing agreement between views of different images. SimCLR employs random cropping, color distortion, and Gaussian blur augmentations, then optimizing info-NCE loss, encouraging proximity of positive pairs in embedding space. MoCo, momentum contrast, maintains dynamic dictionary of negative examples with momentum updated encoder enabling larger negative sets. Critical for stable training, BYOL, bootstrap your own latent, negative examples entirely through predictor network trained to match target network outputs with stop gradient preventing collapse. Real-world contrastive learning deployments include Robotics, NVIDIA's R3M, ResNet for robotic manipulation, employs contrastive learning on 1 million human video frames from Ego for data creating representations that transfer to robotic manipulation with 2x sample efficiency versus supervised pre-training. System enables robots to recognize objects and their affordances from internet videos without robot-specific training data. Medical imaging, Path AI employs MoCo pre-training on 1 million. Unlabeled pathology slide, fine-tuning on 10,000 labeled slides achieving 94% tumor detection accuracy versus 87% for ImageNet pre-training, demonstrating domain-specific self-supervision outperforms generic supervised pre-training when labeled data scarce. Masked image modeling predicts missing portions of input from visible context. MAE, autoencoders, randomly masks 75% of image patches then reconstructs them through VIT decoder learning holistic scene understanding. Data 2 VEC employs teacher-student framework where teacher generates targets from full input while student predicts targets from masked input. Agricultural applications leverage MAE. John Deere employs pre-training on 10 million unlabeled drone images of crops then fine-tuning on 50,000 labeled disease images achieving 92% disease detection accuracy with 10x less labeled data versus supervised training, critical for rare diseases where labeled examples scarce. System detects early blight in tomatoes 14 days before visible symptoms in targeted fungicide application reducing chemical usage 70%. Clustering-based approaches jointly learn representations and cluster assignments. Deep cluster iteratively clusters feature embeddings then uses cluster assignments as pseudo-labels for supervised learning, SWAV, swapping assignments between views, enforcing consistent between cluster assignments of differently augmented views without explicit clustering steps. Satellite imagery applications leverage clustering. Maxar Technologies employs SWAV pre-training on 100 million unlabeled satellite images discovering emergent clusters corresponding to land use types, urban, agricultural, forest, with elves. Fine-tuning on 10,000 labeled images achieves 89% land cover classification accuracy versus 82% for supervised pre-training, enabling rapid adaptation to new geographic regions with minimal labeled data. Video self-supervision extends these concepts to temporal domain. Video MAE masks 90% of tubes during pre-training forcing model to reconstruct motion dynamics from sparse observations. R3M employs temporal contrastive learning on human video datasets learning representations that capture action semantics and object affordances. Robotics applications leverage video self-supervision. Google's RT1 model pre-trains on 130,000 robot trajectories using masked action prediction then fine-tunes on 10,000 demonstrations achieving 74% success rate on novel tasks. System learns temporal dynamics of manipulation enabling generalization to unseen objects and tasks. Self-supervised learning's distinctive value emerges in data-scarce domains. Messaging where labeled data requires expert annotation. Satellite imagery where labeling requires domain specialists. Robotics where collecting labeled interaction data expensive and time-consuming. These approaches transform unlabeled data from unusable resource into fuel for representation learning, enabling vision systems to learn from internet-scale images, robot interaction logs, and video streams without prohibitive annotation costs while often outperforming supervised pre-training when fine-tuned on domain-specific tasks with limited labels. Robustness and safety in computer vision address vulnerabilities that could cause catastrophic failures in safety-critical applications. Adversarial example, distributional shift, occlusion, and sensor spoofing demanding defensive strategies beyond standard accuracy metrics. Adversarial examples reveal fragility to imperceptible perturbations. Adding 0.5% noise to pander image causes ResNet 50 to classify as given with 99.3% confidence. World attacks include adversarial patches on clothing causing person detectors to fail. or stickers on stop signs triggering misclassification as speed limit signs. Autonomous vehicles face particular vulnerability. Researchers demonstrated 3D printed adversarial modifications to toy cars causing Tesla's autopilot to misclassify as speed limit signs, adversarial headlights projecting patterns onto road surfaces causing lane detection failure. Defenses include adversarial training, exposing models to perturbed examples during training, randomized smoothing, adding noise during inference to create certified robustness regions, input transformations, denoising orders, removing perturbations before classification. Medical imaging systems employ adversarial training to resist perturbations that could cause misdiagnosis, reducing attack success rate from 92% to 8% while maintaining 94% clean accuracy critical for diagnostic reliability. Distributional shift causes chaotic failure when deployment environments differ from training distributions. Autonomous vehicles trained on California roads fail in snowy Michigan winters because snow changes visual appearance of lane markings and road surfaces. Medical AI trained on urban hospital data fails in rural clinics due to different patient demographics and imaging equipment. Solutions: domain randomization during training. NVIDIA's robot manipulation system trained in simulation with randomized lighting, textures, and object positions achieved 85% success rate on physical robots without real-world training. Test time adaptation adjusts model parameters during deployment using unlabeled test data, reducing error by 40%. Corrupted ImageNet benchmarks. Federated learning trains models across decentralized devices capturing diverse environments without centralizing data. Google Keyboard's board learns typing patterns across millions of devices, improving next word prediction accuracy 18% while preserving privacy. Occlusion and clutter challenge detection in dense scenes, pedestrians partially hidden behind vehicles, products stacked on retail shelves, surgical instruments overlapping in laparoscopic views. Solutions include a modal completion, predicting occluded object parts through learned shape priors, multi-view fusion, combining observations from multiple cameras to resolve ambiguities, temporal reasoning, tracking objects through occlusion periods using motion models. Waymo's perception system employs multi-hypothesis tracking, maintaining multiple possible trajectories during occlusions, then resolving ambiguity when object reappears, reducing tracking failures in dense urban traffic by 57%. Sensors attacks manipulate physical sensors, projecting fake LiDAR points to create phantom obstacles causing emergency braking, displaying adversarial images on digital billboards triggering misclassification, jamming GPS signals causing localization failure. Autonomous vehicle defenses include sensor fusion redundancy, cross-validating LiDAR and radar measurements to detect inconsistencies, anomaly detection on sensor streams identifying spoofing patterns, physical shielding and encryption for critical sensors. Tesla's vision-only approach avoids LiDAR spoofing vulnerability but faces camera-specific attacks. System employs temporal consistency checks, rejecting detect consistent across frames, reducing spoofing success rate 83%. Safety validation demands rigorous testing beyond average accuracy, edge case mining through generative models creating rare scenarios. Emergency vehicles with unusual configurations, construction zones with temporary signage, metamorphic testing of semantic preserving transformations to inputs verifying consistent outputs, formal verification proving safety properties for critical subsystems through reachability analysis. Waymo employs edge case mining, generating 100,000 plus rare scenarios through generative adversarial networks, then testing perception system responses, discovering failure modes like misclassifying stationary police car with flashing lights as non-obstacle, leading to model retraining. System now maintains 99.9999% safety-critical accuracy across 10 million miles of testing. These robustness strategies transform computer vision from fragile pattern recognizer into reliable perception system capable of operating safely in complex, adversarial real-world environments where failure carries severe consequences, essential for deployment in autonomous vehicles, medical diagnostics, and security-critical applications where trustworthiness determines adoption. Ethical dimensions of computer vision permeate development and deployment. Technical decisions about data selection, algorithm design, and system architecture carry profound societal consequences requiring proactive consideration rather than retrospective mitigation. Algorithmic bias manifests when training data reflects historical inequities or underrepresents demographic groups, facial recognition systems trained on light-skinned male faces demonstrated error rates up to 34% higher for dark-skinned women compared to light-skinned men, according to MIT Media Lab research, leading to wrongful arrests when deployed in law enforcement contexts. Gender Shades Project revealed commercial gender classifiers achieving 99.7% accuracy skinned males versus 65.3% for dark-skinned females, bias stemming from training datasets containing 77.5% male faces and 83.5% light-skinned faces. Mitigation strategies include balanced dataset collection. Microsoft's 2019 update to Face API incorporated 1 million images spanning skin tones and genders, reducing error disparity from 34% to 3.5%, adversarial debiasing, training networks to remove protected attribute information from representations while preserving task-relevant features, fairness-aware loss functions penalizing performance disparities across demographic subgroups. Care applications face bias challenges with life-or-death consequences. Stanford's CheXNet, trained predominantly on chest X-rays from North American hospitals, showed 11% lower pneumonia detection accuracy on images from Southeast Asian hospitals due to demographic and equipment differences. Solution required multi-institutional collaboration collecting 200,000 plus diverse images, reducing accuracy gap to 2.3%, critical for global deployment equity. Surveillance capitalism exploits computer vision for behavioral manipulation. Retail stores employ emotion recognition, analyzing shopper expressions to optimize product placement and pricing. Workplace monitoring systems track attention and fatigue through webcam analysis, raising labor rights concerns. Regulatory responses emerge. Illinois Biometric Information Privacy Act, BPAR, requires explicit consent for biometric data collection with $1,000 to $5,000 statutory damages per violation. EU's AI Act bans real-time biometric identification in public spaces except for narrowly defined law enforcement purposes. Proposed U.S. federal legislation would ban facial recognition in public housing and federally funded schools. Deepfake detection addresses synthetic media threats, manipulation artifacts in frequency domain, inconsistent head pose frequencies, physiological signal and inconsistent blinking patterns, pulse signals, temporal inconsistencies, unnatural mouth movements. Reality Defender platform employs multimodal detection, analyzing spatial, temporal, and physiological signals, achieving 96% deepfake detection accuracy across 100,000 plus synthetic videos deployed by news organizations and social media platforms, reducing deepfake spread 73% during 2024 election cycles. Environmental impact demands sustainable practices. Training large vision models consumes substantial energy. 6TL16 training on ImageNet required 1,800 kilowatt-hours, equivalent to U.S. household monthly consumption. Inference at scale compounds impact with billions of daily queries across platforms. Green vision initiatives address this through algorithmic efficiency, sparse models activating only relevant neurons per input, reducing computation 10x, hardware-aware training optimizing models for specific accelerators, carbon-aware computing scheduling training jobs during low-carbon grid periods. Accessibility considerations ensure vision technologies serve diverse populations. Screen readers for visually impaired users require accurate image captioning. Microsoft's Seeing AI app describes scenes, reads text, and identifies products through smartphone. Colorblind-friendly visualizations employ pattern redundancy alongside color coding. Sign language recognition systems enable communication access. Google's MediaPipe hands tracks hand movements in real time, enabling sign-to-text translation with 89% accuracy. Dual-use awareness recognizes beneficial technology and enable harm. Facial recognition aiding disaster victim identification in earthquake rubble or enabling mass surveillance suppressing political dissent. Drone vision enabling precision agriculture or conducting targeted surveillance without warrants. Medical imaging AI improving diagnostics or enabling insurance discrimination based on predicted health risks. Researchers bear responsibility considering plausible misuse scenarios and implementing mitigations. Capability restrictions limiting functionality in high-risk contexts, refusing to identify individuals without consent, access controls preventing malicious actors from obtaining powerful systems, transparency enabling detection of misuse through output working. These ethical dimensions aren't peripheral concerns addressed after technical development completes, they are foundational design parameters shaping data collection protocols, algorithm selection criteria, validation procedures, and deployment strategies from project inception. with engineers bearing professional responsibility to anticipate consequences, engage diverse stakeholders, and prioritize human dignity alongside technical performance metrics. Computer vision systems increasingly mediate human safety, privacy, and opportunity. Their design thus carries profound societal implications demanding ethical reflection woven into technical decisions rather than treated as afterthought. Slide 9, AI.706, Robotics. Robotics engineering transforms artificial intelligence from abstract algorithms into physical agents that perceive three-dimensional environments, navigate dynamic spaces, manipulate objects with dexterity, and interact safely with humans, grounding intelligence in the unforgiving points of Newtonian physics, material properties, sensor noise, and real-time computational demands. Unlike purely digital AI systems where failure typically means incorrect output without physical consequences, robotic systems operate in shared physical space where errors carry potential for property damage, injury, or loss of life, demanding rigorous safety engineering, fault detection mechanisms, and graceful degradation strategies absent in conventional software development. The field's foundational insight emerges from Rodney Brooks' 1990 subsumption architecture demonstration. Complex insect-like behaviors could emerge from layered reactive controllers without central world models, challenging the assumption that internal symbolic representation is necessary for intelligent action and establishing embodiment as a first principle of robotic intelligence. Modern robotics integrates this embodied perspective with sophisticated learning capabilities. Boston Dynamics' Atlas robot performing parkour and backflips demonstrates not merely athletic prowess but integration, whole-body control coordinating dozens of actuators under dynamic constraints, model predictive control anticipating contact forces milliseconds before impact, state estimation fusing inertial measurement units, joint encoders, and vision to maintain balance despite sensory latency, and learning frameworks transforming simulation experience into robust physical execution. These capabilities enable robots to operate in domains ranging from structured factory floors where FANUC's M2000 IA lifts 1,200 kilograms automotive frames with sub-millimeter precision, to unstructured disaster zones where Boston Dynamics Spot navigates collapsings detecting survivors through thermal signatures, to intimate human environments where intuitive surgical's Da Vinci system enables minimally invasive procedures with motion scaling filtering surgeon tremor to sub-millimeter precision. This spectrum, from industrial precision to field adaptability to surgical delicacy, reveals robotics' unifying, designing systems that maintain stability and purpose amid uncertainty, disturbance, and partial observability while respecting human safety and dignity. Robot components form the physical substrate enabling intelligent behavior, sensors transducing environmental phenomena into digital signals, actuators converting computational command into physical motion, and controllers orchestrating perception action loops with real-time guarantees. Proprioceptive sensors measure internal robot state, optical encoders on universal robots UR5E measure joint positions with 0.01 degrees resolution enabling precise path following, strain gauge-based force-torque sensor wrist detect contact forces as small as 0.1 and enabling delicate assembly tasks like inserting circuit boards without damaging pins. Current sensors infer motor torques through electrical measurements enabling collision detection without external sensors. UR5E stops within 15 milliseconds when unexpected resistance exceeds folds, critical for safe human-robot collaboration. Exteroceptive sensors measure external environment. Intel RealSense D for 55 depth cameras provide 1280 by 720 RGBD streams at 30 fps enabling real-time object recognition and grasp planning for warehouse robots. Velodyne Alpha Prime LiDAR 128 laser beams rotating at 20 Hz generating 2 point per million points. Second, enabling autonomous vehicles to detect pedestrians at 200-meter range regardless of lighting conditions. Tactile sensors like GelSight employ camera-based elastomer deformation measurement, achieving 10-micron spatial resolution, enabling robots to identify surface textures, rough concrete versus smooth metal, and detect slip events during manipulation 150 milliseconds before object drop. Actuation technologies determine force-speed trade-offs. Harmonic drive actuators in QCR LBR IWR provide zero backlash transmission with 1 to 100 reduction ratios enable millimeter positioning accuracy essential for aerospace component assembly. Series elastic actuators, SEAS, In Boston Dynamics, Atlas introduce intentional spring elements between motor and load, enabling precise force control and shock absorption during dynamic maneuvers like landing from jumps, pneumatic artificial muscles. In Shadow Robots, can provide compliance mimicking human musculature, enabling delicate interactions like peeling a banana without crushing the fruit. Control hardware bridges computation and physics. NVIDIA Jetson Orin delivers 275 TOPS processing sensor fusion, perception, and motion planning on mobile manipulators like Boston Dynamics Stretch. As instruments C2000 microcontrollers execute motor control loops at 20 kHz, ensuring stable torque regulation despite electrical noise. Safety-rated controllers like PILS PNO's multi-implement dual-channel monitoring with continuous self-tests, ensuring safe torque off, STO, within 10 milliseconds. When emergency stops activate. These components function not as isolated parts but as integrated systems. Warehouse robot perception pipelines fuse camera, LiDAR, and IMU data through Kalman filters, achieving 2 cm localization accuracy. Surgical robot control loops integrate force feedback with visual servoing, enabling tremor cancellation at 1 kHz rates. Legged robot state estimators combine proprioception with vision to maintain balance on slippery surfaces. Component selection thus represents critical engineering decision, balancing precision, speed, power, safety, and cost. Industrial arms prioritize repeatability, plus or minus 0.02 mils, over adaptability. Field robots prioritize robustness to environmental variation over peak performance. Collaborative robots prioritize inherent safety through mechanical compliance over raw speed. Kinematics provides the geometric foundation for robotic motion, mathematical description of position and orientation without considering forcing movement. Forward kinematics computes end effector pose given joint angles through homogeneous transformation matrices. Denevit-Hartenberg convention parameterizes serial chains with 4 parameters per joint: link length A, link twist, joint offset D, and joint angle. For a 6DOF industrial arm like FANUC 10IA, forward kinematics solves T equals T times T times T times T times T times T, where each T represents transformation between adjacent frames, enabling precise calculation that rotating joint 3 by 30 degrees moves end effector 17.3 cm along x-axis while maintaining orientation. Real-world calibration manufacturing tolerances. FANUC's IR calibration system measures actual kinematic parameters by observing tool positions at multiple configurations, then updates controller models, reducing positioning error from 2.1 mm to 0.3 mm, critical for automotive spot welding where electrode misalignment causes defective welds. Inverse kinematics solves the complementary challenge. Given desired end effector pose, what joint angles achieve it? Analytical solutions exist only for special structures. Pumer 560's spherical wrist enables decoupling position and orientation solutions, but most robots require numerical methods. And transpose methods move joints proportionally to error gradient, efficient but slow convergence, damped least squares. Levenberg-Marquardt adds regularization I to JJ, preventing singularities where small Cartesian motions require large joint motions. Resolved acceleration methods integrate dynamics for smoother trajectories. Redundant simulators, those with more degrees of freedom than task requirements, introduce null space, enabling secondary objectives. Franke-Emaker's PandaArm 7DOF, solving 6DOF task, position plus orientation, employs null space projection to simultaneously avoid joint limits, minimize energy consumption, maintain camera field of view on manipulated objects, critical for assembly tasks where visual feedback guides insertion operations. Mobile robot kinematics introduces non-holonomic constraints. Differential drive robots like iRobot Create cannot move laterally despite 2 actuated wheels. Kinematic model equals V times cosine theta equals V times sine theta equals omega. R reveals that lateral velocity equals times cosine theta times sine theta equals 0 always. Fundamental limitation requiring specialized planners like kinodynamic RRT that respect motion constraints. Legged locomotion faces richer challenges. Humanoid robots like Boston Dynamics Atlas change contact points during gait cycles, creating hybrid dynamics where kinematic chains reconfigure with each step. Whole body inverse kinematics simultaneously solves for arm, leg, and torso configurations, maintaining balance while reaching for objects, enabling Atlas to open doors whilst on one leg by coordinating 28 degrees of freedom through hierarchical task prioritization. Kinematic singularities represent critical failure modes. When Jacobian loses rank, small Cartesian motions require infinite joint velocities. Industrial arms exhibit wrist singularities when joints 4 and 6 align, unpredictable wrist rotations, elbow singularities when arm fully extended causing loss of radial motion capability. Mitigation strategies include singularity-robust inverse kinematics weighting joint motions to avoid singular configurations, path planning algorithms inserting intermediate waypoints circumventing singular regions, and hardware design KUKA's LBR IWA with 7 revolute joints eliminating wrist singularities through kinematic redundancy. These kinematic principles enable precise motion execution across domains. Surgical robots positioning instruments through 8 mm trocar ports with 0.5 mm accuracy, warehouse robots navigating 1-2 meter aisles between shelves with 2 cm clearance, planetary rovers like NASA's. Perseverance maneuvering over Martian terrain with 25 degrees slopes requiring precise will coordination to avoid tip-over. Dynamics extends kinematics by incorporating forces, torques, masses, and inertias governing how move under actuation and environmental interaction, essential for high-speed motion, contact-rich tasks, and energy-efficient operation. Newton-Euler formulation computes forces and torques recursively, outward pass from base to end effector calculating velocities and accelerations, inward pass computing forces and torques required to achieve those Lagrangian formulation derives equations of motion from energy principles. Kinetic energy T minus potential energy V yields Lagrangian L equals T, V, Euler-Lagrange equations d dt, del L, del Q, del L, del Q equals to produce differential equations relating joint accelerations to applied torques. Both approaches yield equations of form M, Q, Q plus C, Q, Q, Q plus G, Q, equals to where M, Q, represents configuration-dependent inertia matrix, C, Q, Q, captures Coriolis and centrifugal effects, G, Q, models gravity forces, and notes applied joint torques. These equations reveal critical properties, inertia matrix symmetry and positive definiteness enabling energy-based stability analysis, skew symmetry of 2C enabling passivity-based control designs, gravity vector structure informing compensation strategies. Dynamic modeling enables multiple capabilities, simulation for testing control strategies before physical deployment. NVIDIA IsaacSim simulates 10,000 warehouse robots simultaneously validating fleet coordination algorithms without hardware wear, model-based control achieving superior tracking performance through feed-forward compensation. QCR LBR IWA's impedance control lines computed torque feed-forward with force feedback enabling delicate assembly of fragile electronics. Trajectory optimization generating dynamically feasible motions respecting actuator limits. Boston Dynamics Atlas uses trajectory optimization to plan park-hour sequences ensuring joint torque limits never exceeded during flips. Contact Dynamics introduces discontinuities challenging traditional modeling. Rigid body assumption breaks down during impacts requiring impulsive formulations. Compliant contact models like Hunt-Crossley represent interactions through nonlinear springs, dampers enabling stable simulation of manipulation tasks. Hybrid dynamics frameworks switch between contact based on geometric conditions, essential for walking robots transitioning between single and double support phases. Whole body dynamics becomes essential for legged locomotion. Models incorporating full kinematic chains with multiple contact points require solving contact force distributions consistent with friction constraints and non-penetration conditions. Boston Dynamics Spot employs whole-body control optimizing contact forces across 4 legs to maintain balance on slippery surfaces. When front left foot slips on ice, controller redistributes forces to other 3 legs within 10 milliseconds preventing fall. Floating base dynamics addresses robots without fixed base. Manipulators like Boston Dynamics Stretch, aerial vehicles like DJI Matrice 300, humanoid robots like Tesla Optimus, where base motion couples with arm motions requiring augmented state representations including base pose and velocity. Parameter identification addresses practical challenge that theoretical dynamic models rarely match robots due to unmodeled friction, manufacturing tolerances, payload variations, and wear, requiring experimental procedures exciting robots across workspace while measuring joint torques and motions to estimate actual inertial parameters through least squares optimization. FANUC's payload identification routine has robot perform oscillations while measuring motor currents then computes mass, center of mass, an inertia tensor of attached tools, critical for accurate motion planning when switching between welding torches, 2.3 kilograms, and material handling grippers, 8.7 kilograms. Dynamics education progresses from single rigid body rotational through multilink serial chains through floating base systems with contacts, each stage revealing how physical embodiment constrains achievable motions and necessitates control strategies respecting dynamic feasibility while achieving task objectives under uncertainty. Sensors and perception systems provide robots connection to physical world, transforming raw measurements into coherent state estimates enabling environmental understanding and decision-making. Sensor fusion addresses fundamental challenge of combining heterogeneous, asynchronous, noisy measurements. Kalman filters optimally combine Gaussian distributed estimates under linear dynamics assumptions. Extended Kalman filters nonlinear systems around current estimate enabling application to robot localization. Unscented Kalman filters propagate sigma points through nonlinear functions capturing posterior distribution moments more accurately. Particle filters represent distributions through weighted samples enabling multimodal belief representation essential for globalization where multiple hypotheses exist simultaneously. Real-world implementations demonstrate fusion necessity. Autonomous vehicles require centimeter-level accuracy. Waymo's system fuses GPS, 2-meter accuracy, IMU, high frequency but drifting, wheel odometry, accurate short-term, and LiDAR precise but intermittent, through tightly coupled extended Kalman filter achieving 10 cm positioning accuracy critical for lane keeping. Warehouse robots face GPS-denied environments. Amazon's Proteus fuses 2D LiDAR, for wall detection, 3D LiDAR, 4 pallet recognition, and visual odometry through factor optimization. Google Cartographer, achieving 2 cm localization accuracy across million square foot facilities. Multisensor calibration establishes geometric and temporal relationships between sensor coordinate frames, hand-eye calibration determining transformation between camera and end effector frames through simultaneous motion observation. Lens method solves AX equals XB equation where A represents camera motion, B represents robot motion, X represents unknown transformation. Modern approaches employ mutual information maximization aligning intensity gradients across modalities. Industrial calibration exemplifies precision requirements. FANUC's 3D system calibrates stereo cameras to robot base with 0.1 mm accuracy enabling bin picking of randomly oriented parts. Recalibration triggered automatically when temperature changes exceed 5 degrees Celsius preventing thermal expansion-induced errors. Perception pipelines transform raw sensor data into task-relevant representations. Image processing extracting edges, corners, and regions. Feature matching establishing correspondences across views. Visual odometry estimating ego motion from image sequences. Simultaneous localization and mapping. SLAM, constructing environment maps while tracking robot pose within them. ORB, SLAM 3 achieves real ocular, stereo, and RGBD SLAM through 3-thread architecture. Tracking thread estimates camera pose against local map. Local mapping thread optimizes recent keyframes and points. Loop closing thread detects revisited locations correcting drift through pose graph optimization. Real-world SLAM deployments face environmental challenges. Construction sites. Boston Dynamics Spot employs stereo visual inertial odometry with loop closure detecting previously mapped areas despite changing conditions. Equipment movement, material delivery, agricultural fields. John Deere's autonomous tractor uses LiDAR inertial odometry with ground plane constraints achieving 5 cm across 1,000-acre fields despite GPS outages under tree lines. Underwater environments. Blue ROV2 employs acoustic inertial SLAM where Doppler velocity log provides velocity measurements enabling navigation where visual features scarce. Object detection and segmentation identify entities of interest. RCNN extends faster RCNN adding parallel branch predicting pixel-wise masks for each detected object. Amazon's warehouse robots use mask RCNN segmenting individual items on cluttered shelves distinguishing between identical SKU variants, different expiration dates, through fine-grained mask boundaries enabling processing with 96.7% success rate. Scene. Understanding infers spatial relationships and functional properties. Graph neural networks modeling object relationships. Chair near table implies dining context. Attention mechanisms weighting objects by contextual relevance. Stethoscope in hospital room. Stethoscope in gift shop. Tesla's vision system employs scene understanding, classifying road types, highway, residential, construction zone, then adjusting behavior predictions, pedestrians at crosswalks versus jaywalking in residential areas, reducing false positives in pedestrian detection by 38% compared to object-owned images. Perception challenges under real-world conditions demand specialized solutions. Domain shift between training and deployment environments. Autonomous vehicles encountering snow-covered roads where lane markings obscured. Solution employs domain randomization during training, exposing networks to synthetic snow, rain, and fog, reducing performance degradation from 42% to 8%. Partial observability where occlusions prevent complete scene understanding. Warehouse robots handling transparent containers. Requiring polarization imaging to detect contents invisible to standard RGB cameras. Real-time constraints demanding algorithm efficiency alongside accuracy. Mobile maneuvers requiring 30 FPS perception on 15W power budgets achieved through model compression, quantization to INT8, and hardware acceleration, TensorRT optimization. These perception capabilities transform raw sensor data into actionable understanding, enabling robots to navigate unknown environments, recognize objects despite variation, and interact with physical world through informed decision-making grounded in sensory evidence rather than pre-programmed behaviors. Motion planning addresses the challenge of generating collision-free trajectories, connecting initial and goal configurations while respecting kinematic and dynamic constraints, transforming high-level task specifications into executable motion sequences. Configuration space representation transforms planning problem, representing robot as point moving through space where obstacles correspond to configurations causing collision. For manipulators with n degrees of freedom, configuration space becomes n-dimensional manifold, visualizable beyond 3 dimensions, but mathematical properties govern planning complexity. Sampling-based planners dominate high-dimensional problems. Probabilistic roadmap, PRM, constructs graph by sampling collision-free configurations and connecting neighbors, then searches graph for path. Rapidly exploring random tree, RRT, incrementals tree toward unexplored regions, enabling efficient exploration of large configuration spaces. RRT* extends RRT with rewiring operations asymptotically converging to optimal paths. Kinodynamic planners incorporate dynamics constraints directly into sampling process, generating dynamically feasible trajectories rather than geometric paths later smoothed into dynamic feasibility. Real-world implementations demonstrate planner selection criteria. Industrial arms, FANUCs are 2000 IB employs optimization-based trajectory planning, generating minimum jerk trajectories respecting joint velocity, acceleration limits, achieving cycle times 18% faster than traditional trapezoidal profiles while reducing mechanical wear. Warehouse robots. Amazon's Kiva robots use prioritized multi-agent pathfinding where each robot plans individual path then resolves conflicts through velocity adjustment, avoiding deadlocks in 10,000 robot fleets. Leggard locomotion. Boston Dynamics employs model predictive control with embedded motion planning, generating foothold sequences 2 seconds ahead, adapting to terrain irregularities detected through stereo vision. Optimization-based planners formulate planning as constrained optimization. CHOMP, covariant Hamiltonian optimization for motion planning, optimizes trajectories through gradient on cost landscapes, penalizing collisions and joint limits. STOMP, stochastic trajectory optimization for motion planning, employs stochastic optimization avoiding local minima through noise injection. TrajOpt formulates planning as sequential convex optimization, enabling efficient solution of complex constraints. Surgical leverage optimization-based planning. Intuitive Surgical's Da Vinci system generates collision-free instrument paths through patient anatomy using preoperative CT scans to define no-fly zones around critical structures, nerves, blood vessels, reducing surgical complications 27% versus manual planning. Multi-robot planning coordination challenges. Prioritized planning sequencing robots to avoid deadlock works for small fleets but scales poorly. Coupled planning treating joint configuration space of all robots suffers exponential dimensionality growth. Decoupled planning individual paths then resolving conflicts through velocity tuning or local replanning enables scale hundreds of robots as demonstrated by Amazon's warehouse operations. Deformable object manipulation planning addresses non-rigid bodies, rope manipulation, cloth folding, cable insertion, requiring models of material properties and contact mechanics absent in rigid body planning. Tesla's battery pack assembly employs programmable object planning, threading flexible busbars through tight spaces. System models busbar elasticity through mass spring systems, then plans insertion trajectories avoiding plastic deformation that would cause electrical failure. Uncertainty-aware planning incorporates perception uncertainty, belief space planning maintaining distributions over states rather than estimates, conformant planning generating sequences guaranteed to succeed despite uncertainty, contingent planning. Branching based on sensor observations during execution. Search and rescue robots employ uncertainty-aware planning. Boston Dynamics spot navigating collapsed buildings maintains belief distribution over terrain traversability. Unlimited sensor data then plans paths maximizing information gain while minimizing risk, reducing mission failure rate 43% compared to deterministic planners. Real-time replanning addresses dynamic environments. D*light incrementally repairing paths as environment changes. Elastic bands maintaining virtual forces pulling paths goal while repelling from newly discovered obstacles. Trajectory libraries enabling rapid switching between precomputed motion primitives. Autonomous vehicles require millisecond replanning. Tesla's autopilot maintains library of 50 trajectory primitives, lane changes, merges, emergency stops, then selects optimal primitive real-time perception reducing planning latency to 15 milliseconds critical for highway speed collision avoidance. Motion planning thus functions not as isolated algorithm but as integrated component within perception planning control loop, receiving updated environment models from perception, generating feasible trajectories respecting dynamics, and providing this to controllers while continuously adapting to environmental changes and execution errors. Manipulation capabilities enable robots to physically transform environments through object grasping, tool use, and forceful interaction, representing one of robotics' most challenging frontiers due to contact-rich dynamics, partial observability, and material variability. Grasp synthesis addresses fundamental challenge, determining contact points and forces enabling stable object acquisition and manipulation. Force closure analysis determines whether contact wrenches span six-dimensional wrench space enabling resistance to arbitrary external forces and torques, necessary condition for secure grasping. Form closure provides stronger guarantee where contacts prevent any motion even without friction, rarely achievable in practice but theoretically important. Grasp quality metrics quantify stability, Ferraricani metric measuring volume of achievable wrench space, epsilon quality measuring maximum disturbance wrench magnitude, alignment metrics evaluating correspondence between grasp wrench space and expected task wrenches. Analytical grasp synthesis solves for optimal contacts given object geometry, efficient for simple shapes like polyhedra but intractable for complex geometries. Data-driven approaches learn grasp success from experience, convolutional neural networks processing depth images to predict grasp rectangles, reinforcement learning policies discovering successful grasping strategies through trial and error, generative models synthesizing diverse successful grasps for novel objects. Real-world implementations demonstrate grasp synthesis evolution. Industrial bin picking. FANUC's IR vision system combines analytical grasp planning for known parts with deep learning for novel objects achieving 99.2% success rate on 10,000+ SKUs in automotive plants. Warehouse automation. Amazon Sparrow robot employs reinforcement learning trained in simulation on alien object grasps then transferred to physical robot achieving 92% success rate on deformable objects, clothing, bags. Previously considered impossible for robots, surgical robotics. Intuitive Surgical's Da Vinci system employs model predictive grasp planning ensuring instrument tips maintain optimal tissue interaction for 0.5 to 2.0 n, preventing slippage or tissue damage during suturing. Dexterous manipulation extends beyond simple pick-and-place to in-hand repositioning, rolling objects between fingers, pivoting against surfaces, sliding along constraints. Shadow Robot's dexterous hand achieves human-level dexterity 20 degrees of freedom and tactile sensing, performing tasks like shuffling cards, turning pages, and assembling small mechanisms requiring coordinated finger motions. Non-prehensile manipulation exploits environmental constraints rather than full enclosure, pushing objects across surfaces, batting objects through air, caging objects in partial constraints. MIT's push grasping system combines pushing to reorient objects then grasping achieving 94% success rate on cluttered tables where direct grasping fails 68% of time. Tool use represents pinnacle of manipulation capability, recognizing objects as tools, understanding their affordance, and employing them to extend robot capabilities beyond direct manipulation. Boston Dynamics Atlas employs tool use in disaster response scenarios, recognizing fire extinguisher as tool, understanding its affordance, grip handle, press lever, then using it to suppress simulated fires. System learns tool affordances through supervised exploration, achieving 83% success rate on novel tools after 500 interaction episodes. Dynamic manipulation exploits momentum and impacts, juggling objects, throwing and catching, striking objects to desired locations, requiring precise timing and dynamic models. Toyota's human support robots 3 balls continuously through model predictive control, predicting ball trajectories 500 milliseconds ahead, then planning hand motions to intercept, demonstrating dynamic manipulation capabilities essential for tasks like catching falling objects before they break. Manipulation under uncertainty addresses partial observability, servoing using force feedback to guide insertion tasks when vision obscured, slip detection and recovery using tactile sensors to maintain grasp integrity, exploratory manipulation actively gathering information through interaction to resolve ambiguity. Surgical robots employ tactile servoing during needle insertion, force torque sensors detect resistance changes indicating needle penetration depth, enabling precise suturing without visual feedback when blood obscures view. Bimanual manipulation coordinates 2 arms for complex tasks, holding objects stable while manipulating with other hand, assembling parts requiring simultaneous constraint satisfaction, leveraging environmental fixtures. ABB's Yumi robot performs bimanual assembly of consumer electronics, left arm holds circuit board stable while right arm inserts components with 0.1 mm precision. System employs coordinated motion planning, ensuring arms avoid self-collision while maintaining task constraints. Human-robot manipulation shares tasks between agents, predicting human intent from motion cues, adapting robot behavior to complement human actions, negotiating role allocation dynamically during task execution. BMW's assembly lines employ collaborative robots handing tools to human workers. Robot predicts when worker will need next tool through analysis, then positions tool within ergonomic reach zone, reducing worker fatigue 34% while maintaining 45-second assembly cycle times. Manipulation planning integrates grasp selection, motion planning, and task sequencing, determining not just how to grasp object but when during task sequence, whether regrasping necessary for sub-operations, and how manipulation actions affect environment state for future steps. Tesla's battery module assembly employs integrated manipulation planning, system plans sequence of grasps, insertions, and fastening operations, ensuring tools access fastening points without collision while maintaining part alignment within 0.2 mm, critical for electrical performance. These manipulation capabilities transform robots from passive movers into active transformers of physical environments, enabling assembly, disassembly, repair, and creative construction tasks requiring dexterity, adaptability, and physical reasoning previously exclusive to humans. Locomotion capabilities enable mobile robots to traverse diverse terrains, from structured indoor environments with flat floors and right-angle geometry through semi-structured outdoor spaces with slopes, steps, and vegetation through unstructured natural environments with mud, water, and unstable substrates. Wheeled locomotion dominates structured environments, differential drive robots achieving simplicity and efficiency on flat surfaces but lacking lateral mobility, Ackermann steering enabling car-like motion with coordinated wheel angles essential for highway-speed autonomous vehicles, omnidirectional wheels, Mechanism, Swedish, providing holonomic motion capabilities at cost of mechanical complexity and reduced traction. Tesla's Optimus prototype employs omnidirectional wheels for facility navigation. Mechanism wheels enable lateral movement essential for tight workspace maneuvering while maintaining 5 km/h top speed for facility traversal. Tracked locomotion improves mobility on soft or uneven terrain, distributing weight over larger contact area, reducing ground pressure, conforming to surface irregularities through articulated track segments. Boston Dynamics handle robot combines wheels with legs, wheels for efficient flat ground travel, legs for stair climbing, achieving 8-hour operational endurance while navigating multi-story facilities. Locomotion achieves unparalleled terrain adaptability, bipedal walking mimicking human mobility, enabling navigation of human-designed environments but demanding sophisticated balance control, quadrupedal locomotion providing inherent stability through multiple support points while maintaining agility. hexapodal and multi-legged designs achieving static stability even jig replacement but sacrificing speed and efficiency. Boston Dynamics Spot quadruped demonstrates legged locomotion capabilities, traversing construction sites with 35 degrees slopes, stepping over 40 centimeters gaps, and maintaining balance on slippery surfaces through real-time gait adaptation. System employs model predictive adjusting footholds 20 milliseconds before footfall based on terrain sensing, reducing falls 76% compared to pre-planned gaits. Dynamic versus static stability defines fundamental locomotion paradigm. Statically stable gaits maintaining projection of center of mass within support polygon at all times, enabling slow but robust locomotion. Dynamically stable gaits allowing center of mass to leave support polygon temporarily, relying on momentum and active control to recover balance, enabling running, hopping, and other agile behaviors at cost of control complexity. MIT's Cheetah robot achieves 14 km/h running speed through dynamically stable bounding gait, touchdown timing precisely controlled to maintain energy-efficient periodic motion while rejecting disturbances through impedance control. Gait generation addresses rhythmic coordination patterns, central pattern generators, CPGs, inspired by biological neural circuits producing rhythmic outputs without rhythmic inputs, trajectory optimization generating dynamically consistent footholds and body motions, model predictive control adjusting gait parameters online based on terrain sensing. Robotics Wymel quadruped employs CPG-based gait generation with sensory feedback modulation. CPG produces baseline trotting pattern while foot contact sensors modulate phase to terrain irregularities enabling 3 km/h walking speed across rocky trails. Terrain perception and adaptation enables locomotion across variable environments, stereo vision or LiDAR identifying traversable regions, geometric analysis classifying surfaces by slope, roughness, and compliance, learning-based approaches predict hold quality from visual appearance, reactive adaptation adjusting step timing and placement based on unexpected contact forces. NASA's Perseverance rover employs terrain-adaptive locomotion on Mars. Stereo cameras identify safe paths avoiding rocks larger than 15 centimeters. Visual odometry detects wool slippage. Triggering gait adjustment. Autonomous navigation software, AutoNav, plans 100-meter traverses without Earth intervention increasing daily travel distance for X versus manual driving. Whole-body locomotion integrates base motion with arm motions, using arms for balance during challenging maneuvers, employing arms as additional points during climbing, coordinating manipulation and locomotion for mobile manipulation tasks. Boston Dynamics Atlas performs park hour through whole-body locomotion, arms swing to counteract angular momentum during jumps, hands contact walls for redirection during flips, system coordinates 28 degrees of freedom through hierarchical control at human-level agility. Aerial locomotion addresses flight dynamics, multirotor drones achieving simplicity and maneuverability through differential thrust control but limited endurance, fixed-wing aircraft providing efficient long-range travel but requiring runways or complex launch, recovery, hybrid designs combining vertical takeoff with efficient flight. Zipline's medical delivery drones employ fixed-wing design with vertical takeoff, landing, achieving 160 km range delivering blood and vaccines to remote Rwandan villages. System transitions from vertical hover to forward flight in 10 seconds enabling runway-independent operation with aircraft efficiency. Locomotion confronts fluid dynamics challenges, underwater vehicles navigating three-dimensional environments with buoyancy control, surface vessels dealing with wave disturbances and limited maneuverability, biomimetic designs emulating fish, jellyfish, or other aquatic organisms for efficiency or stealth. Boston Engineering's Ghost Swim biomimetic propulsion, undulating foil mimicking bluefin tuna achieving 4.5 knot speed with 60% less energy than propeller-driven vehicles, system used by U.S. Navy for covert harbor inspection where quiet operation essential. Locomotion education progresses from wheeled navigation in structured environments through legged walking on frame through dynamic running and jumping through multimodal locomotion combining different strategies, each stage revealing how environmental interaction complexity demands increasingly sophisticated perception, planning, and control integration where locomotion becomes not merely transportation but embodied interaction with physical world. Human-robot physical demands specialized engineering considerations absent in purely autonomous operation, safety standards, inherent safety through design, active safety systems, shared control architectures, physical collaboration strategies, trust calibration, and physical ergonomics. Safety standards provide regulatory foundation. ISO ES 15066 specifying force and pressure limits for collaborative robot applications based on human injury biomechanics. Table A.1 defines maximum allowable forces for different body regions, e.g., 140 N for hand contact during quasi-static interaction, 460 N during transient contact. ISO 0218 establishing safety requirements for industrial robot systems including safeguarded spaces and emergency stop requirements. Universal Robots UR5E achieves ISO TS 15066 compliance through force torque sensing at wrist and base. System continuously monitors interaction forces stopping with 15 milliseconds when thresholds exceeded. This enables cage-free operation alongside humans in automotive assembly lines where robots handle heavy components, up to 5 kilograms, while humans perform dexterous tasks. Inherent safety through design addresses risk reduction at source. Series elastic actuators limiting peak forces through compliance. Franca Emiker's Pander arm employs Cs with 15 Nm per m stiffness enabling safe physical interaction while maintaining 0.1 mm positioning accuracy, rounded edges and smooth surfaces minimizing injury potential during contact. Lightweight materials reducing kinetic energy during unexpected collisions. Rethink Robotics used lightweight arms, 4.5 kilograms each, reducing collision energy 70% versus industrial arms. Active safety systems detect and respond to interaction events. Tactile skins covering robot surfaces detecting contact location and force magnitude. Optoforce HEX 70 sensor provides 100 Hz force mapping over 150 square centimeters enabling precise contact localization. Vision systems monitoring human proximity and predicting trajectories. Emergency stop mechanisms triggered by excessive forces or unexpected contacts. BMW's collaborative assembly cells employ multilayer safety. Time-of-flight cameras detect humans within 3-meter safety zone triggering speed reduction. Tactile skin on robot arms detects contact location enabling localized stopping rather than full system halt. Safety-rated monitored stop maintains robot position without power loss during brief human interventions. Shared control architectures distribute OI between human and robot. Bilateral teleoperation transmitting forces between operator and robot enabling haptic feedback. Da Vinci surgical system provides 3D visualization and motion scaling while surgeon maintains complete control authority. Admittance control mapping human applied forces to robot motion. QCR LBR IWAS hand guiding enables intuitive programming where human physically moves arm through desired motions which system records and reproduces. Virtual fixtures creating forbidden regions or guiding constraints overlaid on physical environment. Johns Hopkins SteadyHand robot employs virtual fixtures during retinal surgery preventing instrument movement beyond 100 boundaries protecting delicate tissue. Physical collaboration strategies enable joint task execution. Hand-over-hand teaching where human physically guides robot through desired motions which robot records and reproduces. Co-manipulation where human and robot simultaneously grasp and move objects requiring force coordination. Assembly tasks where positions parts precisely while human performs fine manipulation or fastening operations. Airbus employs human-robot co-manipulation in aircraft assembly. Humans and robots jointly position 12-meter wing spars with sub-millimeter alignment accuracy. Robot provides strength and precision while human provides adaptability to unexpected fittions reducing assembly time 50%. Trust calibration addresses psychological dimension of physical interaction, predictable motion profiles building operator confidence, transparent intention signaling through motion previews or visual indicators, appropriate responsiveness to human inputs avoiding both sluggishness and hyperactivity, recovery behaviors after errors demonstrating competence and reliability. Toyota's human support robot builds trust through predictable behavior, motion smoothing algorithms eliminating jerky movements, LED indicators showing current state, idle, moving, waiting, graceful error recovery where robot stops smoothly then human assistance rather than freezing unexpectedly. Physical ergonomics ensures interaction supports human capabilities rather than causing fatigue or injury, minimizing required human forces through robotic assistance, positioning interaction zones within comfortable human reach envelopes, timing robot actions to complement rather than interrupt human workflows, adapting assistance level based on human fatigue indicators. Ford's collaborative assembly lines employ ergonomics-driven robot design. Robots lift heavy components, up to 15 kilograms, to ergonomic height, waist level, reducing worker shoulder strain 63%, system times component presentation to match human assembly, eliminating waiting periods, force torque sensors detect worker fatigue through motion analysis then increase assistance level proactively. These interaction capabilities transform robots from isolated automation into collaborative partners, extending human capabilities while respecting physical and cognitive limitations, enabling new workflows where robots leverage complementary strengths rather than competing for tasks. Robotics software architecture addresses challenge of integrating diverse components, perception, planning, control, communication, into coherent, maintainable systems operating under real-time constraints. Middleware platforms provide communication structure, ROS, robot operating system, establishing de facto standard with publish-subscribe messaging, service calls, parameter server, an extensive package ecosystem, ROS2 addressing real-time performance and security limitations of original ROS through DDS, data distribution service, communication layer and hard real-time guarantees essential for safety-critical applications, YARP, yet another robot platform, emphasizing real-time performance for humanoid robotics, LCM, lightweight communications and marshalling, optimizing for low latency, high bandwidth applications like drone swarms. Boston Dynamics and custom middleware for Atlas Robot, hard real-time control loops, 1 kHz, implemented in C++ with deterministic scheduling, perception modules, 30 Hz, in Python with ROS-like messaging, safety monitors running on separate processor with watchdog timers ensuring fail-safe behavior within 10 milliseconds. Model structure software modularity, nodes in ROS representing executable processes with well-defined interfaces, behaviors in behavior trees providing composable action representations with built-in error handling, skills in skill-based architectures encapsulating parameterized action sequences with preconditions and effects. Amazon's robots employ behavior tree architecture, root node sequences high-level tasks, navigate to shelf, identify item, grasp item, transport to packing station, fallback nodes handle failures, if grasp fails, retry with different approach angle, parallel nodes execute independent actions simultaneously, navigation while battery level. Real-time considerations demand special attention, hard real-time requirements guaranteeing task completion within strict deadlines essential for low-level control loops. Motor control at 1 kHz requires less than 1 millisecond latency, soft real-time requirements allowing occasional deadline misses for perception or planning components, priority-based scheduling ensuring critical tasks preempt less critical ones, memory management avoiding garbage collection pauses during time-sensitive operations. NVIDIA Isaac SDK addresses real-time constraints, CUDA accelerated perception modules achieving 30 FPS on Jetson AGX, deterministic control loops with bound execution time, lock-free data structures preventing priority inversion. Fault tolerance mechanisms maintain operation despite component failures, heartbeat monitoring detecting unresponsive components, redundancy strategies employing multiple sensors or actuators with voting schemes, graceful degradation reducing capabilities while maintaining safety when full functionality unavailable, recovery procedures returning system to nominal state after transient faults. NASA's Perseverance rover employs triple modular redundancy, 3 identical computers voting on critical decisions. If one disagrees, it's powered off and diagnostics run during next communication window with Earth. System maintains full functionality after radiation-induced bit flip corrupted one computer's memory in 2021. Testing and validation strategies address physical deployment risks, simulation environments like Gazebo, PyBullet, or NVIDIA Isaac Sim enabling extensive testing without hardware wear or safety risks, hardware-in-the-loop testing integrating components with simulated environments, replay debugging recording sensor data during operation for offline analysis and reproduction of failures, formal verification proving safety properties through model checking or theorem proving for critical subsystems. Boston Dynamics validates SPOT through multistage testing, simulation 10,000 plus terrain scenarios, hardware-in-the-loop testing motor controllers with simulated dynamics, physical testing in controlled environments, obstacle courses, stairs, slopes, field testing in representative environments, construction sites, warehouses, with safety spotters. Architecture education progresses from single-process monolithic designs through modular component architectures through distributed real-time systems, each stage revealing how software complexity grows combinatorially with robot capabilities and demanding disciplined engineering practices to maintain reliability and maintainability while enabling rapid iteration and deployment. Robotics applications span domains transforming industries through physical embodiment of intelligence, manufacturing achieving precision and consistency impossible for humans alone, healthcare extending surgeon capabilities while reducing invasiveness, logistics automating material handling at unprecedented scale, agriculture optimizing resource usage through precision operations, disaster response extending human reach into hazardous environments. Industrial robotics dominates structured environments. FANUC's M. 2000 IA lifts 1,200 kg automotive frames with plus or minus 0.3 mm repeatability enabling precise spot. ABB's IRB 6700 performs aircraft wing assembly with 0.15 mm accuracy drilling 3,000 holes per wing without human intervention. Collaborative robots like Universal Robots UR10E work alongside humans in electronics assembly handling delicate components while humans perform quality inspection. Increase productivity 30% while reducing ergonomic injuries 45%. Surgical robotics enhances rather than replaces surgeon capabilities. Intuitive Surgical's Da Vinci system provides wristed instruments with 7 degrees of freedom enabling maneuvers impossible with human hands alone. 3D high-definition visualization revealing anatomical structures with enhanced clarity, motion scaling filtering physiological tremor to sub-millimeter precision. System performed over 1 million procedures in 2022 including prostatectomies with 50% less blood loss and 20% shorter. Hospital stays versus open surgery. Emerging capabilities include haptic feedback tactile sensation lost in conventional teleoperation through force sensors and vibrotactile displays, augmented reality overlays fusing preoperative scans with real-time endoscopic views highlighting tumor margins invisible to naked eye. Logistics and warehousing automation achieves unprecedented scale. Amazon 750/00 plus mobile robots transport shelves in fulfillment centers reducing order processing time from 60 to 75 minutes to 15 minutes. Boston Dynamics stretch unloads trailers at 800 cases, hour matching human speed while operating 20 hours per day. Autonomous forklifts from Seagrid navigate dynamic warehouse environments avoiding pedestrians and with 99.97% collision-free operation across 5 million hours of operation. Agricultural robotics confronts unstructured outdoor environments. John Deere's fully autonomous tractor navigates fields using GPS and computer vision performing tillage operations with 2.5 cm accuracy. Blue River Technologies see and spray identifies weeds among crops through real-time computer vision enabling precision herbicide application reducing chemical usage 90% while maintaining 99.2% weed control efficacy across 10 million acres annually. Harvest CROO robotics strawberry harvester uses computer vision to identify ripe fruit, soft grippers to pick without damage achieving 95% success rate versus 70% for human pickers while addressing labor shortages. Disaster response and hazardous environment applications extend human capabilities where direct presence proves too dangerous. Boston Dynamics Spot navigates collapsed structures inaccessible to humans detecting through thermal signatures and CO2 sensors. Snake-like robots from Carnegie Mellon thread through narrow voids in rubble piles delivering supplies or communication devices. Underwater robots like Ocean 1K explore shipwrecks at 500-meter depths where human divers cannot operate. Nuclear decommissioning robots like Boston Dynamics with radiation-hardened sensors map contamination levels in Fukushima Daiichi reactor buildings reducing human exposure. Field robotics confronts unique challenges of unstructured, unpredictable environments. Environmental variability introducing perception challenges, lighting changes, weather conditions, seasonal variations, communication constraints affecting remote operations, limited bandwidth, intermittent connectivity, latency, power constraints dictating operational duration, battery energy density limiting mission length, navigation without infrastructure demanding robust localization, GPS denied. Environments requiring alternative approaches. Perseverance rover exemplifies field robotics challenges, operating 225 million kilometers from Earth with 20-minute communication delays requiring autonomous navigation, surviving -100 degrees Celsius Martian nights through radioisotope thermoelectric generator. Traversing rocky terrain with autonomous hazard avoidance, increasing daily distance for X versus manual driving. Social robotics addresses human-centered applications. SoftBank's Pepper engaging customers in retail environments with expressive displays and conversational interfaces, increasing dwell time 27%. Morshi robot from Diligent Robotics assisting nurses in hospitals delivering and retrieving equipment, freeing 30% of nurse time for direct patient care. Companion robots like LQ providing social interaction for elderly, reducing loneliness metrics 22% in clinical trials. These applications share common success factors: rigorous safety engineering with multiple redundant layers, human-centered design respecting user policies and expectations, robustness to environmental variation through adaptive perception and control, economic viability demonstrating clear return on investment, ethical deployment with transparency about capabilities and limitations. Failures occur when these factors neglected. Nightscope security robots falling into fountains due to poor terrain perception. Delivery robots blocking wheelchair access due to inadequate path planning. Surgical robots causing injuries when safety systems bypassed, highlighting necessity of systems engineering perspective where hardware, software, environment, and human factors integrate into cohesive solutions respecting physical constraints and human dignity. Robotics thus functions as powerful tool requiring responsible engineering practices, safety validation, human oversight, continuous monitoring, and ethical reflection, to deliver societal benefit while minimizing harm across domains where physical embodiment creates both extraordinary capabilities and profound responsibilities. Slide 10, AI.707, Reinforcement Learning. Reinforcement learning represents a paradigm shift in artificial intelligence, moving beyond supervised pattern recognition to sequential decision-making under uncertainty, where agents learn optimal behaviors through environmental interaction rather than labeled examples. Supervised learning's input-output mapping. Reinforcement learning agents discover policies mapping states to actions by receiving scalar rewards that signal desirability without specifying correct actions, mimicking how humans and animals learn through trial, error, and delayed consequences. The fundamental framework formalizes this process through decision processes, MDPs, environments modeled as sets of states S representing observable conditions, robot joint angles, game board configurations, traffic scenarios, actions A available to the agent, motor torques, chess moves, steering commands, transition dynamics P, SS, A, specifying probability, state given current state and action, reward function R, S, A, S, quantifying immediate desirability of transitions, and discount factor set membership symbol, 0, 1, weighting future versus immediate rewards to ensure finite returns in infinite horizon problems. Policies Pi, AS, fine agent behavior, deterministic mappings A equals Pi, S, or stochastic distributions over actions, while value functions quantify long-term desirability. State value V caret Pi, S, represents expected cumulative discounted reward starting from state S and following policy Pi thereafter. Action value Q caret Pi, A, represents expected cumulative reward starting from state S, taking action A, then following Pi. Bellman equations express recursive relationships between values at successive time steps. V caret Pi, S, equals, AS, P, SS, A, R, S, A, S, plus V Pi, S, enabling dynamic programming algorithms like value iteration and policy iteration that compute optimal policies through iterative application of Bellman optimality equations. Real-world illustration emerges in elevator dispatch systems. States encode elevator positions, passenger requests, and traffic patterns, select destination floors, rewards penalize waiting times and energy consumption. Optimal policies learned through reinforcement learning reduce average wait times 28% compared to rule-based systems in high-rise buildings like Shanghai Tower by anticipating demand patterns and positioning elevators proactively during peak hours. Temporal differing bridges dynamic programming's model requirements with Monte Carlo's sample-based approach, updating value estimates toward observed rewards plus discounted estimates of subsequent states without waiting for episode termination. TD, 0, updates state values through VS plus alpha, R plus V, S, VS, alpha represents learning rate and delta equals R plus V, S, VS denotes temporal difference error. SASR, state action reward state action, extends this to action values with on-policy updates Q, S, A, Q, S, A, plus alpha, R plus Q, S, A, Q, S, where A sampled from current policy, maintaining expiration during learning essential for safety-critical domains. Q learning employs off-policy updates Q, S, A, Q, S, A, plus alpha, R plus max Q, S, A, Q, S, A, enabling learning optimal policies while following behavior, critical for sample efficiency but introducing maximization bias where overestimated Q values propagate through updates. Double Q learning addresses this through decoupled action selection and evaluation, using one Q network to select max Q, S, A, and another to evaluate Q, S, arg max Q, S, reducing overestimation bias by 42% in Atari benchmarks. Real-world deployment illustrates algorithm selection trade-offs. Warehouse robot navigation. Amazon's Kiva robots employ SASA for path planning, ensuring conservative behavior during learning, never taking unexplored shortcuts through human workspaces, while into optimal paths. Financial trading systems. Renaissance Technologies Medallion Fund employs Q-learning variants for order execution, learning optimal timing strategies through market interaction while maintaining expiration to adapt to regime changes. These applications reveal that algorithm choice depends not merely on asymptotic optimality but safety constraints during learning, expiration requirements, and environmental stationarity. Function approximation extends tabular methods to large or continuous state spaces, replacing lookup tables with parameterized functions like linear approximators, decision trees, or neural networks, enabling generalization across similar states. The mountain car problem exemplifies necessity. Car must drive up steep hill but lacks power for direct ascent. Optimal strategy involves building momentum by oscillating in valley then accelerating up opposite slope. Tabular methods fail with continuous state space, position, velocity, linear function approximation with tile coding discrete space into overlapping grids, enabling generalization. Agent learns policy after 1000 episodes versus infinite episodes required for tabular approach. Deep Q networks, DQNs, revolutionized function approximation through three critical innovations: experience replay, storing transitions, S, A, R, S, in buffer, then sampling mini-batches, breaking temporal correlations and enabling stable gradient descent. Target networks, maintaining separate Q network for bootstrapping targets updated periodically, preventing feedback loops causing divergence. Reward clipping, bounding rewards to -1, stabilizing learning across diverse environments. 2015 DQN achieved superhuman performance on 49 Atari games, learning directly from pixels, mastering Pong through precise paddle positioning, Breakout through strategic brick targeting, creating tunnels, and Space Invaders through anticipatory movement, without game-specific modifications. Real-world applications demonstrate DQ versatility. Data center cooling optimization. Google employed DQN controlling cooling systems across multiple facilities, learning policies that reduced energy consumption 40% by dynamically adjusting fan speeds, pump flows, and chiller operations based on weather forecasts and IT load patterns. Industrial process control implemented DQN for steel mill temperature regulation, learning to maintain optimal rolling temperatures despite raw material variability, reducing energy waste 18% while improving product quality consistency. However, DQN limitations emerge in continuous action spaces. Discretizing steering angles for autonomous creates 100+ actions, causing learning instability. Policy gradient methods address this by directly optimizing policy parameters. Policy gradient methods optimize policies directly through gradient ascent on expected returns, bypassing value function estimation to handle continuous actions and high-dimensional outputs. Algorithm estimates policy gradient nabla j, theta, almost equal to 1, n, nabla log underscore, as, g, where g represents return from time t, unbiased but high variance due to reward scaling. Baseline subtraction reduces variance without introducing bias, using state value v, s, baseline yields nabla j, theta, almost equal to 1, n, nabla log underscore, as, g, v, s, where advantage a, s, a, equals q, s, a, vs quantifies action superiority over state average. Actor-critic architectures combine policy, actor, and value. Critic, networks. Critic evaluates actions, enabling low variance updates. Actor improves policy based on critic's assessments. Asynchronous advantage actor-critic, A3C, employs multiple agents interacting with environment copies asynchronously updating shared network, achieving 10x sample efficiency versus DQN Atari games while eliminating experience replay memory requirements. Real-world implementations demonstrate policy gradients continuous control capabilities. Robotic locomotion, Boston Dynamics employed proximal policy optimization, PPO, training Atlas robots walking policy through 200 years of simulated experience then trained to physical robot achieving dynamic balance on uneven terrain. PPO's clipped objective L caret clip, theta, equals E, minute, R, theta, A, clip, R, theta, 1, epsilon, 1 plus epsilon, A, where R, theta, equals underscore, AS, underscore old, S, prevents destructive policy updates maintaining stable learning, critical when physical trials expensive. Autonomous vehicle control, Waymo employs soft actor critic, SAC, for low-level steering and acceleration control. SAC's entropy regularization maximizing both expected return and action entropy produces robust handling edge cases like wet roads or sensor noise. System reduced intervention frequency 37% compared to model predictive control baselines during 10 million miles of testing. These applications reveal policy gradients' distinctive value, handling continuous actions essential for physical control, producing stochastic policies and expiration without separate mechanisms, and optimizing directly for task objectives rather than intermediate value estimates. Expiration exploitation trade-offs determine how agents balance trying new actions to discover better policies versus executing known good actions to maximize immediate rewards. Fundamental challenge where insufficient expiration convergence to suboptimal policies while excessive expiration wastes resources. Greedy strategies select random actions with probability epsilon and greedy actions otherwise, simple but inefficient in large action spaces. Boltzmann expiration selects actions proportional to softmax probabilities exp, q, s, a, o, where temperature tau controls expiration intensity, higher tau increases randomness but lacks theoretical guarantees. Upper confidence bound, UCB, algorithms maintain confidence intervals over action values selecting actions maximizing q, s, a, plus c square root, ln, s, n, a, where ns represents state visit count and n, s, a, action count, optimism in face of uncertainty driving expiration toward poorly understood actions. Thomson sampling samples action values from posterior distributions then selects greedily, Bayesian approach naturally balancing expiration based on uncertainty. Real-world expiration strategies adapt to domain constraints. Recommendation systems. YouTube's RL-based recommender employs dithering expiration injecting 5% random recommendations to discover user preferences beyond engagement maximizing content, preventing filter bubbles while maintaining 95% of recommendation quality. This expiration increased long-term user satisfaction 12% by uncovering latent interests. Clinical trials, adaptive trial designs employ Bayesian optimization balancing. Patient benefit against information gain, allocating more patients to promising treatments while maintaining statistical power. Pfizer's COVID-19 vaccine trial inspired allocation reducing trial duration 3 months while maintaining rigorous efficacy validation. Robotics, Simtorial transfer employs domain randomization during training exposing policies to randomized physics parameters. Friction coefficients, mass distributions, enabling robustness to real-world variation without explicit explain. NVIDIA's dexterous manipulation system achieved 85% success rate on physical robot after simulation-only training through randomized lighting, textures, and object properties. These strategies reveal expiration as engineering decision, not theoretical curiosity but practical necessity requiring domain-specific balancing discovery against performance degradation. Reward function design constitutes reinforcement learning's most critical yet underappreciated challenge, specifying scalar signals that align agent behavior with human intent without creating perverse incentives or reward hacking. The alignment problem manifests when agents optimize reward specifications producing unintended behaviors. Cleaning robot rewarded for absence of visible dirt learns to hide dirt under furniture or disable its own vision system. Boat racing game rewarded for hitting targets learns to loop endlessly hitting same targets rather than completing course. These failures stem from incomplete specification where reward functions captures rather than true objectives. Reward shaping provides intermediate rewards guiding learning, potential-based shaping phi, s, preserves optimal policies while accelerating convergence. DeepMind's AlphaGo employed shaping rewards for board territory control during training, then removed them for final play, maintaining policy optimality. Inverse reinforcement learning, IRL, addresses specification challenges by inferring reward functions from expert demonstrations. Maximum entropy IRL models experts as approximately optimizing unknown rewards, producing probability distribution P, TO, proportionality EXP, R, TO, over trajectories. Apprenticeship learning iteratively improves policy matching feature expectations of expert demonstrations. Real-world reward design illustrates careful engineering. Autonomous driving, Waymo specifies multi-objective reward combining safety, -1000 for collisions, progress, +1 per meter traveled, comfort, 0.1 per m/s squared jerk, and rule compliance, -10 for traffic violations, with carefully tuned weights preventing optimization of single metric at others' expense. System learned to yield appropriately at four-way stops without becoming overly conservative, blocking traffic flow. Warehouse robotics. Amazon's Kiva robots rewards for task completion time minus energy consumption minus collision penalties, preventing policies that rush recklessly or move excessively slowly. Reward weights tuned through human preference learning where operators rank trajectory pairs, guiding weight optimization. Surgical robotics. Da Vinci research systems employ reward functions combining task completion +100 for successful suturing, tissue damage penalties, -50 per excessive force event, instrument. Collision penalties, -20, and smoothness rewards, -0.01 per jerk unit, producing policies that complete tasks efficiently while maintaining sub-millimeter precision and tissue safety. These examples reveal reward design as iterative process requiring domain expertise, safety constraints, and human feedback, not one-time specification but continuous refinement as agent capabilities evolve and edge cases emerge. Deep reinforcement learning integrates neural networks with RL algorithms, enabling learning from high-dimensional observations like images, LiDAR point clouds, or joint sensor streams, bypassing manual feature engineering required by traditional approaches. Deep deterministic policy gradient, DDPG, extends DQN to continuous actions through actor-critic architecture with deterministic policies. Actor network mu, theta caret mu, outputs actions directly. Critic network Q, S, A theta caret Q, evaluates action quality. Target networks and experience replay stabilize training. Twin delayed DDPG, TD3, addresses DDPG's overestimation bias through three innovations. Clipped double Q learning, minimum of 2 Q networks. Delayed policy updates, executing actor updates less frequently than critic updates. Target policy smoothing, adding noise to target actions, preventing exploitation of Q function errors. Soft actor critic, SAC, maximizes expected return plus entropy regularization, encouraging exploration. Stuck policies with reparameterization trick, enabling efficient gradient estimation. Automatic temperature adjustment, maintaining target entropy level, adapting exploration to task difficulty. Real-world deep RL deployments demonstrate capabilities and limitations. Robotic manipulation. Google's QTOpt employed distributed DQN training on 5+ robot hours, learning vision-based grasping policy, achieving 96% success rate on diverse objects including transparent and deformable items previously considered impossible. System trained on 580,000 grasps across 7 robot arms, then deployed without fine-tuning, demonstrating sample efficiency through distributed collection. Autonomous Tesla's Autopilot employs deep RL for behavior planning. Vision transformers process 8 camera streams, generating latent representations fed to policy network, outputting acceleration, steering, and braking commands. System trained through fleet learning where 3 million vehicles contribute anonymized driving data, enabling exposure to cases, emergency vehicles, unusual road configurations. Impossible to simulate comprehensively. Energy management. DeepMind's data center cooling system employed deep RL controlling 12,000+ sensors and actuators, learning policies that reduced cooling energy 40% while maintaining temperature constraints. System deployed autonomously after safety validation with human oversight, triggers for anomalous behavior. These applications share common success factors. Massive data collection enabling statistical significance, simulation to real transfer reducing physical trial requirements, safety layers preventing catastrophic failures during learning, human-in-the-loop validation for high-stakes decisions. Failures occur when these factors neglected. Microsoft's Tay chatbot employed RL-like reward maximization for engagement leading to toxic behavior generation, highlighting necessity of safety constraints in reward design. Early autonomous vehicle RL experiments caused repeated collisions during days, necessitating simulation-only training with rigorous transfer validation before physical deployment. Model-based reinforcement learning addresses sample inefficiency, the fundamental limitation where model-free methods require millions of environment interactions for tasks humans learn in minutes, by learning dynamics models enabling planning without costly mental interaction. Planet without transition models, learns latent dynamics through recurrent state space models, deterministic recurrent state H and stochastic latent state Z encode observations. Transition model P, ZZ, H, A, predicts next latent state, observation model P, XZ, H, constructs observations, planning through latent space using cross-entropy method optimizing action sequences. Dreama V2 extends this through actor-critic learning in latent space. World model predicts rewards and continues enabling policy learning entirely from imagined trajectories. Real-world model-based applications demonstrate dramatic efficiency improvements. Robotic manipulation, UC Berkeley's Visual Foresight employed video prediction models enabling robots to learn object pushing and stacking tasks in 3 to 5 hours versus weeks required for model-free approaches. System predicts future image sequences given actions then plans sequences achieving goal images through CEM automation. Autonomous driving, Waymo employs model predictive control with learned dynamics. Models predicting vehicle trajectories under different control inputs enabling safe planning 5 seconds ahead. Models trained on 10 million miles of driving data capture complex behaviors like cut-in prediction and pedestrian intent estimation. In silico medicine employs model-based RL for molecular design. Dynamics model predicts molecular properties given structural modifications. Policy optimizes modifications maximizing binding affinity while satisfying synthesizability. Constraints, system designed preclinical candidate for idiopathic pulmonary fibrosis in 18 versus industry average for 0.5 years. Model-based approaches face reality gap challenges, simulation-trained policies degrade on physical systems due to unmodeled dynamics. Solutions include ensemble dynamics models capturing uncertainty, PETs, probabilistic ensembles with trajectory sampling, maintains multiple dynamic sampling from ensemble during planning to account for epistemic uncertainty. Domain randomization during model training exposing models to varied physics parameters, meta-learning dynamics models adapting quickly to new environments through few-shot adaptation. These techniques reduce sample requirements 10-100x versus mod methods, critical for domains where physical interaction expensive, dangerous, or time-consuming. Multi-agent reinforcement learning addresses environments with multiple learning agents, introducing strategic complexity where optimal behavior depends on others' policies creating non-stationary environments violating single-agent MDP assumptions. Centralized training with decentralized execution, CTDE, enables coordination without communication during deployment, agents trained with access to global state and other agents' observations, policies but execute using only local observations. MAPGG, multi-agent deep deterministic policy gradient, extends DD to multi-agent settings, centralized critics Q_I, O_N, A_N, trained with global information, decentralized actors _I, O_I, executing with local observations. Emergent communication develops when agents rewarded for coordination without pre-specified protocols, differential games where speakers describe images to listeners through discrete message channels. Agents develop compositional languages with emergent syntax enabling generalization to novel concepts. Real-world multi-agent applications demonstrate coordination capabilities. Autonomous vehicle coordination, Waymo's fleet employs multi-agent RL for action negotiation. Vehicles learn implicit coordination protocols yielding right-of-way without explicit communication. System reduced intersection delays 23% versus rule-based approaches while maintaining safety. Drone swarms. Skidio employs multi-agent RL for coordinated cinematography. Drones learn to maintain optimal filming angle. Avoiding collisions and occlusions. System enables single operator to control 10+ drones simultaneously for complex shots previously requiring multiple pilots. Warehouse robotics. Amazon 750,000+ robot fleet employs multi-agent RL for congestion management. Robots learn to yield appropriate narrow aisles preventing gridlock. System increased throughput 34% versus prioritized planning approaches by enabling adaptive coordination. Challenges include non-stationarity where agents' policies change during learning, causing environment dynamics to shift, credit assignment determining individual contributions to team rewards, and scarcity where joint action spaces grow exponentially with agent count. Solutions include opponent modeling predicting other agents' policies, counterfactual multi-agent policy gradients, computing advantage functions based on counterfactual baselines isolating individual contributions, mean field approximations modeling interactions with average population behavior enabling scalability to thousands of agents. These techniques enable coordination in complex multi-agent systems while respecting communication constraints and computational limitations inherent in real-world deployments. Offline reinforcement learning, batch RL, learns policies from fixed datasets without environmental interaction, critical for domains where online exploration proves dangerous, expensive, or impossible. Conservative Q-learning, CQL, addresses distributional shift where policies select actions outside dataset support causing catastrophic Q-value overestimation. CQL modifies Q-learning objective adding penalty for Q-values on out-of-distance actions. L_CQL equals L_DQN, alpha, underscore, SD, A, Q, S, A, underscore, S, A, tilde D, Q, S, A, encouraging low Q values for unseen state action pairs. Implicit Q-learning, IQL, learns value function, querying policy during training, avoiding distributional shift entirely by learning Q function through expectile regression then extracting policy through advantage-weighted regression. Real-world offline RL applications demonstrate practical value. Healthcare treatment optimization. Stanford researchers employed offline RL analyzing electronic health record 100,000+ sepsis patients learning treatment policies improving survival rates 12% versus clinician baselines without risking patient safety through online exploration. System trained on historical treatment outcome pairs then validated through retrospective analysis before prospective trials. Autonomous driving, Waymo, employs offline RL training policies on 10 million miles of logged driving data including rare edge cases, emergency braking, construction zones, impossible to safely collect through online exploration, policies trained offline then validated in simulation before limited real-world testing. Robotics, Google's large-scale robot learned offline RL training manipulation policies on 140,000+ hours of robot interaction data collected across multiple facilities, policies learned to handle novel objects without additional data collection through careful distributional shift mitigation. Offline RL challenges include limited data coverage, policies constrained to behaviors represented in data, distributional shift causing overestimation on novel state action pairs, and dataset bias reflecting suboptimal historical policies. Solutions include dataset aggregation collecting diverse data through human teleoperation or exploration policies, importance sampling weighting similarity to target policy, and pessimistic value estimation assuming worst-case outcomes for unseen actions. These techniques enable safe policy learning from existing data, transforming historical logs into training resources without risky exploration essential for safety-critical domains. Reinforcement learning applications span the transforming industries through adaptive decision-making capabilities impossible with rule-based systems. Gameplaying demonstrates RL strategic reasoning. DeepMind's AlphaGo defeated world champion Lee Sedol through Monte Carlo tree search guided by policy and value networks trained through self-play. AlphaZero mastered chess, shogi, and out human data achieving superhuman performance in hours through pure self-play. OpenAI 5 defeated professional Dota 2 teams through multi-agent RL coordinating 5 heroes with complex abilities, fog of war constraints, and 80,000 dimensional observation spaces. System played 180 years of games daily through distributing. Robotics showcases physical embodiment. Boston Dynamics Atlas learned parkour skills through deep RL in simulation then transferred to physical robot executing backflips, gap jumps, and balance recovery on narrow beams. Google's RT2 model combined vision language models with RL enabling robots to follow natural language commands, pick up the extinct animal. By grounding language in physical affordances, Tesla's Optimus humanoid robot employs RL for whole body control coordinating 28 actuators for walking, object manipulation, and tool use. Autonomous systems leverage RL for complex decision-making. behavior planning employs RL policies navigating complex urban scenarios including unprotected left turns, pedestrian interactions, and construction zones. System reduced disengagement rate 73% versus rule-based planners through adaptive behavior. Tesla's full self-driving employs RL for lane changes, merging, and navigations trained on fleet data capturing diverse driving styles and edge cases. Resource management optimizes complex systems. Google's data center cooling reduced energy consumption 40% through RL controlling thousands of sensors and actuators. DeepMind's wind power prediction increased value of wind energy 20% by forecasting output 26 hours ahead, enabling better grid integration. Electricity grid operators employ RL for demand response, balancing supply and demand during peak periods, reducing brownout risk. Recommendation systems personalize at scale. YouTube's RL-based recommender optimizes for long-term user satisfaction rather than immediate clicks, increasing time 12%. System balances expiration, showing novel content, against exploitation, showing known preferences, while avoiding filter bubbles through diversity constraints. Alibaba employs multi-agent RL coordinating recommendations across platforms. Taobao, Tmall, increasing conversion rates 9% through cross-synergy. Finance employs RL for adaptive strategies. Renaissance Technologies Medallion Fund uses RL variants for order execution, optimizing timing to minimize market impact. JP Morgan's LOXM system employs RL executing large equity trades, reducing transaction costs $150 million annually, buying orders based on predicted short-term price movements. Cryptocurrency trading bots employ RL adapting to volatile markets, though facing challenges from non-stationarity and adversarial manipulation. These applications share common patterns. Environments with delayed rewards requiring long-term planning, partial observability demanding robust state action, safety constraints necessitating conservative expiration, and non-stationarity requiring continuous adaptation. Challenges RL addresses through principled frameworks balancing expiration, exploitation, and risk management. Reinforcement learning faces fundamental challenges limiting practical deployment despite impressive laboratory tests. Sample inefficiency remains primary barrier. DeepMind's AlphaStar required 200 years of StarCraft II gameplay to reach Grandmaster level. Human experts achieve similar performance in thousands of games, highlighting orders of magnitude gap in data efficiency. Solutions include meta-reinforcement learning adaptations across tasks. Perl, probabilistic embeddings for actor-critic RL, infers task identity from initial interactions, then conditions policy on inferred task, enabling few-shot adaptation. Model-based approaches learning dynamics models for planning without environmental interaction, reducing samples 10-100x. Demonstration-guided learning leveraging demonstrations through imitation learning or inverse RL jumpstarting. Policy performance. Reward specification difficulties cause misaligned behaviors, agents optimizing literal reward functions producing unintended consequences. Solutions include reward modeling through human preference learning. DeepMind's RLHF, reinforcement learning from human feedback, collects pairwise comparisons of trajectories, then trains reward model predicting human preferences. System employed in ChatGPT alignment producing helpful, harmless responses. Inverse reward design inferring true reward functions. From specified proxies accounting for designer uncertainty. Distributional shift causes catastrophic failure when deployment environments differ from training distributions. Autonomous vehicles encountering rare weather conditions absent from training data. Solutions include domain randomization during training, exposing policies to varied conditions. Test time adaptation, adjusting policies using unlabeled deployment data. Methods quantifying uncertainty to trigger safe fallback strategies. Safety constraints demand rigorous validation. Unconstrained RL policies may discover dangerous behaviors, maximizing rewards. Solutions include constrained policy optimization, maintaining expected constraint violations below thresholds. Lagrangian methods dynamically adjust T coefficients based on constraint satisfaction. Shielded RL employing formal verification to block unsafe actions while allowing expiration in safe regions. Non-stationarity challenges emerge in multi-agent settings or changing environments. Optimal policies shift as other agents adapt or environment dynamics evolve. Solutions include modeling predicting other strategies, meta-learning adaptation strategies enabling rapid policy updates, periodic retraining on recent data maintaining relevance. These challenges don't invalidate RL but contextualize its appropriate domains. Sequential decision-making under uncertainty with sufficient data, well-specified rewards, and safety mechanisms, while highlighting need for hybrid approaches combining RL with planning, imitation learning, and formal verification for robust intelligence. Engineers must diagnose when RL suits the problem versus when alternative paradigms better address sample efficiency, safety, or reward specification requirements, selecting tools aligned with problem rather than defaulting to RL for all sequential decision problems. Emerging frontiers push reinforcement learning toward greater robustness, efficiency, and applicability. Offline to online RL bridges batch learning with limited fine-tuning, policies trained on static datasets then safely adapted through constrained online interaction, critical for domains where initial safety essential but perfect offline performance unattainable. Decision transformers reframe RL as sequence modeling problem, autoregressive transformers predicting actions given past trajectories and return-to-go prompting, achieving competitive performance without explicit value functions or policy gradients while enabling flexible tuning on desired outcomes. Foundation models for RL learn general world models from diverse data enabling rapid adaptation to novel tasks, similar to language model pre-training then fine-tuning. Google's RT-1 model trained on 130,000 robot trajectories across multiple embodiments enabling zero-shot transfer to novel robots. Causal reinforcement learning integrates causal inference to distinguish correlation from causation, enabling policies robust to distributional shift by learning invariant mechanisms rather than spurious correlations, critical for safety-critical domains where spurious correlations cause catastrophic failures under distribution shift. Symbolic RL combines neural perception with symbolic planning. Neural networks extract features from observations. Symbolic planners reason over abstract states enabling systematic generalization and sample efficiency. DeepMind's Agent 57 achieved above-human performance on all 57 Atari games through neurosymbolic architecture combining neural networks with explicit exploration bonuses and metacontroller selecting between exploration strategies. Embodied AI research investigates how physical interaction shapes learning. Robots manipulating objects develop intuitive physics understanding impossible from visual data alone. MIT's Learning from Play approach has robots interact with plus household objects building internal models of object affordances and dynamics that transfer to novel manipulation tasks with 3x faster adaptation than visual-only learning. These frontiers address core limitations while expanding RL's applicability to complex, real-world domains where robustness, safety, and sample efficiency are essential for deployment beyond controlled laboratory environments. The field's trajectory points toward integrated architectures combining RL's adaptive decision-making with complementary paradigms, planning for long-horizon reasoning, imitation learning for sample efficiency, formal methods for safety guarantees, producing agents capable of robust, safe, and efficient decision-making in complex real-world environments where uncertainty, partial observability, and safety constraints define the operational landscape. Slide 11. AI.708, Data Mining. Data mining transforms massive, unstructured datasets into actionable knowledge through systematic discovery of hidden patterns, relationships, and anomalies, extracting signal from noise where traditional querying fails to reveal insights buried within terabytes of transaction logs, streams, and customer interactions. Unlike database querying that retrieves explicitly requested information, show me customers who purchased product X, data mining autonomously discovers unexpected relationships. Customers who buy diapers on Friday evenings also purchase beer, without predefined hypotheses. On statistics that test specific hypotheses with small samples, data mining explores vast datasets generating hypotheses through computational pattern recognition at scales impossible for manual analysis. Unlike machine learning that optimizes predictive accuracy for specified tasks, data mining emphasizes interpretability and business discovering rules humans can understand and act upon rather than black box predictions. The CRISP-DM, cross-industry standard process for data mining, framework structures this discovery process through 6 iterative phases: business understanding, defining objectives and success criteria, data understanding, profiling datasets for quality events, data preparation, cleaning, integrating, and transforming raw data, modeling, applying algorithms to extract patterns, evaluation, assessing business value beyond statistical metrics, deployment, integrating discoveries into operational systems. Walmart's market basket analysis exemplifies successful data analyzing 2.5 million daily transactions revealed unexpected affinity between beer and diapers purchased Friday evenings, leading to strategic product placement increasing sales of both categories 15%. Discovery emerged not from hypothesis testing but from exhaustive pattern enumeration across transaction space. Data pre-processing constitutes the foundation determining mining success. Raw data rarely arrives analysis ready due to missing values, inconsistencies, noise, and heterogeneous formats requiring systematic transformation before pattern discovery. Data cleaning addresses quality defects. Missing value imputation replaces nulls through mean, mode substitution, numerical, categorical attributes, replacing missing age values with dataset median 34.7 years, regression-based prediction leveraging correlations, predicting missing income from education and occupation, or deletion when missingness exceeds thresholds, removing records with greater than 50% missing values. Outlier identifies anomalies distorting patterns. Statistical methods flag values beyond mu plus or minus 3 sigma. Credit card transactions greater than $10,000 when mean equals $127. Clustering-based methods identify points distant from cluster centers. Network traffic packets with 99th percentile size indicating potential DDoS. Isolation forests efficiently isolate anomalies through random feature partitioning. Visors fraud detection flags transactions requiring less than 10 partitioning steps versus 50 plus for normal transactions. Data integration merges heterogeneous sources resolving conflicts. Schema matching aligns attributes across database. Mapping, cust_ID, in sales DB to client_no, in CRM, entity resolution identifies duplicate records representing same entity, matching J. Smith and John Smith at same address through probabilistic matching. Conflict resolution applies rules prioritizing authoritative sources. ERP systems override spreadsheet entries for inventory counts. Data transformation normalizes scales and creates informative features. Minutemax normalization compresses values to 0, 1, range essential for distance-based algorithms, customer income $30,000 to $150,000 0.0 to 1. Z-score standardization centers values around mean with unit variance. Sensor readings with mu equals 24.3 degrees C, sigma equals 2.1 Z sat smiley x, 24.3, 2.1, discretization converts continuous attributes to categorical bins, age, 0 to 17, 18 to 54, 35 to 54, 55 plus, enabling association rule mining, attribute construction creates. Derived features capturing domain knowledge, RFM scoring, recency equals days since last purchase, frequency equals purchases, year, monetary equals total spend. Deduction decreases volume while preserving analytical value. Dimensionality reduction through PCA transforms correlated features into orthogonal components. 100 survey questions 10 principal components capturing 85% variance. Numerosity reduction replaces data volume with compact representations. Regression models summarizing 1 million with 3 parameters. Sampling selects representative subsets. Stratified sampling preserving class distribution for rare fraud cases. Real-world pre-processing illustrates necessity. Targets pregnancy prediction model required integrating point-of-sale transactions, coupon redemptions, and registry data while cleaning inconsistent product categorizations. Is unscented lotion, skincare or baby care? Pre-processing consumed 80% of project time but enabled discovery that vitamin supplements and unscented lotion purchases predicted pregnancy with 87% accuracy before customers announced pregnancies. Classification discovers decision boundary rating predefined classes. Supervised learning where algorithms learn mapping from feature vectors to categorical labels using label training examples. Decision tree induction constructs hierarchical classifiers through recursive partitioning. ID3 algorithm selects attributes maximizing information gain IG, S, A, equals H, S/S, H, S, where H, S, represents entropy, plog P. C4.5 extends ID3 handling continuous attributes through binary splits and missing values through probabilistic distribution. CART employs Gini impurity Gini, S, equals 1, P squared for split selection. Real-world classification applications demonstrate business impact. Credit scoring, FICO employs decision trees analyzing 200-plus applicant features, income, debt ratio, payment history, approving loans with 99.2% accuracy while maintaining model interpretability for regulatory compliance. Regulators require explanatory denials, churn prediction. Telecom companies like Verizon analyze customer usage patterns, call duration, data consumption, support tickets, through random forests identifying high-risk customers, month-to-month contracts with 3 support calls, month, enabling targeted retention offers reducing churn 18%, $4.2 million annually per million customers, medical diagnosis, Mayo Clinic's sepsis prediction system employs gradient boosting analyzing vital signs, lab results, and comorbidities through 15-node trees achieving 94% sensitivity enabling nurses to understand risk factors triggering alerts, elevated lactate plus cardia plus fever. Rule-based classifiers express knowledge as human-readable if then rules. Ripper algorithm induces rules through sequential covering growing rules to cover positive examples then removing covered instances. CN2 employs entropy-based rule induction. Retail applications leverage rule interpretability. Amazon's recommendation engine generates rules like if customer purchased laptop and mouse then recommend laptop bag, with 78% confidence driving 35% of revenue through cross-selling. Fraud detection systems employ rules like if transaction amount greater than $5,000 and foreign country and new merchant then flag for review, 92% of fraudulent transactions while minimizing false positives through confidence thresholds. Bayesian classifiers apply Bayes' theorem for probabilistic classification. Naive Bayes assumes conditional independence P, xc, equals P, xc, enabling efficient computation, despite unrealistic independence assumption, achieves competitive accuracy on text classification. Email spam filtering exemplifies naive Bayes' success, analyzing word frequencies. Free appears in 42% of spam versus 3% legitimate mail, computes P, spam message, proportionality P, spam, P, word spam, blocking billions of messages daily with greater than 99.9% accuracy. Medical diagnosis systems employ Bayesian networks modeling dependencies between symptoms and diseases. Fever increases probability of infection but decreases probability of hypothermia, improving diagnostic accuracy 15% versus naive Bayes by capturing relationships. Support vector machines find maximum margin hyperplanes separating classes in high-dimensional feature spaces. Kernel trick phi, x, times phi, y, equals k, x, y, enables nonlinear separation without explicit transformation. Radial basis function kernel k, x, y, equals xp, xy squared, handles complex boundaries. Financial applications leverage SVM robustness. Algorithmic trading systems classify market regimes, bull, bear, sideways, through SVM analyzing technical indicators achieving 83% accuracy enabling adaptive strategy selection. Credit risk assessment employs SVM handling nonlinear relationships between debt ratios and default probability outperforming logistic regression by 7% on imbalanced datasets with rare defaults. Ensemble methods combine multiple classifiers improving accuracy and robustness. Bagging trains classifiers on bootstrap samples reducing variance, random average 500. Decorrelated trees, boosting sequentially corrects errors through weighted retraining. Ada boost increases weights for misclassified instances, stacking blends heterogeneous base learners through metaclassifier. Capital One employs random forests with 500 trees analyzing 200 applicant features achieving 9.2% credit approval accuracy while maintaining stability against data drift. Individual trees might overfit noise but ensemble averages converge toward true signal. Kaggle competitions consistently demonstrate ensemble superiority with 78% of winning solutions employing gradient boosting or random forests. Models continuous relationships between predictors and numeric outcomes, discovering functional dependencies where classification boundaries prove inadequate for granular prediction. Linear regression models relationships through weighted sums y equals plus x minimizing sum of squared errors sigma, y, squared, coefficients marginal effects, underscore income equals 0.003 means each $1,000 income increase raises predicted house price $3,000. Real-world regression applications drive business decisions. Real estate pricing, Zillow's Zestimate algorithm analyzes 7.5 million home features, square footage, bedroom count, neighborhood characteristics, through regularized linear regression predicting values within 1.9% median error for on-market homes. Economic forecasting, Federal Reserve employs multivariate regression modeling GDP growth as function of interest rates, unemployment, and consumer confidence guiding monetary policy. Decisions, demand forecasting, Walmart analyzes historical sales, promotions, holidays, and whether through regression models reducing stockouts 16% by accurately predicting product demand at store SKU level. Polynomial regression captures nonlinear relationships through higher-order terms y equals plus x plus x plus x, interaction terms xx model synergistic effects, price times advertising spend. Pharmaceutical applications leverage polynomial regression. Drug dosage response modeling employs quadratic terms capturing diminishing returns. Effectiveness increases with dose but plateaus then declines due to toxicity. Trial analysis models patient response as function of dosage, age, and comorbidities through interaction terms revealing subgroup effects. Elderly patients respond differently to standard doses. Regression trees partition feature space into rectangular regions with constant predictions. CART algorithm recursively splits space minimizing mean error within regions. Piecewise constant approximation enables interpretation of complex relationships. Manufacturing applications employ regression trees. Semiconductor yield prediction models wafer characteristics, thickness, doping concentration, through regression trees identifying critical thresholds. Yield drops 40% when thickness less than 145 micrometers, enabling process adjustments. Energy consumption forecasting employs regression trees modeling building usage patterns identifying that HVAC energy spikes when outdoor temperature greater than 28 degrees Celsius and occupancy greater than 80% enabling targeted conservation measures. Support vector regression extends M to continuous outputs. Insensitive tube defines margin where errors, epsilon incur no penalty. Kernel functions enable nonlinear regression. Renewable energy applications leverage SVR. Wind power forecasting employs SVR with RBF kernels predicting turbine output 36 hours ahead based on weather forecasts, hill generation, and turbine characteristics. DeepMind's system increased value of wind energy 20% by enabling better grid integration through accurate forecasting. Solar irradiance prediction employs SVR modeling cloud cover, atmospheric pressure, and seasonal patterns achieving 92% accuracy critical for grid stability with high renewable penetration. Ensemble regression methods combine multiple predictors improving accuracy. Gradient boosting machines sequentially correct residuals through decision trees. Random forests average predictions across decorrelated trees reducing variance. Financial applications demonstrate ensemble superiority. Algo trading systems employ gradient boosting predicting stock price movements 5 minutes ahead through 200 technical indicators achieving 58% directional accuracy, beating random 50%. Insurance premium calculation employs random forests modeling risk factors, driving history, vehicle type, location, achieving 12% better loss prediction versus linear models by capturing nonlinear interactions. Young drivers in sports cars in urban areas carry multiplicative risk. Clustering discovers natural groupings within unlabeled data. Unsupervised learning revealing inherent structure without predefined classes through similarity-based partitioning. Partitions data into k-spherical clusters minimizing within cluster sum of squares set membership symbol cx squared. Lloyd's algorithm iteratively assigns points to nearest centroid then recomputes centroids until convergence. Real-world clustering applications drive business segmentation, retail customer segmentation, target 70 million customer purchase histories through k-means identifying 12 natural segments, budget-conscious parents, tech enthusiasts, luxury shoppers, enabling personalized marketing campaigns increasing sales 15 to 20% through targeted promotions. Genomic research employs k-means clustering on gene expression profiles grouping patients by their subtypes of cancer leading to precision oncology treatments where therapies target specific genetic mutations rather than organ location alone. Image compression leverages k-means reducing color palette. GIF format employs k-means clustering 24-bit colors into 256 representative colors achieving 75% size reduction minimal perceptual loss. Hierarchical clustering builds nested cluster hierarchies through agglomerative, bottom-up, or divisive, top-down, approaches. Linkage criteria define intercluster distance. Single linkage, minimum pairwise distance, produces chaining effects. Complete linkage, maximum pairwise distance, creates clusters. Average linkage balances extremes. Ward's method minimizes within cluster variance. Biology applications leverage hierarchical clustering. Phylogenetic tree construction clusters species based on genetic sequence similarity revealing evolutionary relationships. single-cell RNA sequencing employs hierarchical clustering groupings by gene expression profiles identifying novel cell subtypes driving disease progression. Researchers discovered rare immune cell populations in tumor microenvironments through hierarchical clustering enabling new immunotherapy targets. Density-based clustering identifies arbitrarily shaped clusters in noisy data. DBSCAN, density-based clustering of applications with noise, defines clusters as dense regions separated by sparse areas, parameters epsilon, neighborhood radius, and minute points, minimum points for core point, control cluster granularity. Cybersecurity applications leverage DBSCAN's noise handling. Network intrusion detection analyzes patterns identifying anomalous clusters representing zero-day attacks without prior knowledge of attack signatures. Darktrace system employs DBSCAN detecting subtle deviations from normal behavior identifying threats missed by signature-based systems. Retail analytics employs DBSCAN identifying customer segments with irregular purchasing patterns, seasonal shop, gift buyers, enabling targeted campaigns during relevant periods. Gaussian mixture models employ probabilistic clustering through weighted sum of Gaussian distributions. Expectation maximization algorithm iteratively estimates component parameters maximizing likelihood. Soft clustering assigns probabilities of membership across clusters. Market research applications leverage GMM flexibility. Nielsen employs GMM clustering consumer survey responses identifying overlapping segments. Consumers simultaneously value price and quality, enabling nuanced messaging strategies. Financial portfolio construction employs GMM identifying asset classes with stick membership enabling risk diversification across partially correlated assets. Spectral clustering leverages graph Laplacian eigenvalues for complex manifold learning, constructs similarity graph then partitions through eigenvector analysis of normalized Laplacian. Social network analysis employs spectral clustering identifying communities within massive graphs. Facebook employs spectral clustering on 2 billion user friendship graph identifying interest-based communities. Photography enthusiasts, marathon runners, enabling targeted content distribution. Citation network analysis clusters academic papers by research topics revealing interdisciplinary connections invisible keyword matching alone. Association rule mining discovers co-occurrence patterns in transactional data, uncovering relationships between items frequently purchased, viewed, or accessed together without causal claims. A priori algorithm efficiently mines frequent item sets through antimonotonicity property. Subsets of frequent items must be frequent, generates candidate K item sets from frequent K1 item sets then prunes infrequent candidates. Support confidence framework evaluates rules. Support XY equals P, X union set symbol Y, measures prevalence. Confidence XY equals P, YX. Measures reliability. Lift, XY equals P, YX, P, Y, measures independence. Lift 1 indicates positive correlation. Real-world association mining drives retail optimization. Walmart's market basket analysis revealed customers purchasing diapers frequently buy beer on Friday evenings, a counterintuitive leading to strategic product placement increasing sales of both categories 15%. Amazon's customers who bought this also bought. Recommendations stem from a priori mining frequent item sets with minimum support 0.5% generating rules like phone case, screen protector, wireless charger, with 78%. Confidence driving 35% of total revenue through cross-selling. Healthcare applications mine electronic health records identifying medication co-prescriptions. Mayo Clinic discovered patients prescribed metformin for diabetes frequently receive statins for cholesterol management. Support 12%. Confidence 89%, enabling screening for cardiovascular risk factors. FP growth, frequent pattern growth, improves a priori efficiency through compact FP tree representation, compresses transaction database into prefix tree preserving item set frequencies, mines frequent patterns through pattern fragment growth without candidate generation. E-commerce applications leverage FP growth scalability. Alibaba processes 1 billion daily transactions through FP growth identifying seasonal patterns. Support for winter coat, gloves increases 400% November-January, enabling dynamic inventory allocation across warehouses. Streaming service recommendation engines employ FP growth on histories identifying content bundles. Stranger Things, Dark, Black Mirror, with 82% confidence driving binge-watching behavior through strategic content placement. Sequential pattern mining extends association rules to temporal sequences. GSP, generalized sequential pattern, algorithm discovers subsequences respecting temporal order. Spade employs vertical data format for efficient mining. Web analytics applications leverage sequential mining. Google Analytics identifies common navigation paths, homepage, product page, cart, checkout, with 68% support enabling UX optimization, reducing cart abandonment 22%. Netflix mines viewing sequences, identifying that users watching documentary series frequently watch related fiction content within 48 hours. Our Planet Avatar, enabling strategic content recommendations, increasing engagement 18%. Constraint-based mining incorporates domain knowledge, guiding pattern discovery. User specifies constraints like minimum profit margin, maximum item count, or semantic relationships, reducing search space and improving relevance. Retail applications employ constraint-based mining. Target specifies constraint-only mine rules with profit margin 15%, filtering unprofitable cross-sells. Pharmaceutical companies mine sequences with constraint, only include FDA-approved drug combinations, ensuring clinical safety while discovering novel therapeutic regimens. Anomaly detection identifies rare deviations from normal patterns, critical for fraud prevention, system health monitoring, and quality control where outliers represent events of significant interest. Noise to remove. Statistical methods model normal behavior then flag deviations. Gaussian models assume normal distribution, flagging points beyond mu plus or minus 3 sigma. Grubbs test identifies single outliers in small datasets. Box plots flag points beyond Q1-1.5 IQR or Q3 plus 1.5 IQR. Financial applications leverage statistical detection. Credit card fraud systems flag transactions beyond 3 sigma from customers' historical spending patterns. Visa's system analyzes 150 billion annual transactions, detecting suspicious activity within 50 milliseconds while maintaining 99.999% up to $25 billion in annual fraud losses. Manufacturing quality control employs statistical process control charts monitoring production metrics, flagging points beyond control limits indicating equipment drift requiring maintenance. Distance-based methods identify points distant from neighbors. K nearest neighbors distance d x equals distance to k nearest neighbor. Points with large d x deemed anomalous. Local outlier factor LOF compares local density to neighbors' densities, identifying points in sparse regions. Network security applications leverage distance methods. Intrusion detection systems analyze network traffic features, packet size, frequency, destination diversity, flagging hosts with LOF greater than 2.5 indicating potential compromise. Darktrace enterprise immune system employs distance-based detection identifying subtle behavioral deviations indicating insider threats missed by signature-based systems. Density-based methods identify points in low-density regions. DBS can labels points not belonging to dense clusters as noise, anomalies. Isolation forests efficiently isolate anomalies through random feature partitioning. Fewer partitioning steps required to isolate anomalies versus normal points. Industrial applications leverage isolation forests. Siemens monitors 10,000 plus sensors across factory equipment using isolation forests, flagging anomalies within milliseconds. Sudden voltage dip at substation combined with frequency deviation triggers automatic circuit breaker isolation, preventing cascading blackout. Gradual temperature rise in transformer detected weeks before failure, enabling scheduled replacement, avoiding $1 million emergency repair and 8-hour outage affecting 50,000 customers. One class SVM learns boundary around normal data in high-dimensional space. Kernel methods map data to feature space then find maximum margin hyperplane separating data from origin, points falling outside boundary flagged as anomalies. Healthcare patients leverage one class SVM. Sepsis prediction systems monitor ICU patients' vital signs, learning normal physiological patterns for each patient then flagging deviations indicating early sepsis onset 6 hours before clinical symptoms, reducing mortality 28% through early intervention. Medical imaging systems employ one class S, detecting novel pathologies absent from training data by identifying images with reconstruction error exceeding threshold. Streaming anomaly detection addresses temporal data with concept drift. Adaptive windowing adjusts window size based on detection performance. Ensemble methods combine detectors trained on different time windows. IoT applications leverage streaming detection. Smart grid operators monitor 10 000+ sensors across transmission network detecting anomalies in real time despite evolving normal patterns. System adapts to seasonal load variations while maintaining sensitivity to genuine faults. Predictive maintenance systems analyze sensor streams from wind turbines bearing wear patterns 14 days before failure despite varying operational conditions, wind speed, power output. Text mining extracts patterns from unstructured textual data, transforming documents, social media, and customer feedback into structured insights through natural language processing integrated with data mining techniques. Document pre-processing transforms text into analyzable representations. Tokenization segments text into words. Punctuation, stop word removal eliminates high-frequency low-content words. The is stemming reduces inflected forms to root. Running, run, lemmatization maps variants to dictionary base using morphological better, good. Social media analytics applications leverage pre-processing. Brandwatch processes 95 million daily posts where tokenizer handles hashtags, #Black Lives Matter, Black Lives Matter, emojis, red heart heart, and code switching, Don Esther Albano, to accurately track brand across cultures. Pre-processing choices directly impact accuracy, preserving negation cues, no evidence of metastasis. Through specialized tokenization prevents catastrophic misclassification in clinical text. Analysis. Feature extraction converts text to numerical vectors. Bag of words represents documents as frequency vectors, TF-IDF, term frequency inverse document frequency, downweights common terms while upweighting discriminative terms. N-grams capture word sequences preserving phrase meaning. Topic modeling through latent dirichlet allocation, LDA, discovers latent topics as word distributions. Business intelligence applications feature extraction. Financial institutions analyze earnings calls through LDA identifying latent topics, supply chain constraints, labor shortages, digital transformation, tracking topic prevalence over time revealing strategic shifts before explicit announcements. Customer feedback analysis employs TF-IDF identifying discriminative terms, battery life, in negative reviews versus camera quality in positive reviews, guiding product improvement. Priorities. Sentiment analysis classifies subjective opinions. Lexicon-based methods employ sentiment dictionaries assigning polarity scores. Machine learning classifiers combine lexical features with syntactic patterns. Learning approaches leverage contextual embeddings. Retail applications leverage sentiment mining. Amazon analyzes 500 million annual product reviews through aspect-based sentiment analysis identifying that 68% of negative smartphone reviews mention battery life versus 22% mentioning camera, enabling targeted improvements increasing customer satisfaction 15% for subsequent models. Airline reputation management systems process 2 million annual tweets identifying sentiment toward baggage handling dropped 22 points after fee increases while in-flight service sentiment remains stable guiding service recovery investments. Entity relationship extraction identifies structured information, named entity recognition, NER, tags persons, organizations, locations. Relation extraction identifies semantic relationships between entities. Apple acquired Beats. Legal applications leverage extraction. JP Morgan's Coin platform processes 12,000 commercial loan agreements extracting 150 data points per document, parties, amounts, dates, covenants, reducing manual review from 360,000 hours to seconds. Contract analysis systems identify obligations. Tenant shall maintain premises, enabling automated compliance checking across enterprise contract portfolios. Topic evolution tracking analyzes temporal dynamics. Dynamic topic models capture topic drift over time. Burst detection identifies sudden topic popularity spikes. Public health applications leverage evolution tracking. CDC monitors social media and news sources tracking disease mention bursts identifying emerging out 7 to 10 days before official reports. 2014 Ebola outbreak detected through Twitter mention spikes in West Africa before WHO announcement. Pharmaceutical companies track adverse drug reaction mentions identifying safety signals earlier than traditional pharmacovigilance systems. Web mining extracts patterns from web content and usage, discovering relationships invisible through surface browsing alone. Web content mining analyzes page text and metadata. Search engines employ content mining indexing billions of pages through inverted indexes mapping terms to documents. Sentiment analysis of product reviews informs purchase decisions. Extraction populates knowledge bases. E-commerce applications leverage content mining. Amazon's search relevance employs content mining, analyzing product titles, descriptions, and customer reviews to match queries with relevant items. Query: comfortable running shoes for flat feet, matches products with descriptions containing arch support, use mentioning flat feet, even without exact keyword match, increasing conversion 27%. Web structure mining analyzes hyperlink topology. PageRank algorithm models web as Markov chain where pages importance proportional to probability of random surfer landing there. Its algorithm identifies hubs, pages linking to many authorities, pages linked by many hubs. Search engine applications leverage structure mining. Google's original PageRank revolutionized search quality by weighting links as votes of confidence. Page with 100 diverse inbound links ranks higher than page with 1,000 links from single domain. Modern search engines combine content and signals, achieving 92% precision on navigational queries. Web usage mining analyzes server logs and click streams. Session identification reconstructs user visits from IP timestamps. Path analysis identifies common navigation sequences. Market basket analysis applied to page views discovers co-viewed content. Digital marketing applications leverage usage mining. Netflix analyzes viewing sequences, identifying that users watching documentary series frequently watch related fiction content within 48 hours. Our Planet Avatar, enabling strategic content recommendations, increasing engagement 18%. E-commerce sites employ path analysis, identifying points in checkout funnel. 68% abandon at shipping options page, enabling UX optimization, reducing cart abandonment 22%. Social network mining analyzes relationship graphs. Community detection identifies densely connected subgroups. Influence analysis identifies key spreaders. Link prediction forecasts connections. Marketing applications leverage network mining. Facebook identifies communities through spectral clustering, enabling targeted advertising to interest-based groups. Photography enthusiasts receive camera ads. Influencer marketing platforms employ influence analysis, identifying users with high betweenness centrality whose endorsements drive proportionate engagement. Fashion brand campaign leveraging micro-influencers identified through network analysis achieved 4.2x ROI versus celebrity endorsements. Data mining scalability addresses challenges of massive datasets through algorithmic and architectural innovations, transforming techniques designed for gigabytes to petabytes while maintaining interactive response times. Sampling reduces data volume while preserving statistical properties. Simple random sampling selects records uniformly. Stratified sampling preserves class distribution critical for imbalanced datasets. Fraud detection. Reservoir sampling maintains representative sample from infinite stream. Financial applications leverage sampling. Visa processes 150 billion annual transactions but employs stratified sampling, retaining 100% of fraud cases while sampling 0.1% of legitimate transactions, enabling model training on manageable datasets without losing rare event representation. Sampling reduced training from 72 hours to 45 minutes while maintaining 99.3% fraud detection accuracy. Dimensionality reduction compresses feature space. Principal component analysis, PCA, transforms correlated features into orthogonal components ordered by variance explained. Autoencoders employ neural networks with bot layers learning compressed representations through reconstruction loss. Genomic applications leverage dimensionality reduction. Single-cell RNA sequencing generates 20,000 gene expression measurements per cell. PCA reduces dimensions to top 50 principal components, capturing 85% variance. TSNE further compresses to 2, revealing distinct cell types as spatial clusters, enabling biologists to identify novel cell subtypes driving disease progression. Compression ratio 400:1 enables interactive exploration of million-cell datasets on standard laptops, accelerating discovery cycles from months to days. Parallel and distributed computing partition across multiple processors. MapReduce framework separates processing into map, filter, transform, and reduce, aggregate phases, enabling fault-tolerant distributed execution. Spark improves MapReduce efficiency through in-memory computation and directed acyclic graph execution. Retail applications leverage distributed mining. Walmart processes 2.5 million point-of-sale transactions daily through Spark MLib, identifying product affinities. A priori algorithm parallelized across 1,000 node cluster completes mining in 8 minutes versus 14 hours on single server, enabling daily pattern updates reflecting changing consumer behavior. Distributed K-means clustering 100 million customers in 22 minutes versus 9 hours sequentially enabling real-time personalization. Stream mining processes continuous high-velocity data. Sliding windows maintain recent observations. Landmark windows retain all data since specified time. Exponential weighting emphasizes recent data. Applications leverage stream mining. Siemens monitors 10,000+ sensors across factory equipment processing 1 million measurements second through stream clustering detecting emerging fault patterns in real time. System employs ClueStream algorithm maintaining microclusters updated incrementally enabling anomaly detection within 50 milliseconds for preventing equipment damage. Approximate mining trades precision for speed. Sampling-based approximations provide statistical guarantees. Sketching data structures. Cand-minute sketch. Hyperlog estimate frequencies and cardinalities with bounded error using sublinear space. Advertising applications leverage approximation. Google processes 8.5 billion daily search queries employing hyperlog estimating unique searcher count with 0.5% error using 1.5 kilobytes memory versus 12 gigabytes required for exact counting, enabling real-time audience measurement for ad targeting without prohibitive storage costs. Cand-minute sketch estimates item frequency in clickstreams identifying trending topics within seconds of emergence. Data mining evaluation validates discovered patterns beyond statistical significance, ensuring business relevance, actionability, and robustness against spurious correlations. Statistical validation assesses pattern reliability, support and confidence threshold for weak associations. Chi-square tests evaluate independence between item sets. Permutation testing assesses significance by comparing observed patterns against randomized data. Retail applications employ statistical validation. Target requires minimum support 0.5% and confidence 70% for market basket rules in patterns reflect genuine customer behavior rather than random co-occurrence. Permutation testing validated beer diapers correlation by comparing observed support against 10,000 randomized transaction sets confirming p less than 0.001 significance. Business validation assesses practical utility. Lift measures predictive power beyond line. Lift 1 indicates positive correlation. Conviction quantifies deviation from independence. Actionable insights drive measurable business outcomes. Financial applications leverage business validation. Capital One evaluates credit scoring rules requiring minimum lift 1.8 ensuring rules provide meaningful discrimination beyond randomment. Rules failing business impact thresholds. Reducing defaults by less than 0.5%, discarded despite statistical significance preventing model complexity without value. Robustness validation tests pattern stability, cross-validation assesses consistency across data partitions, temporal validation ensures patterns persist over time, sensitivity analysis tests stability under parameter variations. Healthcare applications employ robustness validation. Mayo Clinic validates sepsis prediction rules through temporal validation. Training on 2019 data, validating on 2020 data, testing on 2021 data ensuring rules generalize across years, changing patient populations and treatment protocols, rules failing temporal validation discarded preventing deployment of time-bound patterns. Domain expert validation incorporates human judgment, clinicians review medical patterns for clinical plausibility, marketers assess customer segments for strategic relevance, engineers verify anomaly patterns against constraints. Manufacturing applications leverage expert validation. Siemens employs domain engineers reviewing anomaly detection patterns identifying that temperature spikes correlated with maintenance schedules rather than equipment faults, preventing false alarms and unnecessary downtime. Expert validation reduced false positive rate 63%, maintaining 94% true positive rate. Ethical validation assesses societal impact. Fairness audits measure performance disparities across demographic groups. Privacy impact assessments evaluate re-identification risks. Transparency requirements ensure explainability for high-stakes decisions. Financial applications employ ethical validation. Credit scoring systems undergo fairness audits measuring approval rate disparities across ethnicities. Models with greater than 5% disparity require mitigation through adversarial debiasing or reweighting before deployment complying with Equal Credit Opportunity Act. Ethical validation prevented deployment of model that achieved 99.5% accuracy but exhibited 18% approval disparity against protected classes. Privacy-preserving data mining enables pattern discovery while protecting individual confidentiality, balancing analytical utility against re-identification risks through algorithmic and policy safeguards. Anonymization techniques remove or gate direct identifiers. K-anonymity ensures each record indistinguishable from K1 others on quasi-identifiers. Zip code, birth date, gender, L-diversity ensures sensitive attributes exhibit diversity within anonymized groups. T-closeness requires sensitive attribute distribution within group close to global distribution. Healthcare applications leverage anonymization. HIPAA safe harbor requires removal of 18 identifiers before data sharing. Research datasets employ K-anonymity with K equals 50 ensuring patient records indistinguishable within groups of 50 preventing re-identification while enabling population health studies. Anonymization enabled sharing of 10 million patient records across 200 hospitals for cancer research without privacy breaches. Differential privacy adds calibrated noise to query responses guaranteeing statistical indistinguishability between datasets differing by single individual. Epsilon parameter controls privacy utility trade-off. Smaller epsilon equals stronger privacy. Laplace adds noise proportional to query sensitivity divided by epsilon. Technology applications leverage differential privacy. Apple employs differential privacy in iOS collecting usage statistics without identifying specific users. Emoji usage statistics aggregated across millions of devices with epsilon equals 2 ensuring individual connections indistinguishable. System collected 1.2 billion usage events while providing mathematical privacy guarantees preventing re-identification attacks. Secure multi-party computation enables joint analysis without revealing raw inputs. Garbled circuits allow parties to compute functions over private inputs. Homomorphic encryption enables encryption on encrypted data. Financial applications leverage secure computation. Banks collaborate on fraud detection through secure multi-party computation analyzing transaction patterns across institutions without sharing customer data. System identifies cross-bank fraud rings while maintaining individual bank data confidentiality. Pilot reduced cross-fraud 34% without privacy compromises. Federated learning trains models across decentralized devices without centralizing data. Devices compute local updates on private data. Central server aggregates updates without accessing raw data. Technology applications leverage federated learning. Google Keyboards borns personalized word predictions from individual typing patterns while keeping raw data on device, transmitting only model updates to central server. System improved next word prediction accuracy 18% while preserving user privacy, critical for global deployment across jurisdictions with strict data localization laws. Synthetic data creates artificial datasets preserving statistical properties. Generative adversarial networks trained on real data produce synthetic records. Differential privacy ensures synthetic data provides privacy guarantees. Research applications leverage synthetic data. U.S. Census Bureau released 2020 census data through differential privacy calibrated noise to counts. Synthetic data generation created privacy-preserving microdata enabling researchers to conduct analyses impossible with aggregated tables while preventing re-identification. Enabled 200+ research projects without privacy breaches. Data mining applications span industries transforming decision-making, driven insights, retail optimizing inventory and personalization, finance detecting fraud and managing risk, healthcare improving diagnostics and treatment, manufacturing ensuring quality and predicting failures. Retail applications drive revenue through personalization and optimization. Targets pregnancy prediction model analyzed patterns identifying 25 products, unscented lotion, vitamin supplements, cotton balls, predicting pregnancy with 87% accuracy before customers announced pregnancies. Model enabled targeted coupon campaigns increasing sales 22% among pregnant customers while maintaining privacy through aggregated analysis. Walmart's market basket analysis identified 200+ product affinities driving planogram decisions. Placing beer adjacent to diapers increased sales of both categories 15% while reducing aisle congestion by 8% through strategic placement. Financial applications protect assets and optimize decisions. Visor's neural network fraction analyzes 150 billion annual transactions in real-time, flagging suspicious activity within 50 milliseconds while maintaining 99.999% uptime, preventing $25 billion in annual fraud losses. JP Morgan's LOXM system employs reinforcement learning, executing large equity trades, minimizing market impact, reducing transaction costs $150 million annually. Credit scoring systems analyze 200+ features through gradient boosting, achieving 99.2% approval accuracy while maintaining regulatory compliance through interpretable rule extraction. Healthcare applications improve outcomes and reduce costs. Mayo Clinic's sepsis prediction system analyzes vital signs, lab results, and comorbidities through decision trees, achieving 94% sensitivity, enabling nurses to intervene 6 hours before clinical symptoms, reducing mortality 28%. IBM Watson for Oncology analyzes patient records and medical literature recommending treatment with 93% concordance versus tumor boards. System reduced treatment planning time from 45 minutes to 8 minutes. While maintaining clinical accuracy, predictive readmission models analyze discharge summaries, medication lists, and social determinants, identifying high-risk patients, enabling targeted interventions, reducing 30-day 18% and saving $4,200 per avoided readmission. Manufacturing applications ensure quality and optimize operations. Siemens predictive maintenance system analyzes vibration patterns from factory equipment using isolation forests, predicting bearing failures weeks before catastrophic breakdown, reducing unplanned downtime 40% and extending component lifetime 22%. Foxconn employs computer vision and clustering, inspecting iPhone components at 200 parts minute, detecting microscopic defects, scratches less than 10 micrometers, with 99.998% accuracy, reducing field failures 76% while eliminating human fatigue-related errors. General Electric's digital twin technology employs regression models simulating jet engine performance under varying conditions, enabling predictive maintenance scheduling, reducing unscheduled maintenance 35%. Telecommunications applications reduce churn and optimize networks. Verizon analyzes customer usage patterns, duration, data consumption, support tickets, through random forests, identifying high-risk customers, month-to-month contracts with 3 support calls month, enabling targeted retention offers, reducing churn 18% and saving $4.2 million annually per million customers. Network optimization systems employ clustering, identifying or congestion patterns, enabling dynamic resource allocation, reducing dropped calls 27% during peak hours. Energy applications optimize generation and consumption. DeepMind's wind power prediction increased value of wind energy 20% by forecasting output 36 hours ahead, enabling better grid integration. Smart grid systems employ anomaly detection, monitoring 10,000+ sensors across transmission network, detecting faults within milliseconds, preventing cascading blackouts. Demand response systems employ regression forecasting household consumption, enabling dynamic pricing, reducing peak demand 15% without customer discomfort. These applications share common success factors: domain expertise guiding pattern interpretation, rigorous validation ensuring robustness, human-in-the-loop design maintaining oversight for high-stakes decisions, continuous monitoring detecting performance degradation from concept drift, ethical consideration addressing privacy, fairness, and transparency. Failures occur when these factors neglected. Target's pregnancy prediction model inadvertently revealed teenager's pregnancy to father through targeted coupons, highlighting necessity of privacy safeguards and contextual sensitivity. Financial models trained on pre-2008 data failed during crisis due to concept drift, demonstrating necessity of continuous retraining on recent data. Healthcare models exhibiting racial bias due to unrepresentative training data, emphasizing necessity of fairness. Audits before deployment. Data mining thus functions as powerful tool requiring responsible engineering practices, data curation, rigorous validation, bias mitigation, preservation, and human oversight, to deliver societal benefit while minimizing harm across domains where pattern discovery drives critical decisions affecting individuals, organizations, and society.